Are we live? Are we live? Okay, nice. All right. Thank you so much, everyone, for joining in. Before I start introducing myself and stuff like that, let's just verify that my audio is reaching YouTube. So if you're watching the stream live, just feel free to comment in the live chat. Say hello and hi and stuff like that. And most likely it's already working. So I'll just go ahead and start the introduction. So hi, everyone. Welcome to ADCx India 25. This is the second time we are doing this. So that's not a small thing to happen. Because yeah, streak is everything in life. But before we get to the main part, let's just ask a question. How many of you have attended ADC or ADCx India before? Raise of hands. Okay, nice. And how many of you are attending it for the first time? Oh, nice. That's really cool to know, because last year our aim was to kind of spread the word and make sure that the community grows, and looks like we have slightly succeeded in that. Before I give an introduction of the whole set of event of what the agenda for today is and some of the rules and stuff like that, I think it's important that you hear from Bobby, who is the chair of ADC. But the thing is, he's not available with us here today in person, but we live in the world of technology and ADC. So let's just actually meet him virtually. And I just need to ping him so that he's aware that I'm coming his way. So coming your way. Nice. All right. So basically, this is an application called Gather Town, which is used for the virtual version of the main ADC event. This allows us to attend the talks remotely without having to travel to the location where event is happening. And this is for the main conference. So last November in 2024, the event was in Bristol. There were like really good participation in person, but there was also an amazing participation through this app from all over the world. So if you see this page, is all virtual. We have like recreated the Bristol city here. And actually, let's find where Bobby is. So if I just right click on his name and select locate on map, okay, he's probably like chilling in a restaurant. So this Urban Tandoor restaurant actually is an actual place in Bristol. So Ralph, the designer of this whole thing, he actually made this virtual space. So actually just go and say hi to him. I need to stop locating. Oh, there he is dancing. This is fun. Okay, I can also dance with the Z key, I guess. All right, so we are having some fun. Some of the audience members are also dancing. For the live stream audience, is just like you cannot see them. Who is seeing this anyway? All right, so let's actually just have some chat with Bobby. So I'll just unmute myself so I can start.
Hi, Prashant. I'm not sure if you're speaking, but I can't hear you. But hi, everyone.
Hi, hello, Bobby. I hope I'm audible.
You are.
Amazing. So I'll hand it over to you to make the introductions. So please go ahead.
Thank you, Prashant. I really appreciate it. And welcome to ADCx India 2025. Very excited about what's going to happen today. Actually, really excited. This is our second ADCx India. So very excited that we've come back for the second year. And Prashant, this is all largely due to your stewardship here. And I really look forward to ADCx growing in the years to come. So great job. And I'm so happy you can all join us here at the Indian Music Experience Museum in Bengaluru, India, as well as streaming live right now on the Audio DevCon YouTube channel. So the whole event today is streamed live and then later will be posted to view offline. So excited by all that. I wanted to say thanks to the sponsors that make this happen, but also to all the volunteers that Prashant and team has put together. And I heard you had a wonderful Music Hack Day India, and I look very forward to seeing the videos of the outcome of the hack, as well as winners. I'm assuming will be announced during this, so all great stuff. I am Bobby Lombardi. I am your chair of the Audio Developer Conference. Also wanted to share here, and actually this is the first time sharing this publicly, is that the Audio Developer Conference will return to Bristol, UK again this year in 2025 in November 10th through the 12th. And if you're interested in that event and you want to know about speaking at the event, doing an academic paper, or maybe joining us online. And there's also speaking and poster session opportunities online as well as in person. So you can join from anywhere in the world. Please go to audio.dev and sign up for the newsletter, and you'll get more information about that event. So enough about ADCx or ADC 25. I will hand it back to Prashant, and I'm wishing you a wonderful day today with ADCx India.
All right, thank you so much, Bobby. There are claps going on that you'll probably hear in the live stream, and I'll get back to my rest of the presentation. Thank you so much for taking the time.
Take care, everyone.
All right, so that was the message from Bobby. I'm just going to do a little bit of housekeeping here. So I hope my screen is still getting streamed. Okay, awesome. So just a little bit of more fun stuff. Right, so that was the message from Bobby Lombardi. And again, like you saw, we were able to just do the remote conversation quickly. And the whole ADCx Gather experience is always like this. So in November, when the main conference is happening on 10 to 12, at the exact same time, there will be an online version. And it's not just for attending. Even if like you're a speaker who cannot travel all the way to Bristol, you can actually apply for a talk. And if your talk gets accepted, you can actually sit in your home and give the presentation. As long as your internet is stable, it's all going to be fun. Coming to like a quick recap of 2024, this rewind thing is not copyrighted yet, luckily, because almost every app is doing it. But this is from 2024, January, just a year ago. Before, and that time our agenda was that, hey, can we bring people with similar interests together? And looks like we were able to like do it pretty successfully. So we'll be taking a picture similar to this today as well, and we'll let you know when that happens. All right, so basically after the event last year in Jan, there's a feedback for some reason. Is this mic on? Okay. I can probably mute my screen. Yeah. All right. So basically, after the event last year, we actually saw some really interesting things happen. Like we saw a lot of attendees who got internships and jobs like right during the event. There were also a few startups that showed up, and some of the folks from people who are making new startups and companies were also present during the hack day, and I'm sure they'll be here in the audience as well. There used to be like many communities that used to do some events in small pockets across India. And then because they met together like at the same place, they started collaborating. So now there are very like cross community collaborations also going on. And there are a lot of local initiatives. There are WhatsApp groups, there are Discord servers. Basically the agenda that we had in 2024 to like somehow bring this all together worked. And for those of you who were here, I said the word ecosystem like at least 1 million times, and that at least has started moving in that direction. So we are really like happy that worked out. There have been also like book club sessions and online workshops, all being hosted by people on their own. So that's a really cool thing that happened. Another thing that happened last year was the ADC mentorship program. Anyone who was a mentor or mentee at the ADC mentorship program? Okay, a few, right? So, I mean, the agenda for this mentorship program was that people who are in the industry can guide people who want to enter the industry. This will happen again, by the way. The forms will be open next year, like this year sometime. But I will share all those details during the conclusion. ADC 24, the main conference used to be in London, but last year it moved to Bristol. And in 2025 also it will continue to happen in Bristol. And that was a lot of fun. The talks and stuff will be available on the ADC's YouTube channel, so you can take a look at that. So before I hand over to our first speakers, a quick agenda for today. The introductions is done, so we'll strike that off. We'll have some really cool talks and keynote. The talks will be 18 minutes long, and they will have like 5 minutes for Q&A, and the keynote would be 50 minutes long in total. There will be networking breaks for half an hour, so you all can like make ideas, maybe make companies, who knows. There will also be like towards the end of the day, there'll be hack day winner presentations. So for the last 2 days, there were a few people who participated who were like making some projects. So the winner of those, like the top 3 teams will be presenting. So that's going to be interesting as well. And at the end of the day, for the in-person audience only, sorry folks who are watching on YouTube, there'll be a museum tour, which is also part of the networking activity. Just be aware that when you're asking questions during Q&A, wait for the handheld mic to reach you so that the question that you ask gets recorded in the YouTube live stream. That sounds good? All right, you can say yes or no, it's fine. Yes. Okay, nice. Just making sure I have not missed anything. All right, so have fun, make connections. We have like shared a QR code there in the back of the room, which is only for the in-person audience. The agenda for the QR is it has a Google form where you can mention your name, your area of interest, and your expertise. And everybody here who has access to the QR code can see the responses in the sheet and they can try and meet you, right? So please don't share that link online. It's only for all of us. And please don't share any personal information because the sheet is publicly accessible. It's again an optional activity. If you want, use it. If not, completely your choice. Take pictures. When we send out an email after the event, there will be a link to OneDrive folder where you can upload the pictures. So feel free to take pictures and videos, but please be mindful. Like if somebody is not comfortable and they are saying no, please let them have their personal space. And Arjun will be helping out with the pictures as well. So if you don't want to your pictures clicked, just let him know and he'll make sure that's not done. And yeah, help us keep the schedule on time. Because we have like 18 minutes talk and we have to wrap up things on time, please make sure that once you're done with the break, head back to the performance theater so that we can continue with the next talks. So yeah, those were the quick things to just note about. You'll also see some cables going all over the place. So please don't step on it. Please be mindful of it. And this tag, so actually the Indian Music Experience Museum is an open space. People actually also show up and like see the museum around. So if you wear the tag, then the IME staff will know that you are an attendee for the conference and you don't have to pay again to enter. Okay, so this is very important for all of us. Yeah, I think with that, we can start off with the first set of talks. Our first talk is by Gopikrishnan S and Bharat, who will be talking about breaking the communication barrier for India's deaf community with AI audio apps. We'll take a quick short break so that we set things up for them and we'll be good to go soon. So thank you so much and again, welcome to the event.
Hi, I hope I'm audible. My name is Gopi. I'm a machine learning engineer and I'm currently an AI fellow here at People Plus AI. So, People Plus AI is a non-profit initiative by Nandan and Rohini Nilekani Foundation. We work on building AI digital public infrastructure for solving societal problems. So, I have with me Bharat Shetty, my co-anchor in the project. So, interesting fact about both of us, we both are coming from the overall spectrum of deafness. We are this project Envy is our attempt to solve a real world challenge we face every day in our life. So let's dive into the project. So based on the internet, it says that there are 65 million plus deaf people in India, but unfortunately more than that we don't have many information, statistics and all. But I think it's more than 65 million people are there. But when people hear about deafness, people just think that okay, it's just a deafness, but there are different spectrum, and unfortunately in India and mostly around the world, there are no specific solutions catered for each of these spectra, and that's causing a lot of issues like in education, employment. In my school and college life, I struggled a lot to listening to lectures and taking notes and all. It's still there. It's still not solved there. So we both are coming from a spectrum called oral spectrum. I'll just, for your context, I'll just give you an explanation of what it is. So the oral spectrum includes individuals with a poor speech clarity, so people who can't speak properly, and then it includes people with excellent to medium to excellent hearing challenges or speech medium. So people with a poor speech clarity or 80 to 90% speech clarity, but then narrow to medium hearing loss. So these are people who can understand you by unconsciously lip reading. It's not a superpower. We can just do that from here and there. But again, unconsciously, based on practice, unconsciously we'll be able to do a combination of lip reading and somewhat we hear. And then there are people with a profound hearing loss. They are also in the oral spectrum. But the key fact is that we cannot build a one-size-fits-all solution for all spectrums. So one need to understand the problems and then again figure out how we can tackle these problems. So that is one thing. So let's dive into how deaf people in the oral spectrum communicate. So lip reading, like I said, it's an art, but again it varies from people to people and situation to situation. Sometime I can properly do the lip reading plus what I can hear to understand you, but sometimes it will be very hard. So what we do, we use real-time captioning tools. But there are issues like so my co-anchor Bharat is using a real-time captioning tool. But the problem with the real-time captioning tool is the rate of words or sentences, it varies. Say for example, I talk a lot and I talk sometimes very fast. And if that's the situation, the real-time captioning tool will be bombarding you with the live transcriptions. And conversation is not just understanding what the other person is speaking. It's basically taking the visual cues, their expressions, and then if somebody is presenting something here, I need to constantly switch my attention from the transcription screen to the presentation screen to the people around me. So it's a very big challenge and it causes this cognitive fatigue. It's still there. And so a lot of folks with higher hearing loss, they cannot speak well. So you can think it like okay, they will be speaking in a muffled voice, or basically you won't be understanding them properly. So what I have seen is my speech is kind of okay, but I still have issues with pronouncing some words. But again, these folks, what they do is they write or type and then show it to you. So the problem there is like there will be a lag in conversation, and it takes a lot of time for the normal hearing folks to read. So two problems will happen. The conversation health will be that energy, excitement will lose. That chance is there, And second thing is hearing folks often don't pay attention to the chat and all. Say for example, if somebody is in the online chat, I mean the online folks will understand, because you folks might be typing something, questions and all, but yeah, we are not able to see that thing. So that happens a lot. So these are two challenges we face every day. Now I will dive into the demo, and then let's get into the specifications and all.
Sunva is an intelligent communication tool we built for solving communication challenges for deaf people in India. At its core, Sunva provides intelligent live transcription and seamless text-to-speech interface for making communication easy. Now, let's see Sunva in action. I'm going to click on the microphone and show how it works. Hi, I'm Naima. I'm an employee here at People Plus AI. Sunva is an intelligent communication tool built for helping deaf people in India communicate better with the help of AI. See here, I introduce myself. As you can see, Sunva Notice the Above transcription is a casual intro which can be simplified for quick reading. A deaf person can have a glance at the simplified conversation and get back to the other person without reading the whole sentence. I can click here on the original and it shows me the original text. If I want the summarized text, I'm going to click this button. As you can see, it works really well. Now, let's see another scenario. TensorFlow is a machine learning library we are using at work. We use the library for training AI models and deploying AI models. Here, as you can see, instead of simplifying the text, Sunva highlighted important keywords, helping a deaf person to read the sentences quickly without losing important information by glancing over the important keywords. As you can see, it's highlighted TensorFlow, machine learning library and AI models. Again, you can click on original to see the original text and click on enhanced for the highlighted text. Now, let's see a different mode. Due to the lack of early intervention and lack of speech therapy, a lot of deaf people unfortunately have non-standard speech. For helping them to express what's in their mind, Sunva provides a seamless text-to-speech interface. I'm going to click on the keyboard icon, pick my gender and type into the box. I'm going to make some grammar mistakes to show Sunva's capability.
I am Neema, an employee at People Plus AI.
I can once again click on the button to show the original text and the enhanced text. A deaf person with non-standard speech can type what's in their mind. They don't have to write full sentences or worry about grammar, spelling, etc. Sunva will complete the partial sentences, correct spellings and grammar, and then speak it aloud for you. I welcome all of you to check the Sunva AI tool and interact with our work. Thank you.
Sunva is
An intelligent
Sorry, I did something. Yeah, I'm back. So, thank you. So, as you can see, it's basically so in at People Per Se, we have something called a plus one philosophy. So it says that instead of reinventing the wheel, basically we take something that is abundant here and then add a plus one to it, so that we can, with the smallest effort, or with the small resources, we can make a huge impact. So in till 2 years before, this speech to text capabilities and real time processing and all, it was not that good, and every time a new application comes in, I install it and see, okay, will it help me attend an event or something. But then most of the time it helped, but again that cognitive fatigue and all was there. But again, thanks to the transformer architecture, the technology behind ChatGPT and all of these new audio applications, audio AI applications, now real-time processing of these transcriptions, and in parallel using LLMs to simplify, concise, and all these things are possible now. So basically what we do there is, I will explain the architecture a bit. So the text-to-speech communication, previously we had to write the whole thing and then press the button to for the system to speak it aloud. Now we are trying to use LLMs so that a person like Bharat or me can just type a few things. The LLM will fix the issues, expand it, and then ask it aloud. And I have seen so right now we are using some APIs and all, but I have seen better and better models are coming in. So now the text-to-speech models, it basically sound like a robot or something, but eventually it will get better and better, giving deaf people with the speech irregularities a very nice voice. And for the highlighting and concise part, what we do is, instead of seeing the full transcription bombarded to you and taking you back from looking at the speaker or like looking at the presentation screen, we use LLMs to see, okay, this particular thing I have said can be concised or not. If it can be, we will concise it. If it cannot be concised, say for example somebody is talking about some big audio engineering pipeline and all, if I simplify it, I will lose the whole essence. So there what we try to do is just highlight important terms, so I can still quickly glance and then come back to you. So this is the whole architecture. So the technology is used. So at People Plus AI, we are fully research based. So we wanted to quickly build a prototype and take it to the deaf volunteers and test, and then based on their feedback only we can iterate properly. So most of our efforts was with APIs, available APIs. We used Grok. It's a fast inference API for speech, LLMs and all. We used that for automatic speech recognition in English. And there's we have partnered both the Navana API, so for Kannada, Hindi and other languages. And then we are trying Google ASR as well now. For the LLM layer, we are using OpenAI GPT-4o model and then for English, and we tried Claude Sonnet and all for Hindi, but again it's still not that working good. So text-to-speech layer, we used AI for Bharat Indic TTS model. It's an open source fine-tuned variant of Coco TTS model. We use it for English, Hindi, Kannada and Malayalam. So as you can see, Naima typed it in English, but again you can use Manglish English or what do you call Tamil English, I don't know, but again you can do that thing, but it will still do the TTS thing thanks to the AI for Bharat models. We really need your help. So as you can see in the demo, the ASR have latency. Our real-time audio speech pipeline is still not that good because we still need to quickly get it to the deaf volunteers, take their perspectives and then iterate. So right now we are doing the user search part. So in parallel, we would like to get help from open source volunteers with expertise in audio speech pipelines. We need your help in building a good real-time speech pipeline. And the English model works kind of good. We still need some fine-tuning, but the real problem is with the Indic models, because as you can see, the summarization and all, it will work, but highlighting important terms. But it's not just summarizing, including key part and not missing the important part, that kind of things we still need to collect data set, fine-tune LLMs and all for doing that thing. We need help. And then this is another big project we want to take after this thing. So still fun thing is like I still struggle with Google Assistant, Siri and all. Because I think most of you have understood what I said, but again the computer systems are still struggling to understand my voice, and for people with a higher level of non-standard speech, it is very hard to use these technologies as well as communicating better. So we need to find and collect audio speech data of non-standard speech and fine-tune model can be that can be used for speech to text transcriptions and all. So yeah, here we need help. So Sinva is a fully open source project and People Plus AI. You can find it here. It's People Plus AI /Sinva. And we are looking for speech audio pipeline engineers, front-end engineers, back-end engineers for contributing to this effort. Yeah. Thank you so much, ADCx, and yeah, it's wonderful to be here. And I'm so glad that this kind of efforts are happening, because people like me speech is something, I mean, listening and responding is a big challenge, and this kind of conferences, it will bring together people with like-minded thoughts and ideas, and then eventually we can build similar tools and all. Thank you so much.
Yeah, I think we can take some questions. So any questions? Okay, Arjun.
Hi, thank you so much for the talk. So people who are interested in contributing to the project, how do you support the computation for the AI model training?
People who want to contribute to the project, how do you support the computational capacity?
So we have some. So we have a machine, GPU machine in on premise in the office, but it's mostly for inference. But yeah, we have cloud credits and all for fine tuning and all. So based on the requirement, so this whole project is volunteer driven. Bharat and I are project anchors, and then we bring in open source volunteers and contributors to work with us. So based on the request, we can get credits. We have AWS as a GPU credit, so we use that for fine tuning and all.
Yeah.
Hi, have you considered incorporating lip reading as well, or that's just a waste of compute? It's only audio or visual as well?
Yeah, so this is an interesting question. So so this is just one dimension. The conversation, I mean, so basically eventually the goal is like can we integrate multiple signals? So sign language is one option, lip reading is one option, but eventually in general how we deaf people communicate is based on multiple signals. So sometimes we anchor into the lip reading, or sometimes your speech. Some people say people have this weird idea that okay, if I speak louder, the deaf person will understand. But the thing is not. I mean, it's a bit more complex. Like say for example, some people, even if they are loud, their tone and all, it still won't be able. So eventually the goal is how can we integrate these kind of signals as well, like lip reading, and a combination of that thing will eventually help. We have seen some interesting project, like there's some project AI model that do not take any kind of sound. It will just take the lip reading and then generate captions. So that kind of models are coming in. So the future is exciting. So eventually we are trying to see if we can integrate these kind of signals as well to the project. I think, yeah.
So since you are trying to make the process seamless of conversation, right? One question I have is, let's say the AI makes a mistake and something else is coming there. What's the correction mechanism? How is that being handled right now?
So
in terms of if the AI makes a mistake, how is that correct as of now?
This is something, this is part of our user research as well. So so in US and all, we have a system called CART. So for education, so what they do is they keep a stenographer in the classroom, and while the lecturers speak, they type in very fast. Stenography you can type very fast. That's how it used to be done before the pre-chat GPT era. So we are trying to get inspired from that as well. Say for example, can we add online or offline manual characters in a combination with AI? And maybe the AI can actually for every token output we can get a threshold or accuracy or something. So based on that, maybe can we show okay, something that could be wrong in red, so that this your other fellow here or other student or your classmate can notice it, and then like a beehive mind. Say, for example, there are two deaf people in the classroom and there are 10 students, other students. So not everybody have to spend time here, but again, people can randomly fix these issues. So these need to be researched. So we are taking this to user research and then try to see how these models are performing, and based on that we need to build these pipelines, and some of these cannot be solved with the technology, but again with a combination of manual plus AI thing. Yeah, it's a very interesting question, because in a classroom or in a workplace, understanding things, misunderstanding thing or that kind things will mess up the whole experience, right? So we are trying to figure out how we can do this thing. Yeah, thank you.
Yeah. Any other questions? I think I saw one more raised hand. Okay. Yeah, I think it's a really important topic to talk about. So thank you so much.
So thank you so much. Yeah.
Yeah, round of applause for Gopikrishnan and Bharat.
Hi, so we are starting with our next talk. Just before that, one announcement. So People Plus AI have shared some of their ideas that they do want to work on. We'll share it over email in our, like after the event. So hopefully some of you guys can definitely contribute to their very inspiring project. And our next talk is by Rasagy Sharma, Information Echoes. Yeah, go ahead.
Thank you. Thanks, everyone. I want to start with a very simple question, which is, what does a black hole sound like? And for some of you, this might be a familiar thing. You may have seen some interesting variations of listening to space, which when I first found out about it, just broke my mental model, because I always imagined space is soundless, and that's clearly a myth. But here is a small piece, and I'll play it, and then maybe we talk a bit more. And now you know what a black hole sounds like. What's interesting about this piece is it's not just looking at an image of some space and then translating it into audio, but this is actually based on sound waves that were collected, which is essentially based on pressure. And there's some really interesting work that's been happening at NASA and many other space agencies, where they're trying to take complex data about space and turning it into something that can be essentially transformed into audible hearing space. Or like hearing range, and so you can start to interestingly consume things that otherwise would be, graphs, numbers, or interesting processes. And that's really what my talk is gonna start with, which is information echoes. There is a lot of interesting ways in which data, which is predominantly seen in visual form, is now being explored in auditory and many other sort of modalities. And it doesn't just have to be things like this, which is complex data, but it could also be something more playful or personal. A quick bit about me, I'm Rasagy Sharma. For the last 13, 14 years, I've focused on making data sort of meaningful, which is by doing data visualization, charts, dashboards and stuff like that at companies like Microsoft, Barclays, Grameener, Mapbox, and then more recently at Capital One. However, about a decade into doing this, I kind of started getting bored, because I was only making things inside a screen on like a two-dimensional space. So I went back to my design school, NID, where I decided to teach a very short module on taking data beyond 2 dimensions. What this really meant for most of my students was to make things like this. This is a project by Kirti. He took all the books that he owned and essentially arrange them in a way to encode whether he's read the book or not. And so suddenly I have a physical representation of my Goodreads read, unread list. He also then made it into a light installation in his room. So the more he reads, the more light comes into his room, the more illuminated he gets, right? So suddenly now data is turned into like light and physical representation. Another student of mine, Parvati, she looked at her Netflix binge watching history, sort of counted every genre and how many times she was watching a particular episode, and then knitted a blanket so she can be a bit more cozy when she maybe consumes more Netflix, right? Both of these were tangible in nature. They were taking data from like a screen to something more physical. And then I had one student called Ridit who did something even more interesting. He decided to talk about his food ordering and delivery sort of data. And he's been stress eating since he came to Bangalore. He also started eating a lot more by ordering, and he wanted to, represent that feeling in an interesting way. And interesting is again understatement here. So here is what this project turned into. This is called Binge Beat. It's a sonification of his food ordering data for the last 1 year.
Bon appetit.
Every time he ordered for a friend, there is that sound. A group is a doorbell, and then when he orders for himself, there's a birth. Now the next bit is going to be extremely disgusting, and that is by design. So this starts with some of the time that he spent in Kolkata, which is his hometown. At that point, he's having food at home. There isn't any food ordering happening. So you see this nice beats. Every week is sort of represented by 2 bars, and then he moves to Bangalore, which is the college, and you start to notice some differences. And so that was the first order that he made. More orders for friends. For himself. On his birthday, a huge order, and I'll not sort of torture you into hearing the whole piece, but you're welcome to listen to it. It's a lot of fun, and the reason why I think it's very interesting is, when was the last time a bar chart made you feel disgusted, right? And so this really got me excited about data sonification, and this idea that this whole field of turning data into sound could yield very interesting results. What I started to notice after I saw this project was that data sonification is actually all around us. It's not something that is only made in these like weird, quirky NASA space videos or burp sounds, but Slack notifications, data sonification. Every time an event is happening, it is communicating it with an abstract sound. Your typical clock. It's using a sound that mimics the real world, so the sound of the clock, and repeating it multiple times to communicate what hour it is. And even this sound, which I think some of you might be very familiar with. Yeah, that's your typical car sensor, which you would use in parking. And suddenly it's using a data set of how far the sensor is from a particular obstruction, and varying tempo and a few other volume-based properties of audio. These are 3 different techniques. So while the NASA space work is often audification, so they'll take a signal and they'll essentially transform it or squish it to make it audible in human range. Slack notification is an example of an ear con. It's essentially an abstract sound driven by data. The grandfather clock is an auditory icon. It is mimicking real world and then converting data to sound. And the car sensor is parameter mapping. It's taking data and then tweaking or mapping or controlling one of the many properties of audio that we can play with. While ear cons and auditory icons are super easy, they're also fairly limited because there aren't so many different sounds that you could make. But parameter mapping opens a huge world of interesting experiments. So here is what a very simple parameter mapping experiment would look like. This is done in a tool called Two-Tone. It's an online tool, very simple to use, and you can upload a data set like I have here, where this is Delhi's AQI data for roughly 2 years. And on the top, I have the average of PM 2.5 data. So this is one of the many aspects you look at in AQI. And the second is the average of SO2 data. What I've also done is map the PM 2.5 to a violin sound. So, higher it goes in octave, the more annoying somewhat it sounds, like it will be more sharper. And this SO2 sound, I could actually even filter. So I filtered and only kept the points where the SO2 was essentially crossing the mandated weekly safe limit. So every time it goes beyond the average weekly limit, you can hear some sort of a bass, in the background. So this is what it sounds like. And so this is data of AQI turned into something that we could listen to. Now, one of the limitations of using tools like Two-Tone is, of course, that you're limited by a few instruments. And sometimes the data that you have may not really map to an instrument. Like if you're looking at something like AQI, which is not a very good thing. You don't want to make it sound like a violin or a piano, etc. And so this is one of the limitations of easy to use tools which allow you to plug and play things. But there's also a lot more that you'll start to notice. One, that it really just sounds like data sonification, right? It's turning very clearly sounds into it. It isn't really pleasant to hear. And there is a variation between taking data and making sounds or noise, and then taking data and making it into music. And that's, I think, where a lot more understanding of music helps. A lot more custom sort of tooling also helps. And then a lot more mixing and matching of multiple data sets could also work. So while simple parameter mapping could just be a single data set turned into one of these elements, a more complex data set with multiple layers could also be used to really tune it well to form music. And I am no expert in making music, so I relied on somebody else who's a much better expert. So Miriam Quick and Duncan Gear, they are both been running this project called Loud Numbers. It started off as a small project, a podcast, it became a conference, and now I think they run a studio. And they've been turning a lot of data set into some really interesting music. So here is a small piece that I'll play, which is called Boom and Bust. It's also on their podcast. I'm happy to share links later. And it's a sonification of US economy. So they really wanted to think, what does money sound like? And they change the sort of sounds based on when economy is going well versus when it's in recession versus when it's out of recession. There's also multiple layers of other data like Dow Jones data added, some context like president's speech talking about economy, some small indicators of wealth gap, richest, poorest, expanding or collapsing. And then there's also some beats around US elections which happen at a very regular period, so it's very easy to bring that into sonification. So I'll play a small bit of it and then we can talk more.
This is Boom and Bust.
It's the economy, stupid!
Now you see the economy is shifted, it's descending. And now there is economy coming out of recession, so that on sort of comes in as well.
It will be essential for all of us to live and work in lower temperatures.
And then you have like a president's speech also overlaid. Now this, I think, comes much closer to what might sound like music, yet has immense amount of data enriched. However, it also makes it very hard to understand unless somebody really explains it piece by piece. So I recommend you to listen to their podcast where they first introduce every element, and then you can listen to the whole sonification piece, which is much longer, and actually start to notice some of these details, a bit better. So I want to conclude by highlighting when I think data sonification is a good choice and really why you should be using this. So in terms of when, it works really good for some specific kind of data sets. Of course, temporal data set very easily translates to sound, which is also fairly linear and temporal. If your data set is sequential, it also works really well. Periodic data tend to bring some rhythm in the sound that it is generating. And sometimes when it's a simple trend, it's easy to hear it as well. So the AQI one is very simple. It really increases, then falls, increases and falls. So it becomes easier to actually notice the pattern if I'm just listening to it and not seeing it at all. There's also some multidimensionality. So the one that we just heard has multiple layers of data added. And you can actually start to notice details once you get a bit more familiar with it. And there is a lot of opportunity to do real-time data sort of turned into audio live, right? So there's also that bit. And in terms of why, I think there is, of course, this emotive element. So for me, I love to see like playful data representation. So there is a lot more emotive aspect that comes in. I also think there's a huge accessibility bit, and I loved some of the conversation that we were having just before my talk. And I think there is opportunity to take data visualization, which is predominantly only visual field, and make it accessible to many other sort of domains, right? It also makes it memorable. Like I'm hoping even today when we all go for lunch and if somebody burps, somebody will be thinking about Ridit's data sonification. And the real-time nature can actually be very useful as well. So if you think about hospitals where there is a heart rate monitor, it is an example of data sonification. And it's even more useful because a person who is supposed to be running around the hospital may not always be looking at the screen to see the actual heart rate. And so the sound is a good way for you to focus somewhere else, but then notice if there is a change or there is a need for you to pay attention. But for, just to end it, it could just be for fun. And I'm going to end with some very simple piece that I've been thinking about and doing it for a data visualization conference that's upcoming in India, where we wanted to make a unique sort of signature for every attendee. And we wanted to make something visual first, but I thought, why not push it to also make something that is audible? So we did something very simple. We are mapping each letter to a position in the alphabet, vary the frequency a bit, and then we suddenly get interesting sounds for every name. So from A to Z, we're going to do frequency mapping. It'll sound like this. Fairly simple and straightforward. That means that my name, Rasagy, which has letters that alternate between end of the alphabet and starting of the alphabet, A and R, is going to sound like this. So suddenly I have a small tune that is my name. I could take Prashant's name, for example, and his name is interesting because it has two letters that are a bit more on the right side, and then one A, and then two letters and one A. So it has this 2 1 2 1 2 beat. Suddenly we have something for Prashant, and we could probably also do it for the conference, right? So maybe next year, or when we do ADCx India next time, there is an audio that plays for every speaker for the conference, and it'll be somewhat like this. So with this, I'm gonna try and end with some obvious stuff. How do I get started for those who are interested? Two-Tone was the UI-based tool that I showed. P5.js is a very good intro to creative coding, and I've made the sound piece that I just showed you from names with p5.sound. There's also Tone.js, which gives you a lot more power. There is SonicPy and Pure Data that some of my other friends in creative coding and Algorave, etc., tend to use. And for folks who've done a bit more creative coding, there's also processing, which was a slightly earlier version, and it used to use Minim, which is also very powerful. I will share links to all of these resources on the right, but Loud Numbers is something I highly recommend if this has piqued a bit of your curiosity. There are some portals like sonification.design which actually archive a lot of data sonification examples. And then there is some sonification handbook. There are some people like Data Driven DJ, which have been doing a lot of experiments. And there's a nice NASA documentary called Listen to the Universe, fairly short video, which talks a bit more about space audification. And I want to end with this particular quote, which is most of us need to listen to the music to understand how beautiful it is. But often that's how we present statistics. We just show the notes. We don't play the music. And I think it works well for data visualization. It works even better for data sonification. And this is by Hans Rosling, who was a wonderful sort of data pioneer. And, his TED Talk is wonderful as well. Thank you. Any questions? Anybody is more curious about some of the work? I'm happy to talk more.
Yeah, thank you for the great talk. I'll probably listen to, I will make that like my SMS tone or something, so every time I'm called, so I can listen to it. So my question is, like, when you think about like mapping data, like when you used A to Z,
yeah.
How did you, so as of now, you are changing frequency. Is it note based, each sound? And how do you plan on other type of data? Like what note, is it always musical? Is it always based on C major or some scale?
Yeah.
Or is it always frequency based where you don't have to worry about it to be like actually in
Mapping
the musical
like
notes and
exactly.
stuff like that? So how do you make a decision on that when you were exploring different types of sonification?
Yeah, so I think if you look at two-tone, it is a lot closer to actual sounds that make sense from like a synth or an instrument perspective. So all of this was like, I think it's C3 octave, the ones that I was playing with violin. The piece that I've made here for names is actually just frequency values. So I've just taken a name, I'll take each letter. A is given one number like 1. B is 2, C is 3, all the way to Z, which is 26. And I essentially take that range 1 to 26, and then I map it to say 600 hertz to 1000 hertz. and then I get a tune. So there, I don't think it is directly mapping to say a piano's exact frequencies or a pitch that I could control, but those would also be very easy to manage. I started with doing something very simple and playful, so it is using the bare bones of just frequency manipulation, but I have a whole oscillator which is essentially running, so I could always tweak it around to add maybe different aspects to it. There are other things that I would love to see. For example, if we do it for ADCx, apart from just the letters changing some sound, maybe there is some genre of music that might come in where we think about what is a person's area of interest, like we were filling in the form, and maybe that tweaks the sound itself, or maybe an instrument or some other style. So I think there are a lot of opportunities, and before we get into doing this for more formal use cases, I think it is important for us to play so that we start to notice which work, which don't work. So these are, I think, good experiments to play around with.
All right, thank you.
Thank you.
Any other questions?
Hi, it's not really a question but a comment, because it gave me such a cool idea, like as a composer, now this is a different way how you think about writing ideas. Because now you can look at text and data to create melody lines, for instance.
Yeah.
So thank you for the inspiring talk. Yeah, it was very interesting.
Thank you. Yeah, and I am fairly noob at making music, so I would love to see what people who actually understand music a lot more do. And happy to always jam and help out, maybe build prototypes if that's helpful. Yeah.
Thank you.
There's one more question.
Yeah.
Can you give some more examples of real-time data where it's performance dependent? For example, the proximity sensor is pretty cool, where it changes your performance. So like, are there any stock traders who listen to the music of the market, or anything else where it matters?
I have not seen stock traders listen to music, but I think that is going to save a lot of people's time, because otherwise they're always staring on the screens looking at stocks, right? And yeah, like I would pair it up with maybe notifications are easy for us to think about, because that's something that we look at. But instead of visual notifications, turning them into audios would work great. There's this whole world of places where if it's a big factory, you would have a representation of all the factory's health in a way, in a single screen. Some of the work that I did at Microsoft was to visualize a data center's health. And that would be like an actual physical data center where we're looking at data, and if there's some errors, there's some things that are going off or not working. All of that was visual, which requires somebody to constantly look at a screen, which isn't practical. So I haven't yet seen very good practical example of somebody implementing it, but I do think sound for notification is fairly easy for us to maybe bring in. So if I was a stock trader, I essentially put all the stocks that I've focused on and give a threshold. And then whenever it goes below that threshold, it gives me a sound. Would be a very simple experiment to make, and would be a lot of fun. And because all of this is computational, it really makes it easy to take a real-time API and build some sort of a sound. I haven't seen examples. I will look for this. I am quite interested now as well on this.
So in trading companies, usually there is a squawk box as well, which keep announcing the price changes and like.
Yeah.
So that's not directly sonification as such for the data, but it's like the actual data there. But it's an augmenting your sensory input as well.
Yeah, I think even in general, the whole idea of dashboards that people tend to make could really be improved or enhanced by adding some sonification. And if it's as simple as you're in Myntra or Flipkart and you have order history coming in, celebrating a particular set of orders and milestones are generally done with just numbers. Make music out of it. So yeah, I'm going to look for more examples. Thank you for that, Naj.
Hi, thanks. So before just answering the question, I wanted to talk about that stock thing.
Yeah.
So we actually tried that. So what happens is when your stock is moving, there are certain frequencies involved in that. So what we thought in the graph, there are hidden frequencies. So we did some FFT response on that.
Oh, wow.
And we could find out what frequency it goes in when there is a certain movement in the stock. But then we could give it a sound now. As you said, as you had also suggested, and then find out what kind of frequencies are involved in certain movements of the stocks. But it's not very conclusive. You need large amounts of data to understand, because every time one stock moves, there is a different frequency comes out, and then there is some other graph, other frequency comes out. But both are falling, so you don't understand really. maybe deep diving is required. So thanks.
Yeah, I do feel just like visualization in a visual form, sonification would also require a bit of getting used to, because it's a very different, like we don't listen to sounds and think a bit about pitch or think about, is there a frequency change or not. So I'm assuming anybody who spends a bit of time doing it learns to notice some of these patterns, or you use ear cons or audio icons to actually just say this shot up more than 15%. So then there is not so much of how much is the exact angle, but it's really threshold based buckets, and that becomes easier as well.
Okay, so coming to my question, so now I understand that you have assigned certain frequencies to certain inputs of the sensor.
Yeah.
Is there a now way to add emotion to it in a way that Indian classical music does? Like there are certain ragas which you listen only into the morning because there has a lower frequency ranges.
Right.
And in the morning you don't like to really hear about high frequency. So have you thought of anything about adding an emotion part of it?
I haven't, but I'm very excited about the keynote that's happening at 3. And I think we'll probably hear a bit more about Indian sort of music aspect of it. My sense is that it isn't as straightforward as just like lower frequency versus higher frequency leading to an emotion. But I've, like when I learned a bit of music, just this idea of komal sa versus like sa, like this variation between a single note changing how a particular piece is interpreted would be interesting. I haven't seen a good example of it yet where somebody could just say, take this data, sonify it, but make it sound happier or make it sound morose, right? So I would be curious about just this music principles that would go behind this before we can actually encode it. I have the whole frequency as my playground. So what I really need to now understand is it just discrete jumps? Is there variation between the discrete jumps that changes that emotional aspect of it? If there's some people here who've done a bit more research on this, I'm happy to pair up.
Hi. So I just have one question. Like the letter been noted to each note, right?
Yes.
Like can we like also add a vocal bit to it, like a like by a voice vocal bit, so that while playing the name, it'll be like a vocal tune.
That would be fun. I think it would work a bit better if we do this for languages which have, which are written the way they are spoken. So for example, any Indic language like Hindi, right? It's easier to pronounce my name in Hindi because every letter and matra is essentially mapped to a sound. Whereas in English, cycle is my favorite sort of word to say, where the two C's have very different sounds, right? So if I'm going to say saisal or kaikal, it's going to be very annoying, right?
Like, is there some project working on like that, like where we can research upon that and then map it like that? Like,
so I think the way to then do this is not to use the name as we write it in English, but actually use the phonetic representation. And then that I think gets us closer to how it should sound. It would be more fun to not make it sound like how you anyway hear it, because then you're really doing a lot of steps to make it sound like, Rasagya directly.
No. I was just asking to integrate the thing that is already there and also the vocal portion of it.
But
so
I think it'll be interesting to mix a bit of the name. So if I do tell you a particular sound, like let's just do this, right? If I did play this without telling you this is Prashant, I don't think we can hear this again. Yeah, but if I did play that same sound without telling you that this was Prashant or Rasagya, you would not really get the name from it, right? So it's easier to say that this is my name, so you understand my name and then make a sound with it, which is fun. But I don't think it works as I will tell you my name by just making a sound. So maybe some of the bits that you mentioned where you add a bit of letter for phonetic might make it a bit more recognizable as well. So I like that idea. I haven't seen a project that does this very seamlessly. I wish there were projects like this.
Thank you.
It would make my life so much easier. I think we're running out of time.
We're running out of time.
Yes.
Time for the next talk. So maybe next speaker can take the questions offline.
Thank you.
And the topic is quality audio for low cost embedded products. And me being an audiophile, I'm really looking forward to this talk.
welcome to this talk. Oh, yeah. All right, thank you. And welcome to this talk. So we are going to talk about quality audio for low-cost applications. So I think a lot of the conference will be about high quality music, that kind of stuff. So here we are dealing with the low end, and there's a bit of electronics orientation in this. So I want to quickly ask, how many people design electronics, if at all, here? Okay, software side or hardware side? Hardware. Okay, great. All right. So we'll try to keep it kind of high level. So here we're going to talk about good quality audio at a low cost, wherever it's possible. Quickly to introduce ourselves. So Sri Kumar, I am a software guy. So typically software and hardware are both involved. So I've been doing a lot of electronics, and I've been leading software teams which develop hardware. So one of my projects which you might find online, which is probably one that I'm most known for, is something known as Kite Phone. It was like a DIY smartphone that you could actually 3D print. I've been also working with a lot of Indian silicon. So there's some silicon which is coming out from companies in India, microcontrollers, that kind of stuff. So that is the board, which is the only open source board you'll find based on Tejas 32, which is CLAX microcontroller. I do a lot of cycling, so that's my primary hobby. I've been on and off trying to learn music and instruments. Never succeeded because I never spent that much time on it. So that's something that I'm hoping to improve by coming to this conference. So generally that's a bit about me.
Hello, I'm Atharva. I work at Samsung currently. I'm more interested in a little bit of electronics as well as I know, like finance also. I dabble with behavioral economics and then finance is about it. Currently, I mean, I am engineer at work, but I'm actually supposed to be a sports player always. So I do a little bit of swimming and then coaching of the swimming as well. So we are going to talk about audio hardware and not just like software part of it. So I will let Sri Kumar continue.
So very briefly, so this talk is about mostly doing DACs, and then ADC is analog to digital converter. So it's not audio developer conference, right? And again, like I said, there's nothing hi-fi about what we are going to say. We are not going to talk about the fantastic quality of audio and all that. So we will stay away from a very detailed characterization and graphs and all that, and that's about it. So when we are saying low cost electronics, what product are we talking about? So let's first set the context about the product. So basically, we were creating an end user terminal. So like think of it like you have a laptop. Similarly, you have an end user terminal. It's a graphical terminal. So you have video coming from HDMI, keyboard and mouse you get through USB. Then you have audio, which is of course the what we are going to talk about in this talk. So we settled for 16 bits 48 kilohertz audio and stereo audio, and each terminal, so it has like 2 audio headphone support. So basically, like it's for applications like education, where 2 students might be sitting in front of a single computer and single terminal and sharing the terminal. Education and kiosks, both are big applications for these kind of devices. I will show the hardware later on in person because it's very hard to show from here. It's like a small box. And we support both playback and recording. So that means that both side bidirectional audio use cases are supported by the devices. And this work was actually done some time back in where we used to work. So we both used to work in a separate company called InnoMinds. So this product was actually being developed there. And there's a bit of retrospective in this, whatever we are actually going to tell you today. So breaking down, what does low cost mean, right? So when you're doing low cost, and if you're familiar a little bit with electronics, you will try to figure out what are all the chips and what are all the components, which are the boards, how much does it cost to assemble. So that's all elements of low cost. But there's another element of low cost, which is like the audio. So we are doing video through HDMI. So that's like very high quality video. So typically what happens is when you are trying to build a device from first principles, like what we were trying to do, you also need to have very good audio, because people are already addicted to very good quality audio, either in terms of phones or in terms of TVs. So they are reasonably well designed audio compared to embedded systems which might not have had the same kind of audio quality. So what happens is that all these typical platforms that we use are based on reference designs which are optimized for very specific purposes. So when we are trying to create an entirely new kind of a device, we end up with a challenge how to get a good quality audio out of it. So just a quick background of what kind of team. So of course, a lot depends on what kind of a team you have when you start off engineering a device. So we were trying to create hardware for a novel low-cost architecture. So that was a thing. But we were like a small team. We were like just 3 people: Atharva, me, and another guy, Muhafiz. Believe it or not, we didn't have any experience with what we call discrete audio implementation. Why is that? Because, see, I've been working in embedded systems for like 14 years now. I designed the first 3G tablet design for India. But more or less, we're doing a lot of job of system integration. We're taking standard designs, we're tweaking it a little, taking it quickly to market. So that means we have more or less no time to master the, should I say, basics, right? So when a new area comes along and you have to like really engineer something hard, you know, you can be a bit lost. So that's part of our story. So quickly getting in and giving you guys a feel of how audio works at these kind of low levels. So there's a protocol called I2S. It's like a signaling protocol over 4 wires. So how many, just for my understanding, how many people understand I2S here? All right, a few people, right? So basically, the way this works is, so there's a processor, right? And when the processor wants to generate sound, it has to, so generally the logic of taking the audio samples and converting it to actual audio is offloaded to a different chip, which is typically called a codec, right? And data is transferred, in this case, over 4 wires. So one is, of course, the frequency, which is also called the LR clock, if you actually get down to the wire basics. There's a bit clock, which says these are the bits which are going. And then there are 2 data wires. So one of the data goes, which is like for the digital to analog conversion. One is for the analog to digital conversion, which comes back, right? And in all these cases, it's the raw audio samples. So when you open the raw audio samples in any of your favorite software, this is exactly that raw audio samples which are going on the wire. So and remember, in all these cases, since everything is offloaded to that other chip, the choice of the chip is very critical. I mean, that's what determines more or less the cost and the quality trade-off. So there can be expensive codec chips, there can be low-cost codec chips, they can work in different ways. So that's what we ended up exploring actually. What kind of thing? So we also tried something where there was no codec. I mean, there was a partial codec. So more or less, but this is the architecture. You have a processor on one side, you have something to which you are going to outsource a lot of your audio work, and then you're only going to send out samples and receive samples, whether it's relevant. Now, quickly to come to what we started off first when we are trying to create this device. Every time you need to have an MVP, because when we are creating a new kind of architecture. Now, describing that architecture is out of scope here for the device. So first thing you always want to do is you want to prove the concept. This thing is working fine. So you want something which is like, you know, will work, right? So what we did is we actually created a base board for this. It was based on the Raspberry Pi RP2040 microcontroller, which is what you see here in the diagram. We had a simple low-cost board. It was still not an expensive board at that time, and it was connected to a codec, which is what Atharva will describe now.
So since I'm a hardware guy, I'll just give it a little bit about hardware architecture of this. So all of your tablets, mobiles have this chip. This is called a codec, which takes care of your speaker circuit as well as your mic circuit. So you don't have to have a different chips for the speaker and the mic. So this codec was especially from the Cirrus Logic. So this is the company, this codec is in Apple phones. So we try to use this and evaluate this codec. Part of this codec has headphone drivers and the mic amplifiers. All the filtering circuit is already taken care of the inside chip. On top of that, then there is a nit bits of the circuits, which are like mic bias circuits and which are very important pre-amplifier circuit for mic, also is taken care of by this. So this is like a very high integrated solution, but comes at a cost. So this was around $1.8 chip, and then it's pretty hard to get also in the market. So this is also one of the problems in the manufacturing. When you actually have a design, but you have to manufacture it, you have to take care of how availability is also. So this was also one of the harder chips to get. So this was like, a little bit of the architecture of this. So you want to continue?
Yeah. So what happens in this case is we put this chip on the board, and the way we communicated with it is that we have an I2C bus, or I2S bus, which you can see on the diagram, and there is also I2C bus. So I2C bus is generally used to configure registers which are related to how the audio is going to come, audio parameters, tuning parameters, all those things will go over I2C bus. And there is I2S bus on which the audio will go. And then you will also see a 12 megahertz signal there, which is basically the main clock for the codec. So the codec basically uses that clock, and from that it generates all the clocks which are internal, which are required to generate the audio. So we did this, and we implemented our first version with this, and then of course we have to do an evaluation, and basically what we found is that we got fantastic quality out of it. I mean, fantastic given the circumstances and the kind of product that we were trying to get. It was very good quality as far as we could say, well, the cons were that of course it was much higher cost. Like Atharva was saying, it's about $1.8, and you might think $1.8 is not a lot. The fact is the microcontroller that we're using, the heart of our board, is about 60-70 cents. But so $1.8 is a big cost in the overall scheme of things. And then what happened is something that Atharva still has to explain, is that we ended up with the end of life wars. So what does that mean? So what that means is when we design a product, we are not designing it for today. We are designing it for like next year or the year after next. So generally what happens is that vendors, depending on their product roadmaps, will say that product will go end of life next year. So when that happens and you have designed it now, they will tell you at the last moment that it will go end of life next year, right? So that means that whatever you have engineered, you can't really take it to the field, because if you do that, you'll have to redo a lot of engineering around it. So then we asked them, so what are the alternatives? So then they said, take this more expensive chip. Okay, here, take this, $3.50, right? And why is that? Because if you really notice, high-end vendors of components don't want to get stuck in the low end of the value chain, because profits are, and everybody is snapping at their heels. So everybody wants to, many people like companies like Cirrus Logic, they will no longer offer low-end codecs. They will all want to go up the value chain, which is what happened in this case. So it was pretty clear to us that we couldn't go with this as a solution. So we had to really find a different thing. And I was in trouble because more or less this hardware product and everything was like my baby. So I was the one who had pitched for the project. I was the one who got funding for it and so on. And it was on me now to find an alternative. So I went back to my maker roots, and I was trying to figure out what we can do which is lower cost, right? What can we find from the maker projects and so on. So we found a couple of chips in this, which Atharva will explain.
Just two people think is clearly.
It's okay, go on.
Okay. So what Cirrus Logic chip made at $1.8 is mainly the ADC logic inside, how the circuit works in the ADC. So there are different kinds of ADC in the world. It was the most recent technology, which was the sigma delta technology. So this was the highly effective way to convert your analog to digital. Now if you want to sell this system, you still cannot actually sell with a $1.8 chip, what Shree told me. So that's why I had to now reduce the cost. So Shree suggested, can we go from monolithic solution to a discrete solution? Now we are to find out for each function, speaker function, mic function, filtering function, we have to find a different chips, different set of circuits and put it together to see if it works. So now for the speaker circuit, we could find that there is a PT8211. This is a Princeton IC again. These are all Chinese companies. So this mainly chip uses the R2R ladder network for the ADC. This is a, let's say, old school method of converting analog to digital, I would say, compared to sigma delta. But it works, but it's a low cost as well. But problem with that circuit is you need still driver circuit outside, discrete filters outside. On top of that, then now you have taken care of speaker, you have to take care of mic. So for mic, you need a pre-amplification circuit, because when I'm speaking to this, I am generating 100 millivolts. But 100 millivolts I cannot read. So I need a good amount of voltage swing to read and make a sense of that data. So that's why we need a pre-amplifier chip. Then you need a lot of filter circuits outside to tell your microcontroller this is sound, not noise. So these were all the components we added in the hardware architecture to make, to evaluate again the design. So you want to?
Yeah, so on the software side, if you know the RP2040 chip, you will realize that it has a few ADCs. It has 4 ADC channels. But the resolution is kind of low. So like 12 bits is the official resolution, but in reality, if you look at the results they have produced, I think it's somewhere, the resolution is somewhere between 9 and 10 bits. So when we were trying to do the audio and trying to get stuff in, right, it really hit us. So overall, if you really look at it, when we evaluated it, we felt that it was a lower BOM cost. Cost-wise, we had achieved a saving. But in reality, we might not have had much savings, because what happens is you put these kind of components, and many of the components, you have to also solder them. And soldering also costs money. And when you are trying to build something at a low volume, it's a problem. So we didn't actually make any gains from the perspective of costs. And we got unacceptable quality in our own this thing, because the volume was less. And the fidelity of the recording was much worse, because like I was saying, we got somewhere between 9 to 10 bits of recording for the audio. So overall, we decided that this is not going to be worth it. But again, I was back in trouble, as you can imagine, because now I had spent some time, I had not gotten any results. So then we were like really struggling and burning a little bit of what we call midnight oil, because people are asking, where's the solution, right? So where's the solution? So I was like frantically searching around online. I luckily found something known as ES8388 codec. And to my not so surprise, but to my thrill, I found that it's actually a clone of a different codec from Cirrus Logic. And I immediately suggested it to Atharva, and Atharva will say a little bit about the codec itself.
Okay, so from the hardware point of view, we talked about earlier monolithic solution, Cirrus Logic. Then we talked about discrete solution. Let's say it's now we understood it's not worth it. So we need a quality at low cost, like everything else. So at low cost, I need a best quality. So then I could say as like we found a Chinese solution through hardware. So this is one of the Chinese vendors chip. This is basically a clone of all the US-based made chips. There are a couple of companies they have clones of. This is a clone of that Cirrus Logic codec we saw. It has all the ingredients which we know. We have a headphone driver, which is the important circuit. It has a mic preamplifiers, which is also an important circuit. On top of that, it comes at 1/3 of the cost. What are the problems with it? You really don't know what goes on in Chinese chips. Okay, they say it's the data sheet they have or the information they have from the clone chip, but it doesn't map really one-to-one. So we struggled a lot about the mapping of the register, how we set, how we actually bring up the chip and then understand and get the audio out of it. So yeah, these were the advantages and then disadvantages of it from the hardware point of view.
Yeah. So while we achieved acceptable quality with this particular codec, because it implemented the much better analog to digital conversion and the reverse, we did make some trade-offs. So of course, one of the important ones is that we sacrificed the jack detect. So this chip did not have a jack detect circuit. So what that means is when you plug in a jack, we don't know. So we always keep the audio running, which is not a problem, because if there's some sound and nobody is there to listen, who's going to lose? And it's a low-cost product, right? And we also made some trade-offs in terms of frequency response. We figured out that somewhere between 40 hertz to 100 hertz, and below that, we don't really want to spend money on it, because you have to spend money on expensive capacitors. So we cheaped out with the non-electrolytic capacitors, right? And we tested the frequency response with Audacity. So we had like the box giving audio to a laptop, then we visualizing it with Audacity, and then you are checking the frequency response. So that's what we did. So the biggest challenge we face with this is that Chinese chips documentation is difficult, and they're harder also sometimes to source. That means you can't buy them easily, and support woes will be there. So like you are speaking in English, there's a Chinese thing coming there, data sheets are bad. So all that, but all said and done, I think it was a well worth solution that we achieved with our respin number 2. So originally we had one first MVP, then we had a respin which did not work, and then we had a respin which worked fantastically. right? But sometimes you might wonder, how is it that the Chinese chips are much cheaper, right? Because they sacrifice some functionality. Obviously, they can't do by magic. Of course, there's a cost angle to it. There's a cost arbitrage difference. But if you really look inside the chip, you'll find that there's no PLL. So why is the PLL important, right? So typically, when we do audio, we do like 44.1 kilohertz is a very common frequency, right? So since there's no PLL inside this, it cannot take a 12 megahertz signal and convert it to 44.1. If you actually look at the sheet there, you will see 44.118 kilohertz. So there is an error of 18 hertz. But if you look at 48 kilohertz, that's an even divisor, which can be achieved from 12 megahertz. So by dropping that, they made their value proposition very clear. This is a chip, take it at $0.50, right, in low quantity, and this is what you're going to get. And it worked for us. So some of these trade-offs you have to be very careful when you're actually taking these kind of chips. So obviously the devil is in the details. When you're taking a solution like this, you have to fix your frequency rate, you have to fix a lot of things. You can't be very, very generic solution, and you can't be cheap. So that's always the case. And in this case, 12 megahertz can easily be can give us 48 kilohertz by direct division by 250, like what it is. And unlike regular I2S audio, if you deal with I2S audio, you'll find that you are doing either 16 bits or 24 bits or like 32 bits, like that kind of bit width. In this case, if you look at the I2S signal, you'll find that 25 bits per channel. So what happens really is 16 bits are data, everything else is ignored. So that's how you get 25 as a divisor, and only 16 is data, remaining is ignored. So that's actually the overall solution that we came up with the final Chinese chip, so to speak. So when we talk about Indian silicon and all that, we always fixate on things like, oh, we have to make the processor. We have to make a lot of other supporting circuits also. Even audio components are very important to be like, I don't want to call this Atmanirbhar, but you get the picture. So we always think about processors are the most important thing. No, they are not. So there are a whole lot of other things around this. So to conclude, we actually went around tuning for cost, and we achieved a very good cost and a good quality with some trade-offs. And in hindsight, now that 1 year has passed by since we implemented the solution, 1.5 years, when we picked up this codec, it was not, data for this was not available. Now if you go and you will find that it's in ESP32 reference designs. So ESP32 is a microcontroller which is very commonly used by a lot of people in IoT. And that is proof that we probably made the right choice, because nothing ends up in a reference design unless it is that good, unless that's optimized. So that's one thing. The other one is human strategies that work, as I would say. So there's this constant fight between Atharva and me when we were designing this. So I was the product owner and the software guy. He was the hardware guy, and hardware guys typically have this question: what is the target price? Okay, he will constantly see this. Whenever people talk about hardware, the first question that always comes up: what is the cost? And the designer will always ask this question, because the responsibility is on the designer to meet the cost. But I was like a very demanding customer for him. I would never set a cost. I would say, I won't say what it is. You find the next lower cost. How are you sure that it is the lowest cost? Have you considered the alternative? So we had like a lot of fun time and stressful times, right, in this thing, and I think we achieved a reasonable result. So in summary, if you are doing custom electronics, you can easily buy a P2E8211 to generate a wide range of useful audio. I mean, if let's say you're doing some hobby microcontroller projects, you can easily buy a P2E8211. I think it costs about 20 rupees or something like that. You'll get like decent, I mean, it's not for audiophile and all that kind of thing, but if you want something to make some sounds, it's not a bad solution. And that's something, it comes with 8 pins. It's easy to even hand solder. So that kind of stuff you can use. But for anything which is more complicated, you will have to probably spin a board and use the other chips. So that's about it from our side. Thank you. Any questions if you have time?
Yeah, we definitely have time for questions. So yeah.
Hi, thank you for your presentation. There was one thing that I thought you didn't touch upon, which was software side of it. What is the cost that goes into driver development for something like this?
I see. So for something like this, since we're using the RP 2040, it doesn't have native support for I2S. So you have to develop a PIO program for. I think this use case is not very common. A lot of hobbyists, whatever programs you'll find in the wild, will take care of the ADC part, but not the DAC part, but not the ADC part. So that's some tuning that we had to do. So for the Chinese chip, we had a lot of trouble because of the undocumented registers. So there's a lot of back and forth which happens. But if you actually leave it out, and if you are a skilled developer, it's probably about a week's worth of time. If you exclude the tuning.
The skilled developer comes at a cost.
Yes, the skilled developer comes at a cost. If you have a newbie developer, for example, who doesn't understand I2S, who doesn't understand a lot of the background around it, I can't really estimate. Right? So if you understand the protocol, if you understand signaling, if you have done it sometimes, I think if, let's say, to give you an idea, most people would have programmed something like PCM audio. Let's say you've done Windows programming with PCM audio. You already know that you need to have at least 2 buffers. You need to have some kind of background processing happening, which is DMA. DMA trips a lot of beginners when you are actually trying to develop an embedded system. So if you account for all that, beginners will take more time. But if you have some experienced people, you should expect them to have a working solution in a week. If you have documentation, which is good.
Right. So thank you. And the respin 2 that you said was your final solution. How much would it cost for me to buy?
Respin 2?
Yeah.
Which part? So this the
product.
Oh yeah, so it's a B2B product, so you obviously can't buy it, but I can show it to you.
Okay.
The BOM cost for that device is about $6.50 or something like that in about 1,000 quantity. And we were not even negotiating prices and all that and buying from specific suppliers. We were just doing a generic costing. It was about $6.50 from what I remember. $6 or $6.50, something like that.
Cheap enough, but.
Yeah, it could even go lower, and I'm saying specifically because when you start shipping something in volume, it becomes a very different ball game. Hardware is a very different ball game at that level. So
yeah, thank you.
Right, we have one more question there.
But overall, on this audio tuning and everything, we would have spent, not just on the audio, the entire device part, we would have spent more than a year and a half going through various iterations because it was not just audio. So,
hey, I think the 2 words that stood out during the presentation that you made was one, cost, and the other one is quality. Cost in itself is measurable. How do you really measure quality? How do you benchmark it? Because it's a product, right? I look at, how can I read the quality and then make an informed choice?
Great question. So here's the thing. So we were targeting this for education, and the problem is, what exactly is education? Education is basically all types of content. And it's not like education in the past, right? Now education is like all kind of videos. So really, you are basically saying you want a decent quality, and the test for that finally we devised is, beyond all our graphs and everything. We just took some educational YouTube content from YouTube, from Diksha. So Diksha is the online education thing from the government of India. We took a lot of educational lectures. We even took National Geographic videos, and we were listening to who was that guy? Richard. No,
David.
Yeah, we were listening to him like every day, right? So we basically had a bank of videos, and of course the junior most guy got the thing to now listen to this implementation, now tune this, now do this. So there was some amount of that. So there's a subjective angle, there's an objective angle. So whatever we did in Audacity, it was fine, but we didn't want to really say that is the sign-off part. We wanted to make sure that all sorts of audio at an acceptable level will work.
All right, we have time for one last question.
Hi, thanks for the nice presentation. I see you use a lot of cheap materials for a low cost. It's understandable. But what about the reliability? Like, will it work for if I purchase from you? Will you give any warranty or?
Oh yeah. So believe it or not, these products were deployed in a factory also. They're probably still running. And we found that very interesting because we engineered for education, but education is a very hard market to sell to. We found the value proposition resonated very well with factories because they were trying to digitize their paper-based workflows. And we have not had a problem from reported from a factory, and factory keeps running it all the time. Unlike education, for example, where it will only work in class hours. So And these are electronics. Electronics typically have a very high MTBF, mean time between failure. So even though we want to think that, I mean, if it's pure electronics without, capacitors can fail over many years. Okay, but we didn't even use electronic capacitors. So basically we took out a lot of stuff from the equation. So our hardware probably would work without problems for, I don't know, 10 years. Though we haven't done any analysis. We don't have too many components. So when you do the MTBF analysis for an entire board, the results depend on also on how many components you have. The more components you have, the more liable you are to failure. So I think it's a pretty reliable design because mostly like ICs and passives. So is that right?
All right, so round of applause for the speakers. This is the time we have.
Thank you. Thank you.
Okay, so now we'll take a quick break. This will be like around half an hour. So we'll all be back at 11:30. So please be here on time. You will be given welcome drinks, which will be at the near the registration desk area. So you can all head there, do some networking. For all the Music Hack Day winners, Pradeep will reach out to you if your presentation is ready. Just let him know what the status is. It's completely okay if you can submit the whole thing by lunch, so don't worry about it. And yeah, have a great time networking, and we'll see you all again at 11:30. All right, welcome back, everyone. I hope the live streaming folks can also hear us. Okay, all right. Welcome back, everyone. Now we are ready with the next set of 3 talks. We'll start with a really interesting one by Daniel Fernandes, who will be talking about MIDI effects, a node-based MIDI effects processor. A round of applause for Daniel.
Thank you, everyone. It's wonderful to see you all here. My name is Daniel, and this talk is about a project that I had been working on for the past 3 years. It's called MIDI effects, and by the end of this talk, I hope you can see how it can be useful to you to implement your own custom MIDI setups, no matter how niche or how crazy your ideas are. I hope that you can try to use this tool to solve your own problems. A bit about me. I'm a computer engineering student in my final year, and I picked up music production about 6 years ago. I was exposed to all of these plugins, EQs, reverb, the Fourier transform, and all of this stuff. It felt like magic to me. So I was like, I want to learn how to make these things on my own. I want to understand the magic behind all these tools that I was using. So that's what got me into audio development. Last year, I was accepted into the Google Summer of Code program, where I worked on the free and open source DJ software called Mix, and I improved its harmonic mixing workflow. Back to our project. To understand what MIDI effects is, we need to at least go over the base for what MIDI is. So on the left, you see a very familiar device. It's a it's a MIDI keyboard. So over here you have a MIDI keyboard. When you press a key on this keyboard, it's not going to generate sound on its own. It's instead going to send a message to the computer that, hey, this note was pressed and here's how loud it was pressed. Then when you release a note, it's going to send another message back to that computer. This device can also have knobs and sliders, and it needs to be able to send that information to the computer again. Then on the computer, you can use whatever sounds you want. You're not restricted to whatever comes with the keyboard. On the right, you have a more interesting device called an electronic wind instrument. The cool thing about it is when you play it, it's going to sense how your breath is flowing, and it's going to send that information to the computer. So you can use it to control flutes, an oboe, a piccolo, any other device. It can even change the fingering mode. So with one device, you can control many different wind instruments, which is quite powerful. And I wanted to show you that you don't necessarily need a computer. You can connect a MIDI keyboard directly to a lot of analog synthesizers. So MIDI has to be a protocol that is simple enough that you can use it even without any digital computers. So MIDI, it stands for Musical Instrument Digital Interface, and it is the standard language that's used by all kinds of manufacturers, whether it's Yamaha, Roland, anything. They use MIDI for sending information between other devices. And you might also know that you can record MIDI data into MIDI files, and then you can play it back. Now, MIDI data is sent in the form of messages. So in the next slide, I'm going to show you what a message looks like. Most messages have 3 bytes, so 3 numbers. They're called status, data 1, and data 2. Status tells us what kind of message this is. Is it a note on event? Is it a note off event? Is it a knob that's been turned? Is it something else? Then the meaning of data 1 and data 2 changes based on what status is. If status is a note on event, data 1 will be which note it is. Data 2 will be how loud that note is. If status is a control change, which means a knob or a slider or something like that, then data 1 will be which control is it. Data 2 will be what's the current position of that control. MIDI also has this feature called channels, which means through a single MIDI line, you can send information for up to 16 channels. and that information is also encoded into the status byte. Now we come to MIDI effects. So it's a program that it's used for manipulating MIDI information, and it does that by using a node-based architecture. You can have a single node that does something very simple, like it might delay the MIDI information, or it might transpose the note that's being played, and you can combine these nodes together to create something very complex. In addition, MIDI-FX runs in the browser. This means that you can leverage browser APIs you can interact with MIDI and the browser APIs. So you could, for example, send MIDI through the internet. We have a few demos to show that, and yeah, let's just get straight into the demos now. So the first demo, over here I have an external input node. That's my MIDI keyboard, and the external output node is my DAW. So I just connect them, and then I can play. Nothing surprising here. We are just sending MIDI through MIDI-FX. But now I've added a delay node. What's going to happen is as I play on the keyboard, the raw MIDI signal is going to go to the DAW, but another copy of the MIDI signal is going to be delayed and sent back to the DAW. Now we're going to add another node called the transpose. You might be familiar with this function. It's just going to change the delayed node. So in this case, I've transposed the delayed signal by 2 semitones. And you can even change these values. So I like to use 7 semitones, a fifth. Then you can even scale the velocity of these nodes so that the delayed signal is a little bit quieter. Cool. So that's like how MIDI-FX works at its core. You have all these different nodes, and then you can connect them together. Now I want to show you another demo, which is the hand tracker. It looks something. I've set it up in this way, where I have the hand tracker node in the middle, and on the 4 sides I've kept other nodes. These are called control change visualizers. They can see what is the value of a knob or any control that's being changed. So what this node is going to do is it's going to look at my hand through the camera, and then based on what my hand is doing, it's going to change some kind of control value. For example, if I open and close my hand, I've set it to change the cutoff of a synth. If I move my hand front and back, that's set up to change the timbre from a saw wave to a square wave. Then I also use my other hand to change the attack and the ADSR curve. So let's have a listen to that. So the way the hand tracker is able to tell what my hand is doing is I use a library called MediaPipe, and it looks at your camera feed and it will give me points for wherever my joints are located. Then once I have that information, I can use some vector math to figure out what my hand is doing. For example, over here, to detect whether my hand is open or closed, I'm using a dot product. So if you see on the left, I'm making 2 vectors for my knuckles So I'm taking these 2 points and making a vector out of it. I'm taking these 2 points, making another vector out of it. The dot product is an operation that tells us how aligned 2 vectors are. So if they're both pointing in the same direction, the dot product is going to be very high, and I'm going to know that my hand is probably open. If I bend my finger, as you see on the right, my dot product is going to be much lower. So that's how I know that my finger is probably closed. So do that over every joint of your hand, and you figure out whether your hand is open or closed. So that's kind of how you can use some vector math to figure out what the hand is doing. The next demo is with an Arduino. I was quite happy to see that a lot of you are into electronics, and MIDI-FX can be used with any serial device, including an Arduino. So over here, here's what an Arduino looks like. It's an Arduino Uno, and on both of its sides you have a lot of pins to which you can connect different things. And around this Arduino I've put just a very small subset of things that you could connect it with. So on the top left we have an ultrasonic distance sensor. Below that we have an infrared sensor, which is used a lot in line following robots. Below that is a pressure sensor, a force sensor, and I believe this is what's used in a lot of MIDI controllers, which can detect how hard you're pressing a button or a keypad. Below that is a camera. You can connect a camera to this thing. On the right we have some output devices. We have an LCD display. You can connect a speaker with it. You might want to use some amplification, but it works. You can connect LEDs. The golden thing, that's a piezoelectric buzzer. It's the thing that makes the beeping sound in our watches. And every speaker is a microphone, so this thing can also be used as a contact mic. On the bottom right corner, the blue thing, that's a servo motor. It's a motor that moves 180 degrees, and you can control exactly what angle it's moving at. And that's useful for robotic arms and things like that. So for our demo, I've used the ultrasonic sensor, the one at the top left. This device, here's how I set it up. So this device, it has a transmitter and a receiver, but it works in the ultrasound range. What it does is it sends an ultrasound signal, and as soon as there's some object, that signal is going to bounce back, and it's going to be received by the ultrasonic receiver. We can measure the time delay between the transmission and when we receive the signal back, and we can figure out how far the object is. So let's see how that works out. So I did flip the control values inside the door so that as my hand is closer, the sound gets louder, because I felt that was more intuitive. But yeah, over here it does show that the value is lower when my hand is closed. Now, the next demo, okay, yeah. As for how you would send information from the Arduino to MIDI-FX, it's as if the Arduino was a MIDI device itself. You can just serial.write the MIDI bytes. You can, for example, for sending a control change message, you just write the status byte, then the data 1 byte and the data 2 byte, and MIDI-FX picks it up. Now, for the next demo, MIDI over internet. Now, when you do something like this, you really are concerned about latency. We want the latency to be as low as possible. So the way we achieve this with MIDI-FX is we use a protocol called WebRTC, or Web Real-Time Communication. It's used mainly for video calls and stuff. It's used by Discord, for example. And what's special about it is that once the two devices have established a connection, the data transfers between them directly. You don't need a third intermediary server. The way it works is, first we have a broker server. In this case, it's called peer server. What's happening is client A is going to tell peer server that, hey, I'm client A, this is my IP address, these are the ports I'm willing to connect with someone else to. Then client B does the same thing. Then client A says, hey, I want to connect to client B, can you give me its IP address and port? Then peer server, since client B has said that it's willing to connect with someone, peer server is going to give that information to client A, and then client A can establish a direct connection with client B, and the peer server is not required anymore. So the reason I call the intermediary server peer server is because I'm using a library that simplifies the WebRTC protocol called PeerJS, and it just takes away all of the under the hood mechanic stuff, so you just focus on making a good product. So let's see a demo for that. So over here I have my phone on the right and my laptop on the left, and you can see I've given each of them an ID. So my laptop has Dan laptop, my phone has Dan phone, and then I'm gonna connect to peer server and say that, hey, I wanna be ready for establishing a connection. And after that, I'm gonna put the ID of my phone on from my laptop. So I'm establishing a connection from my laptop to my phone. Now I'm able to send data between the two. So initially I'm sending data from my phone, from my phone to my laptop, but I can even send information the other way around. So in this case, I'm going to be playing from my MIDI keyboard, which goes to the laptop, which goes through the internet to my phone. And I have a little node at the bottom here called the chord explorer. It tells me what chord I'm playing. So yeah, that's a C major. The way I actually use it in practice is I have my keyboard over here, I have my laptop over there. I can't see my laptop when I'm playing the keyboard, so I'm going to take my phone, keep it in front of me, and then when I play the keyboard I can see what I'm actually playing, which chord I'm playing, things like that. So the power of MIDI effects is really in combining different things together. So yeah, I'll just finish the demo. Yeah. So one thing I want to show is maybe the nodes that are available aren't enough. Maybe you want to implement something of your own. So I just wanted to give you a peek under the hood of what a node looks like, because MIDIFX is open source. So if you want to build something, if you want to add something on your own, you can do that. So this is the transpose node. It's a very simple example. When you give any MIDI signal to it, it's gonna check whether this is a node on-off message. If it is, then it's gonna transpose it up or down. So mainly there are three things that are going on. You have an export called input, and yeah, I just want to open MIDIFX itself so you can kind of see what things look like. So here's the actual app. So if you look at MIDIFX, you have the inputs over here, you have outputs over here. Some nodes, they can have multiple outputs as well. For example, this is the node splitter, which will split node on and node off messages into separate streams. So that's the reason why inputs is an object. You can have an input called MIDI, you can have another input for something else. Now, every input is actually just a function that takes in 3 bytes, the status data 1, data 2 bytes from MIDI. Then we just check, is this a node on-off message using the status byte? If it is, we figure out what's the transpose node by just taking the node that was supplied to us and by figuring out what is the transpose value, which is stored as a state variable. Then we emit the transpose node to whatever outputs are connected. So in this case, the output is also called MIDI. It's this thing over here. And you can see that's defined in the outputs. If it's not a node on-off message, then we simply emit the MIDI message as it is. As for outputs, you just define it, and then you use new set because that's something that's relevant under the hood. Every output is actually a set of input functions. So it's the way it works is like when I connect this thing to this thing, this input function goes into the set of this output node. So that's why it's used, but you usually don't have to mess with that. State, that's a variable that's an export that stores the state, whatever parameters you want. And what's cool is this information gets stored in preset files and also in the local state of MIDIFX, because you don't always want to recreate the setup that you just made. Now, what's next for MIDIFX? Right now, I'm working on making UX improvements. I'm working on making it easier to use, because when I started it out, it was just an idea like, what if we could, would this thing even work? But now that it did work, I want more people to be able to use it. So I want to make it user friendly, and if you have any feedback on how I could do that, that's very welcome. I'm also working on upgrading to Svelte 5. MIDIFX is based on a web framework called Svelte. It's one of the most loved frameworks in the JavaScript land. If you haven't heard of it, it's basically HTML, CSS, JavaScript, the core web languages, with a little bit of extra syntax added on top of it, so that these three things, they work together very nicely. And lastly, I do want to build a community around MIDIFX, because of its modular nature. I feel that the more minds we have working on it, the more we can explore what we could really build. So with that, I want to say it's been a fun time talking to all of you, and yeah, thank you for listening to my talk.
Yeah, I think we have some time to take some questions. So, any thoughts? Yeah.
Hey Daniel, nice presentation.
Thank
very
you.
Impressive work.
Thank you.
So the MIDI over internet, how real time it is? Did you try to measure the latency over there?
So it depends on several things. For example, if I'm sending the data within my room, then the latency is going to be quite low, because it's going to go from my laptop to my router, possibly to my ISP, but I don't think it's going that far, because it feels so instantaneous that I doubt that it's going too far from my house. But it's probably not going too far and then it's coming back to my house. But if I'm transmitting signals from India to maybe my friend in America, then obviously the latency is going to be a lot higher, right? So it's related to the latency of WebRTC itself. Yeah, but as for the options we had, I feel like this was the most the lowest latency option that we could use in the web browser.
Amazing. Any other questions? All right. Again, round of applause for Daniel for such an amazing talk.
Thank you.
Hi everyone, we are ready with our next talk with Anmol and Satyajeet. They are also from my same university as MTG, which is in Barcelona. And the topic today they are presenting is Groove Transfer VST for Latin American Rhythms. So yeah, welcome them.
Hello everyone, I'm Anmol and Satyajeet, and we're both master students right now at the Music Technology Group in UP of Barcelona. So this work was inspired by basically I'm a DJ and Satya is a music producer, and this work was inspired by a shared love for making beats, and we were specifically inspired by this swing or groove in the Latin American rhythms, and that's what we're going to talk about today. In fact, the preliminary nature of this work was also presented at Izmir this year, and we have some more experiments now, and yep, let's maybe proceed with the talk. So yeah, just stating like the inspiration again, we wanted to bridge the gap between the algorithmic rhythm creation, which is, let's say, a lot more quantized and grid-like and sounds very machine-like, and maybe bridge this gap between the expressive qualities of a live performance, where the mistakes, let's say, are not so much mistakes, but a part of the performance. And how we do it practically is like we build an algorithm, which we're going to talk about in the talk. And then we are very, being musicians ourselves, we really wanted to make our research usable. So we wrapped our model, the neural network model, in a VST plugin so that people can use it. And we're going to share the GitHub repository where it's there and you can download it and basically start using it. So I want to talk maybe a little bit about the overview of the presentation. So we have first of all, we're going to talk about if you see on the top left, the candombe drumming style, which is the one specific style that we want to show to you. And like because our technique works for style specific rhythms, because every style has a unique groove. And the method is general, but we can extend it to any methods. And that's what we're going to talk about. Then on the right side, you see more technical or more engineering like stuff on how we actually mathematically represent some of these ideas. And finally, in the center is the VST plugin that we make and we're going to present. So for maybe, let's say, the non-musician audience in the audience, we want to talk a little bit about what micro timing and grooves are, and I'll have Satya present that part.
So yeah, this work is based on this core concept of micro timing, right? A lot of you may or may not know the exact technical understanding of this, but I promise you that you've heard it, and you know what groove is, and you know what feel is, in rhythmic expression. So technically though, micro timing is subtle deviations from a strict metronome-like or grid-like timing. So if you look at any of the images on the left, you'll see that there's a grid, right? And it's an equal space grid. But humans don't perform like robots. So these subtle deviations are called micro timing, where the notes or the beats, they come slightly ahead or slightly behind the expected positions on the grid. And this is what we understand as feel or groove. And we know this, we have heard it in all kinds of music, like in Western, you have jazz and even hip hop, like lo-fi hip hop, we love it. So, and especially in India, we have so many folk traditions, street music, we are very familiar with it. And so that is micro timing. But now there's an extension of this term, which is a generalized term called micro rhythm. And it basically says that groove is also represented not just by timing, but also by other aspects like dynamics, and then timbre can be one of them, like duration or central frequency. Now, I'll just give you a small audio demo of how this concept of micro timing affects groove, okay? So this is something which is quantized. Quantized means everything is locked to the grid. So this loop, every every drum shot sound is at the same volume and locked to the grid, right? Very robotic. Now we add one layer of humanization to this. So the drum hits are coming in at different loudness or dynamics. So that accent is already giving you that feel, right? Now let's add micro timing to this. So just using dynamics and micro timing, we are creating so much expression, right? So that's the basis for this work. And now coming to candombe drumming. Candombe drumming is very specific style of drumming, a street style drumming from Uruguay in South America. And this is the focus of our work. I'll just play a small clip of what it sounds like. So like you see, there are 3 drums. It's a 4/4 pattern, but the way they groove, the way they swing the beats gives that unique expression. So it's not random. They are in sync with each other, and they are moving the notes away from the grid in a very conscious way, right? So there are 3 drums. One is called Chico, and piano, and repique, which each of them has their own micro timing pattern, and this will be relevant later in the work. Okay, Anmol will take you through the engineering part of this now.
Yep, so after having talked about the musical meaning of what we do, let's go a little bit into the mathematical representations that we use to model this phenomena. First of all, you can think of a quantized grid as simply a 2D matrix where, let's say, your y-axis, if you look at the figure down below, let's say if you're aware of the concepts of beats and bars. So one bar has like 4 beats, but one beat also can have 4 subdivisions. And these are the 16th note subdivisions that are like the most common representation used in popular music. And what we do is that if we model sequences over, let's say, 2 bars, which are, let's say, in our case, we find that those are the lengths over which patterns repeat. So you can model these 2 bar sequences, which would then be 16th note subdivisions for 2 bars. So that's 32 total time steps quantized. That's your x-axis. And the y-axis is, let's say, different instruments. So for our case, which is candombe, there are 3 different instruments. So these 3 different channels, let's say. And modeling each of these channels is important. Now, the first matrix would be the hits matrix, where it's this 32 cross 3 representation, but it's a binary matrix where at each time step, you know where there's a drum hit or not. Then there's 2 other matrices, the velocities and offsets, which are of the same size. And the velocities offsets actually has this information about the MIDI velocities or the dynamics. And we simply scale, let's say, the values from 0 to 127, the ones who are aware of MIDI format, between 0 to 1. And the offsets are actually this micro timing information, because the hits pattern is just binary, and that's what leads to the quantized formulation. Now, how we go back to adding this timing information is through the offsets. And these offsets are from -0.5 to 0.5 at each of the hit positions where there's a 1 hit. And it goes -0.5 to 0.5 because it's like you can either have this beat shifted, let's say, negatively in the which is like a bit quicker to arrive, or it can be slightly delayed, so it will be like a plus positive 0.5 shift. So once you have this mathematically modeled out, we have some more information here about our specific data set on how we extract these informations, but this is the key idea here. And now it's the model architecture part, where we actually, it's a transformer based model, and we go from, so before going into the depths of the model, we go from a very, let's say, just the hits matrix, which you see on the bottom left, to the offsets and velocities matrix, which I, as explained in the previous slide, is the part which actually adds this performance information. And in the general terms, we call this going from score to performance. And how we do it in a transformer is, so we have like an encoder only transformer where we project, and there's some interesting technical details here which we had to, so if you're aware of, let's say, how language models work, you have to tokenize things and stuff, but somehow we find out we actually do not need to, because these representations by themselves are already, let's say, some sort of word vectors. These are interesting details which maybe if some of you are curious, we can talk about later. These were in fact the key details that were very popular at Izmir this year, like because they concentrate a lot on the computer science of it, but it's not very musically relevant, so I'm kind of not going to go so much there. So for let's say a few more details about the model, it's a multi-head self-attention with 4 heads and model dimensions, and again, for the losses, it's a simple mean squared error. So once we have these performances, like once you learn, let's say, this model from a dataset, you give it a hits matrix and you get the offsets and velocities. Now this is interesting because once you learn this groove from a style, not only can you, let's say, get the style back for the same hits, you can actually take these hits, the score patterns from other styles, and see what groove the model adds. So you can maybe, let's say, take some style and play it in the style of another like genre. And so this groove transfer thing is also something that's a direct application of the way we model these rhythms. So here we have some experiments, and I'll probably invite Satya again to talk a bit more about it.
So yes, how much time do we have?
We have it.
Okay. So experiments. So now that the data is represented, we had about 35 minutes of data then which got represented in the way Anmol explained, HVO, hits, velocities and offsets. You train the transformer, and then how do you know whether it has learned something? So you need to do some experiments to evaluate, and for that we use the musicological understanding of Candombe. So and in Candombe, like I said, there are 3 drums. One of them is called a chico, right? And the chico is a timekeeper drum, and it plays the same pattern over and over in every beat, right? So what we did is we took our input data, and then we took the predictions from the model on the chico hits, and we plotted the distribution, and we see that from the distribution, it's very small. I know you can't see all the details, but just to give a general idea of the experiments, that you can see that the distributions are similar. They're not identical, but they're similar. So it means it's learned a general sort of representation. Same with the velocities of the chico hits. So it's learning patterns within a beat, and in the same way we did experiments with patterns at the level of a cycle. So there are patterns called clave. If you're familiar with Latin music, there are patterns which play repeatedly over a bar. They're called clave patterns. So we did the same experiment. So again, it learns the distributions over a cycle. So I will not play the audio examples now. We'll keep the time for the final demo. And so this is the interface. So this plugin, you give it your quantized MIDI file, and you press the humanize button. It adds the groove and velocity, the timing and the velocity, and you can drag that out, or you can play it with the stock samples inside the plugin. Yeah, I think we can play the demo now.
if you heard throughout the performance, like you could definitely felt how when we go from the quantized pattern to humanized, there's a certain groove to it. If you're a musician, it would be much more obvious. And there's one more thing, let's say for the engineers in the audience, if you look below, you can see these distributions of velocities over the entire performance. And if you're aware of the Ableton interface, and if you look at the, let's say the quantized sections, these are all like the same velocities, right? And these are all the same velocities here in the bottom. And these, let's say, are the technical variations which actually add this performance element. Also the timings, but there are too many notes here, so it's hard to see these variations, let's say. And yep, so I want to talk about like why we are here at the ADCx India, because there are a lot of Indian rhythms that have very similar properties, and that's something that we want to explore. And I just want to play, let's say, a tabla sample, and it's very, very evident how groovy it is. So using something like what we do, you can have these same groovy tabla feeling patterns added to some other drum sounds. So let's say you play Latin drum sounds on and you feel tabla like grooves over there, and that's the kind of stuff that we're very interested in. At the end, I'll just want to talk about some of the, let's say, challenges of our work. So there's a huge dependence on data here, which is one of the reasons why we worked with the Candombe dataset, because it was publicly available for such a use case. There also and for Indian datasets, it's a bit hard to find, and we've had a chat about this today morning with some people here as well. The ethical implications, that's also important, because we don't want this to be something that, because there are a lot of cool grooves found in very folk traditions. We don't want this to be a tool that replaces those artists' livelihoods. It's more about, and that's why we claim also, which is also very true, that it's never going to be as good as a human performer. The idea is that someone else can sample the rhythms from some different style, and if you then, some other person from some other part of the world, and then if they really like some particular style, then we hope that this will lead them to actually work with the musicians from different parts of the world. And yep, so the opportunities it provides for us and to the ability to study various rhythmic cultures within the same framework, and what we want to again provide in our tool base. So we want to add more styles, so that music producers can have richer algorithmic rhythm creation tools in music production. So thank you so much, everyone, and you can scan this QR code to check out our VST plugin. And yeah, that's all from us, and thank you.
Hi, thank you so much for that presentation. I would like to learn more about the Candombe dataset itself, and also the categories and how it's structured. And secondly, what do you like the dependence on data? What do you estimate as like the minimum threshold and like a decent threshold for good performance of the VST?
So the first question about the dataset, I think I understood that. So I'm going to first answer that. I mean, it's structured as what we have is for each of these, like let's say 3 different drums, we had 3 different mics. So we had already 3 different channels. And to talk about, let's say it's because it's already labeled by human annotators, so it's very accurate for our tasks. So the actual drum hits at the times were labeled, and also the beats were also labeled. So you have like a beat grid already, and the actual hits, drum hits for each of these channels. So then from that information, it's very straightforward to get to this deviation mapping. For the velocities, what we use is some MIR tools for getting the, if you're aware of the concept of onset strength, and use that as a proxy for the velocity. So these are, let's say, the technical details of the dataset. The second question, could you repeat that? No, I think I didn't get it exactly.
It's more about the size of the data required for the performance to be good.
I see your point. So the thing is that for this, let's say the general task, we had like there's a very large data set for like not genre-specific grooves, but other grooves like MIDI samples. And then let's say if you already have MIDI performances directly, then it's super easy to go from those to quantized performances. And we use that for, let's say, the pre-training part of it. So we already are in some solution space. And then this part of the work is done with actual audio recordings, which is why we need to do these extraction stuff. But then you don't need way too much data if you're like fine-tuning, let's say. I mean, the exact, so we can maybe discuss later on what the numbers would be. But for our performance stuff, it worked fine enough. In fact, like if you're doing, because we do a generative model, it's not exactly correct, but like you kind of want some sort of overfitting. You kind of want to be able to sample from a style specific.
Absolutely, yeah.
So I guess, yeah.
Cool. Thank you so much.
Hey, thank you for the presentation. Do you see the methodology or the approach itself also to help with what's called assessment and learning as well? So since you're modeling deviations, what's called deviations from a standard grade, both in terms of timing, dynamics, and other dimensions here.
I think I didn't get
Do you see an opportunity also in helping, of course, this is music creation, but also the music learning of it. So if I want to learn, say, Candombe, and then learn it like a human, would this kind of a methodology be useful as well?
So when you say learning, you mean learning by a model, right?
Learning by a human.
By a human, okay, as an education.
As an education tool.
Yes. Let's say. Oh, I see. So you mean once the model is ready, then like they can use it to listen back, or like how these deviations are, and sure, yeah. Let's say, for sure, yeah, please.
So like if you're a student of Candombe, right, and you perform and you record it and you use it to evaluate whether this student is performing the right groove or not. I understand the use case, very interesting, but at this point this is very challenging because like we said, to get from audio to that format which is learned by the transformer is a slightly challenging pipeline itself to go from. So that's why we specifically worked with this Candombe dataset, because they have created this rich dataset which goes from audio recordings to human annotations. So that's why data is always a challenge in this kind of project. But I can completely understand like how this could be a useful application. But once that pipeline is ready, which can go from audio recordings to a very nice sort of allocation of every onset to a subdivision, if you have that some way to do that, then opportunities are like many. Yeah.
Right. Yeah. Thanks.
Hey, the dataset that you mentioned, right? Is it tailored based on the choice of artist that you've picked?
Yes. So this is, I think that's a good thing. That's what we want. In fact, like this makes it in fact customizable for each artist. Let's say you are a band and you want to learn your groove, then you have a set of your own recordings and then you throw it in this model and you get a model specific to your groove. And that's very important for musicians, to be able to have, let's say, tools specific to their style. So when we say it's like a Candombe like dataset, of course, there's implicit assumption that it's for these specific artists, the way they've performed it. However, what we do observe even in musicological studies is that these random deviations are not completely random, and there's a pattern to it. So you can find these similar deviations in other performers as well. And when humans perform it, we would expect our model to be able to learn this general representation of the style. But if, let's say, a particular musician has some of their own variations on top of it, they get learned as well. Yeah.
Nice.
Hi, thank you for your presentation. So I just had one question. I'm sure you would have tried sort of collecting audio and then creating a data set without human annotators, because I would think with a drum like this, it's just one sound, like unlike a tabla where they play on different parts of the tabla, this is just one sound. So did you try using maybe an onset detection to cut it into strokes, and then you would get the timestamp which you can translate into like a tick value or something? Did you try something like that? And did you face any challenges?
So, I mean, yeah, that's a very good question.
Tell them about our assignment itself.
I think first of all that would be like very difficult, especially in the case you say where there are multiple sounds. I mean, that's almost like any of so, and I think like we have at least a way, or like how we think there's an easy way to avoid it. Where if you, because even in this case, the candombe dataset has been specifically recorded. So these days there are these, let's say these surfaces for electronic surfaces for something like tabla, and there are these, and there are performers who actually perform tabla grooves on these electronic surfaces, and from then on you entirely skip this problem of having to actually like label these, let's say, annotations. And if you have a bunch of players playing on these electronic tabla hits, you get this very detailed annotations automatically, and as soon as you have it, then the rest of the pipeline follows well. So when we were actually discussing about we would do it for Indian rhythms, that would be the case, but these surfaces are kind of expensive for grad students, so it's we're looking at ways on how we can build forward with this.
Also, like to answer both of your questions, like this started as an assignment actually in our course. So we thought we want something to learn to help us do J Dilla grooves on drums, if you're aware of hip hop, J Dilla. And we started with that. We took some audio recordings, tried to go from that audio to that, and it fails at many different stages, if you want to go, and that sort of stops you from even approaching this problem. So we said, okay, for now we'll skip that pipeline. We'll work with ready-made data in this format. But yes, you're right that technically that's what we are supposed to do. Like if you find a recording of any particular style, you should be able to go from there to this. But there's a pipeline that needs to be really, developed, which goes from that to that hits velocity offset format. That's a little challenge at the moment, yeah. But
okay. Thank you so much.
Any other questions?
One possibly trivial question. This candombe dataset that you're talking about, how big is it? Like,
we write that. I think it's like around 40 minutes of recordings. Yeah, it's that's.
So there's a project called Interpersonal Entrainment in Musical Performances. So they have 3 or 4 different rhythms, including North Indian tabla, I think. But it wasn't as rich as candombe. There's also Mali and Djembe, so you can look it up. Interpersonal Entrainment in Music Performance, IEMP dataset. Yes.
Oh, hi. Thanks for your presentation. This is something that I relate to because I do a lot of drums programming for my own music. I used to, at least. One thing that's challenging is I know where a certain hit has to be placed, but how a drummer would really play would be completely different. It's not just the timing, but it's also like adding ghost notes, right? Would something like this be extended to mimic a human performance? Like let's say I just know rock music 4x4, I know kick, snare, but fill the rest of the space.
Yeah, no, that's in the current format, nope. Because let's say if you don't have the hits mapped out, then however, I think where we are, let's say, differing is how you're thinking about this score, this kicks. Like let's say if there's a ghost note, we would still at the ghost notes have like a 1 in our hits matrix, even though with a very low velocity. So if you're purely doing our framework, you should be able to get that. But strictly speaking, then that would not be in musicological sense the purest score. But our model actually doesn't have that problem. It's just a very low velocity hit. That's how we treat it as. That's how we treat it as.
Okay. Yeah. Thank you.
Yeah. Thank you. We can move on to the next talk. Yeah. A round of applause for both of them. Yeah. So next up is Dharanipathi, and he'll present profiling neural audio plugins.
So, hi everyone. Good afternoon. Good to be here again this year. So today I'll be talking about profiling neural audio plugins. So let's get started. So in essence, what is profiling? So the general idea is that anytime you have some program, you would like to know, how well it performs and what are the bottlenecks that's there, so that you can try and improve the performance. So anytime. So again, the difference between profiling and then benchmarking is that benchmarking is something you do when you either, let's say you have some an algorithm section, you want to see how well it performs with some other algorithm. There's some comparison also between your old version with the new version. But again, profiling is more to do with trying and finding, is there any possible hotspots which you could try and improve. So as it says, benchmark is measured to know your application, while profiling is measured to improve your application. And again, one important thing which anytime you do some profiling, what you need to do is that you always need to profile in the release build, mainly because of the fact that with debug builds you wouldn't really have any optimization that's done, and also with release build it strips away all the debug symbols and stuff. So and also another thing to note is that anytime you build something, always try and include an debug symbol file with it. Otherwise, when you do, when you want to see the call stack and stuff, if you don't have, if it doesn't have the symbol files, it can't really map to the actual memory address with the names of the functions and stuff like that. Another small reminder is anytime you do profiling, just make sure that premature optimization can be costly. So make sure that you don't go deep into it. Just try to get some minute performances and stuff like that. Ideally, you build you build your application, and then you do profiling as you go along to see whether is there any major bottleneck, and if there is something, you try and improve that. And why would we want to profile neural audio plugins? One of the main reasons is that currently, audio plugins are predominantly CPU dependent. Even though there's been explosion of machine learning and things like that, still the DAW ecosystem hasn't really changed. Anytime, even if let's say you're a researcher, you built a nice let's say a morphing model or something, and you want to bring it to the creators, then the only way you can do is make that as a plugin which has to run in real time, in a sense. Take a small buffer, process it, sends it back. So, and again, even though there are companies like GPU Audio working on trying to bring GPU processing into it, we are still mostly reliant on CPU. So performance is very much a key factor here. And also DAWs host multiple plugins. Generally, when you have researchers publish their results and stuff, they focus on just real-time factor of one inference. But let's say in a big project, when you have like hundreds of tracks, and sometimes your plugin can be in series, so everything has to process within that hard deadline. And also neural network-based plugins need to be highly efficient for all these reasons. So profiling is a really important tool to help identify places where we can improve. So in general, we have two broad categories of profiling. One would be sampling based and one would be instrumentation based. Sampling based is pretty simple. The idea is that in a predefined interval, just like how we have sampling with audio, what you do is the program, the operating system, what it does is it goes takes a snapshot of the call stack of your particular process you're trying to profile. So let's say it has multiple threads. It's going to take a snapshot of all the different threads. So in essence, you'll have a snapshot of the call stack, a program counter, registers and stuff like that. And then it just records it, and then later on you could view that. So it's less overhead. You don't do any function calls and stuff like that. Even though there's small bit of time it takes for snapshots, it's pretty low overhead. And disadvantages with that is that sometimes you could miss infrequent bottlenecks. Again, we'll come back to specifically how sampling works and stuff. And then the Instrumentation technique is where you explicitly add some code into your program, and so that anytime that particular code hits, it records something, whatever you're trying to record. And also, you could also have, event-based recording where, like, let's say, sometimes, let's say a cache hit happens or a certain number of cycle happens and stuff like that. The disadvantage with that is, again, the advantage with that is that it's a bit much more detailed, because anytime you have, if you want to know exactly how long a particular function get called or something like that, you would be using instrumentation. Again, we'll look at that in a minute. And the disadvantage with that is that it has a high overhead, because since there might be some function calls every time that particular point hits in your code. So those two would be the broad category. Again, with the different type of profilings, you have something called a time profiling. It measures how long functions take to execute. In essence, it'll tell you, okay, these are all the function calls that happen, and these are all the time it generally took, not a particular function. And then it's generally sample based, and you have something called system trace, where you capture pretty much all system-wide information like CPU cycles, memory allocation, thread interrupts and stuff. And then you also have something called performance counters, which track specific hardware events. You could see cache misses, branch predictions misses, and stuff like that. So since I pretty much use Mac, the profiling tool I use is Xcode. You do have other tools, Xcode instruments. Sorry, you do have other type of profiling tools available for Windows and Linux. So the advantage with instruments is that it's pretty much it's well integrated with Xcode, so you could develop at the same time profile as you go along. And also it has nice visualization features. You could see the call stack, timelines, and everything. We'll look at that in a minute. And also analyze traces alongside timing data. So it has a nice user interface, so that really helps us viewing things. So before I go with that, let's quickly look at how we do time profiling. Again, so this is how instrument looks. So you have different instruments is the name of the app. You also have different instruments which you could select. You have a whole bunch of different type of profiling you could do with that. So in here I have just a bunch of ones. The main thing we will be looking at are audio client, CPU counters, time profiler, and OS signpost. So let's say in this particular example, I have used RT-Neural. It is an a library for real-time neural network inference. Specifically, you could use that for audio. It's real-time safe. So in this case, I have two simple example models. One is a bit small, and another one is a slightly larger model. So in here, if we just go to time profiling, what we could see is that, so you get this, a detailed view at the bottom, and also you could have this track view. So if I zoom out, so in essence, you could see that I have ran the whole profiling for 20 seconds. So this is what the whole CPU usage is in that particular track. The advantage with that is that you could, like let's say I'm in the time profiler track, so I could choose different ways I want to see the call tree. So let's say in this case, I'm going to separate it by threads, and I'm going to hide all the system libraries. So you have these two views. One is called a call tree, and another one is called a flame graph. So in here, the one thing we are, so when I profiled it, I ran the plugin in a simple audio plugin host that comes with Juice. So here you could, the one thing we are looking for is the audio thread. So not this one. So I could expand. Sorry, I think it's the other one, I guess. Am I missing something there? All right. Okay. Can't really get that one exactly out. Anyway, I'll come back to that in a second. The idea is that you can view all the, maybe I'll try in this one. Time profiler. So I could see that. So this gives the whole call stack. So pretty much the HALC is the hardware layer abstraction controller thread. So this is where your real-time processing happens. And you could see that in here is where the process block gets called. So if I want to isolate that, I could see that. And it tells me within these, call stack, it tells you the whole process block in that 20 seconds, it ran for 15 seconds of CPU time. And in that, each of these particular blocks ran for a certain number of times. So more than the call tree view, the flame graph is a bit more ideal to see what gets called and how much time something got spent there. So what the main advantage with this is that if you have a code block and let's say you have a piece of your main forward function that process the neural network, you could pretty much see which section or which function within that takes what amount of time in the overall context, right? It doesn't tell you how exactly or the exact timing of each function call, but it tells you in overall time how much each one contributes to. So it gives you a general idea, but we'll look into instrumentation. That'll tell you a bit more detailed view. So let me go back to the slides. Yeah, so the next one is called instrumentation, as we looked at earlier. So the main advantage with instrumentation is that you could, let's say you have a function and you want to exactly time how long it took for that particular function to get executed. So then you could use, instrumentation. So in Mac OS, you have something called signpost. It comes with the OS log. So you could add that to your code. So in this case, you need to explicitly add, certain macros at points where you want to profile. So, and the advantage with this is it is very precise. It exactly tells you in microseconds and milliseconds how long something ran. Again, signpost is not that much. It doesn't have a lot of overhead. It's kernel level, so it's really handy to do things. The disadvantage is that you need to manually add them into the code. So it's more helpful with development. But let's say you have a compiled binary somebody else wrote, then you can't really use that in that case. So to see that as an example, I have added the signpost in the process block. So in here I could see that. So with RT Neural, you have these two versions. You have this compile time version and also runtime version. So these two tells me where it happens. So I could also choose a certain portion, and let's say if I want to see what happened there, I could take them based on, let's say, let me select that, and then in this case I could see the average time it took for each of those functions, function calls, and also you could see that what's the max time it took. There's not much of a deviation here, so it means that pretty much every time the process block was executing that neural network code, it has consistently been running at an average of 1.2 milliseconds. But when you have this larger code, and if I again see what happens there, in this particular example, I could also see, you could see that even though the average time is between, for the runtime block, it's 8.2, but sometimes the maximum duration has reached 16, right? So this is a bit, it tells you that it's not efficient all the time. Again, in real-time audio programming, the one thing you focus on is the worst case performance. So this helps you identify how much something takes and what's the maximum duration that happened and stuff like that. Again, you could go in depth into it. You could also see where exactly that happened and things like that. I'm just brushing over things here. So that would be your instrumentation. Then the next thing is you could also since we saw earlier, we have something called instrument counters. So the advantage with that is that you could look at things like cache misses and stuff like that. So modern CPU relies heavy much on fast caches. So you have this two type of localities. One is spatial and one is temporal. So with spatial, the idea is that anytime there is this, the computer goes and fetches some chunk of data from the RAM, it doesn't take the exact piece of data it wants. It takes a larger chunk. The assumption is that if you're accessing something, you probably will be accessing something close by soon. So that would be your spatial locality. And temporal locality is that if you access something recently, there's a high chance that you might access that again. So yeah, so the idea is that you try and you could use for example, quickly, if you look at the instrument counter, it tells you how much cache misses happened. In this case, I have L1 cache and also branch misprediction. So you could again see that using your for particular threads and stuff like that. So again, things to keep in mind is that anytime you do some type of let's say you're managing your tensors and stuff like that, you focus on data-oriented approach. In a sense, you do structure of arrays over arrays of structures, so that memory is all in a contiguous block, so that anytime there is prefetching, it's cache friendly. So finally, you have this different type of inference engines that's available right now. So the main one is the Anira is a pretty new one. I think it came a few months back. So the advantage with that is that you could use different backends. You could use Onyx runtime. You could use libtorch. So again, it works on a separate thread. It doesn't run that on the audio thread. With RT-Neural, everything works on the audio thread, but the problem is that it's a pretty doesn't support all operations or layers. So and finally, anytime somebody really want to produce a professional production grade neural network based plugins, personally I feel that the custom inference code is the best way, rather than relying on other methods. So in that particular case, then you would really be you should be taking advantage of profiling, because there's going to be a lot of places where you want to specifically see whether a particular layer, like let's say you work using RT-Neural, you could use RT-Neural for particular layers, and then you could write your own code for your custom layers and stuff like that. So in that case, again, profiling really comes in handy. So that's pretty much it. Yeah, thanks.
Yeah, let's take some questions.
Thank you so much for that talk. Carrying over actually from your last year's talk, have you worked with, for example, using quantization and like these techniques, pruning, and then comparing the and doing profiling basically and seeing what works best?
Not really. Pretty much whatever I have done so far is I use profiling even before you start training, mainly because of the fact that you have an estimation of what type of model size. You don't really need a trained model. All you need is just some random weights, and you could profile it and see whether can this survive, or what's the worst case performance of that, so that can it run in real time. So then you have an estimation of, okay, this is the largest I can go with model size in terms of number of channels or in terms of layer size, and then you further start doing training. Then you do quantization or pruning that way.
I see.
So
because if you run it
still, you could do that with mainly with quantization. It helps with to at least profile and see, do you get any advantages with any particular chunks. But again, that would be more of benchmarking, as I said earlier. Comparing, okay, this is my pruned model and this is my pruned model, how much of an advantage I get, rather than particularly looking at any bottlenecks and stuff like that.
Got it.
Yeah.
And if I was interested in, for example, comparing two inference engines like
Right.
Anira and RT-Neural, would profiling be useful there, or would that be benchmarking?
That again, that's more of a benchmark if you're comparing the whole thing. But as I said, if you're working with some RT-Neural based stuff, and a particular block is taking more time, or a particular layer is taking more time, then you could, or like let's say you're using different backends, XMD, or you're trying to take advantage of Egan or something like that, then you could compare it based on for example, that would be in one thing. And also, if you are using Anira, again with Anira, like let's say you're using Onyx, then that has different execution provider. you could have Core ML there. Then that could use if it's a Mac, then you could use the neural engine and stuff like that.
Okay.
So yeah, for anything that's just a section, then you could use profiling. Yeah.
Cool. Thank you so much.
Any other questions? Okay, so I have a question about, so like say for somebody who's just starting out and who wants to like take the Xcode project and start profiling. So is instrumentation app is part of the Xcode
Yeah, it's
thing
part
itself?
of the Xcode, yeah.
Right. So,
So just when you just like how you have build, you just have another option where you could profile it. So it automatically compiles your code and then opens it in instruments, and then it runs in there, and then you could just profile it.
Right.
So the only tricky part is that you need to, since it's all you're developing VST plugins or AU plugins, then it needs a host to run. So the problem is sometimes the host has to recognize the updated one. So there's a bit of things there, but still it's pretty like let's say you're working on a standalone application, then it's all straightforward.
And like, do you also have like some suggestions on any resource material for anyone who wants to learn more on this?
No.
Except for the documentation available online, is there like a?
To be honest, specifically with instruments, there's not much of documentation available, and even the ones that are available are more focused on Swift for iOS development or specifically for iOS apps, where to see whether there is any hang or lag or things like that. So, but again, yeah, you would be mostly looking at that. But I think like it's pretty intuitive in a sense. If you look at the UI, it's not much there. It's just that you just need to know what you're looking for and what you're seeing. So it should be pretty simple. And I think the one thing I always find it in juice forums and stuff like that is that anytime somebody asks a question, some veteran says that just profile it first. So people should be profiling a lot. So that's the idea.
Okay. All right. Thank you so much. Any other questions? If not, yeah, please round of applause for. I think. Meant to make here. Okay, right. So basically, we'll take a quick break now. It was supposed to be an hour break, but now we'll take an hour and a half break. Unfortunately, the talk that was scheduled at 2 p.m. had to be cancelled for some reasons. So we will all meet here at 2:30 p.m. And for those of you who are Hack Day winners from yesterday, we can discuss your presentation status. For those of you who have your talk scheduled from 2:30 onwards, you can come in here at 2 p.m. for your tech check. And apart from that, the space for lunch, because it's raining outside for the online audience, the lunch would be served indoors, like next to the area where piano is kept. So it's a lobby area. So please be mindful of the space. No food is allowed in this performance theater area, so please don't bring anything here. And the museum tour is scheduled for the evening. So don't take the food and go roam around there as well, right? So just be mindful of like these small bits, and we'll catch up at 2:30 p.m. Again, thank you so much, and we'll connect soon. Have a great time. All right. Welcome back, everyone, in person, watching in person and online. We are going to start our next batch of talks. First of all, I hope you all had a great lunch and did some great networking right now. Okay, let's actually see if people got some energy after eating some food. So, did you all have some fun time? Yes. Nice, this is better than the morning one. All right, awesome. So, the next up we have Dr. Balamurugan, Pawan, and Dhayanithi, who will be giving a talk on the topic Advancing Music Score Source Separation for Indian Classical and Semi-Classical Cinema Compositions. So please give a round of applause for the team.
Okay, thank you. And welcome all for the presentation. So we will have, hope you had a good lunch, and then as usual you had a good energy. And let's go into the source separation model that we have applied for Indian classical music and semi-classical cinema compositions. Here I will be showing only some I'll be showing only some open source classical compositions that has been published in Saraga dataset. That is a very famous dataset from the MTG group of Spain. We have taken some pieces, and then you'll be seeing some segments out of that, and then that will be taken for the source separation models, and we'll be showing it to you instead of only the cinema songs, because of the copy, as usual, the copyright issues, we cannot show those things here. So hope everyone know here what is the importance of source separation, and it has a very long history, at least minimum 30 to 40 years in DSP. It started all with the DSP and then advanced signal processing techniques, and then now it has been entered into music signal processing. Of course it is there. Then our AI came into part for playing inside, and we have started applying for the past 4 or 5 years after the invention of the neural networks, so the attention models and transformer models. We have started applying those things inside the source separation models. And we, like that, we have taken some architectures and we have tested on different types of music genres, like Western music and then Indian classical music, and of course our cine music, which is semi-classical in nature. It is we have a total Western background, but it has an Indian flavor applied over there to that. So like this we have several combinations, and then we have taken some tracks, and then we have applied those things to the different models, and the majorly we have taken 2 models. So here you see here that the Indian classic music system mainly works with, it's not just the an octave of C, D, E, B, A, B, C, the 12 notes. It is totally based on the swara system, which is working on microtones. It is not working just on the notes or just the frequencies, because the ragas are totally dependent on the microtones, and that microtones have glides and slides and the gamakas, what they call, which creates the microtones, or anuswaras they call in ragas, and then you get these kind of complex rich structures for expressing our emotions there. So these kind of things are present inside our system, and we need to separate this music from the these models, the AI models, which are all designed, are not designed for this kind of an architecture. They are designed for totally for the Western system, and so we need to apply such kind of a Western architecture to our system. What is the result? We will see that. And if it is not going to work good, hypothetically we think that it is going to separate the rhythm separately, and then the beat separately, and then vocal separately, like that we are going to think, but we hypothesize that, but it may not be the case. It may not happen for our system. We will see what happens. We have taken 2, if what are the problems or challenges that we face, and what can be changed over there so that it can be applied to our system or the Indian system. So it can be applied by the composers, because the composers are the main people who are going to reach the public, and then we need to create plugins. We have a lot of developers here who can create plugins out of the source separation models, and we can give it to the composers, which they can reach the public. This is what is very well given here, because here the string instruments, already in Western string instruments have the bleeding problem over there, and here also the bleeding problem is very high. Bleeding is what is bleeding in source separation? When you separate a vocal from the others or all other beats and others, this vocal will be infested with all other the string instrument sounds. That is a timbra overlap they call, and then this will be entering inside the vocal thing, frequencies.
Aradayami sadadam Ardanarishwaram Aradayami sadadam Ardanarishwaram Aradayami sadadam Ardanarishwaram.
Okay. So we heard a classical music piece which consisted of a violin, a mridangam, and then a vocalist playing over there with a drone or a shruti being played at the background. So when you like to separate, what are the three things? It's so simple. It is so we need the vocal separately, a violin separately, and the beat or the thala, which is given by the mridangam separately. We have to have these three structures separately coming out of the model. But is this going to happen or not? We will see using the two different types of architectures. So what is this kind of a general classification challenges? As I already very well explained, the timbral problems, what we have, the string instruments colliding with the vocals, and that too this microtonal variations that what we see in the raga also plays a very complex part in vocal separation there. That is one main overlapping problem of the timbral problem. Then the annotated data sets, we have only one data set, that is what is available now, and we have used it over here, because for the Carnatic and in cinema data sets we don't have. Only in the Charaga data set we have for the Carnatic, and we have used it here because for an annotation purpose it is very tough to annotate and take it, as usual for all IA models. Again, I want to again and again say about this microtonal variations are the very, very important things in our system that will create the model more and more complex, and because it is not totally separated out, the frequencies are not totally separate, we cannot simply apply an MFCC coefficient or else a chroma feature over there and then extract out all the information. We need very specific deep understanding of the MIR, music information retrieval features, that is which feature is going to act on which area, and then can we get that information out of that. For that we need a very deep understanding of the music information retrieval features or the attributes that which is going to contribute into the AI model, and these kind of things are much important. And for that we have to in depth we have to understand the model, and then only we can apply that model for our test patterns for the use case. And also they have the dynamic rhythm patterns. The thala can change, and then the beats change, the tempos. There are the gadi systems are there inside our music. Those are not that much the complicated maybe in Western, but I'm sorry, I'm not very good in Western beats. Okay, here these gadi patterns are there, and then separating out those gadi patterns and all those things are also a very big tough job over there. As I told, the timbral overlaps. You have a vocal, you have a string instrument veena over there, and then if you have a nadaswaram over that, it is very, very tough to remove the bleeding out of that, because nadaswaram and veena will entirely have a timbral overlap over the vocal things, our vocal frequencies, which it will merge there. We have tested it very well. We have tested this nadas. When you have a vocal, someone singing there, and then when you the other track is totally overlapping over there, the nadaswaram track is overlapping over the vocals track, then we will not be able to get properly the vocal track. It will be totally bleeding will be occurring there in the vocal track. And also if you have a veena track over the vocal track also, the same problem will occur. So only in Carnatic music concerts, or you won't find so easily a vocal being heard along with a veena or else over an nadaswaram. It will be played separately. The vocal will be first they will be singing, then the veena will be, all other instrument also will be going on around. You can take many concerts, you can see these things also there. So next things about the annotation of the data sets, and then what are the two types of data sets the models we have used. One is a DMux model and the splitter model, both having a very different kind of architectures, but both works on the neural network architecture, but the arrangement of the architecture is different. Those things will be explained by Dhayanithi and Pawan. You can just go on.
So like Sir said, we have very limited data sets for training the models on these specific genres. Like we have very limited data set. We have the well-known Saraga data set, which is recorded from live concerts, which may contain bleeds and bleeds of other instruments also. So we shall go through the existing source separation, well-known source separation models, which is first splitter, which is a unit-based model. Unit architecture is basically a image classification architecture, which is then transferred to audio field also. So this works on unit-based architecture. Like audio is converted to spectrograms, and then it is processed to in unit architecture. And three kinds of models are there available, like they separate 2 stems, 4 stems and 5 stems, like. And then it comes to DMux, which is time domain, and also it also takes unit, it also incorporates unit architecture also. It works on raw audio waveform and also with spectrogram also. So it's a hybrid model, and it takes much computational resource and time also to separate the sources. And then there are OpenUMX, which is also a spectrogram model, and XUMX, enhanced version of UMX, and MIDx model. So we can compare the top 2 models, which is splitter and DMux, which gives better results when it is tested with these kind of genres like classical music and semi-classical music. So as we saw, architecture are both similar, but DMux has one which it works on raw audio form also. Speed comparatively, DMux is time consuming because it works on raw audio. So when it is passed through neural LSTM, it takes time to analyze the patterns and then outputs the stems, various stems. So the speed is comparatively splitter has the fast speed. Like separation quality, as we saw, DMux is though time consuming, but it separates stems clearly by as compared to separation splitter. So this is the separation quality. So we can use both these models for our use case, and it's easy to use. So they come up with different models. Like splitter has 3 models, and DMux also has various stem models, like 4 stems, 3 stems, and up to 7 stems, I think so. So these are the we analyzed these models with our audio track. So this is the original spectrogram. First is we took a original vocal track and compared it with both the sources of splitter separated vocal and also demux separated. So as we can see that what is the audio.
Aradayami sadadam Mardanarishwaram.
So as I said, there is very few dataset which is very which has the quality like original quality. So as compared to Western, it is low quality is low for the existing classical datasets. So this is the vocal and this separated from
Aradayami sadadam Mardanarishwaram.
So we could hear that with vocal mridangam also is bleeded in this vocal part. So splitter struggles to Western trained. It is trained with Western dataset, so it struggles to remove that mridangam because of that peaks, strikes in that which comes across the vocal. So it struggles to separate the sources clearly. And as we compare with
Aradayami sadadam Mardanarishwaram. Aradayami.
So we could hear that this is a little bit clear compared to splitter because it is a hybrid model and it takes time to separate the source clearly. So this we can see the scores. It is in the negative. So because of the quality of audio we have. So comparatively, splitter gives the score better for the classical musics. So as we come here, we take splitter for the Carnatic classification because it is based on unit architecture and it requires less data set comparatively to the DMAX architecture. DMAX is a hybrid model which requires a high quality data set and high resolution data set. So we try to improve this splitter model for this particular genre, which has unit architecture and gets the spectrogram inputs, which contains encoder for the encoding signals, like splits the features separately as it moves through the model. So it has also a skip connection which is used to transfer the low level features directly to the decoder. So we will not lose our fundamental frequencies of the audios. So this skip connection is used for that, and it provides various models for splitter has some models to separate various stems. So working architecture and improvement of this model will be delivered by Dhayanithi.
Okay, hello. Okay, so for the source separation models existing in a Western music system, explained by Pawan, we have seen so much of source separation models. Within that, we have selected two models, which is both are also open source models. One is splitter and another is DMAX. So why we chosen those models is that both models are deeply working in using unit architectures of neural networks model. So now we get into the working model of splitter. So basically, splitter is an open source tool. It is developed by Deegar, which uses deep learning to separate tracks into audio tracks into pieces. which such as vocal, drums, bass, and other instruments. So basically, splitter model works on spectrogram based input. It converts the audio file, in which we can see here. The audio file is input taken as input, and is converted into spectrograms for short-term Fourier transform, which produce a time frequency representation. Then the spectrograms are further processed into a unit architecture, which is contain encoder part and the decoder part and a bottleneck for as it is a unit architecture. In the encoder path, it captures the high-level features and it undergoes dimensional reductions. So in the bottleneck part, we can behind the scene and layers, the abstract features are marked from one layer to another, from first layer to the final layer. Not every features are contributed to for the source separation project. Ultimate goal is to split the audio file into audio pieces. So for that, which features are mainly used to for that separation that can be extracted from the abstract features. Then in the decoder part, it concatenates features from the corresponding layers, and then the abstract features which contains the data of the unique pieces are then gone to a masking layer, which predicts soft marks for each sources. So from that we get the output of different stems. For example, if we had the audio file containing two string instruments and one percussion instrument and the vocal, and it will be, we can by this process the model will give output as vocal and guitar, strings, and a percussion instrument. So this is the working model of the splitter. So basically, what is our idea? We have the Western source separation model, which is trained fully on with Western datas, Western music instrument data. So our goal is to build a model or fine-tune a existing model for perform well for Indian classical music instruments. So so we choose a splitter model. So we have in previously I have say the abstract features. So we can see the what are the features that have selected in the abstract layer. So these are the 9 features which are responsible for splitting from audio file to stem pieces. I just playing 2 audio file. What is inside the audio file is first audio file contain Indian classical audio, which contains 2 instruments. One is veena and mridangam played audio, and another audio is having a Western audio piece having guitar and drums. I will just play the audio for a demonstration. So we have seen that in classical music piece, we just hear the Western music piece. So basically, these two pieces are fed into the model and analysis based on the extra features. So these graphs contains all this first graph says a chroma feature plot of both audio phase. That red color line shows the Carnatic audio piece, the graph of chroma feature of Carnatic piece, and the blue color line shows the chroma features of Western piece. So it is well known that splitter model works well on Western data. So the Western piece of chroma feature is very precise. So while we using on to Carnatic Indian classical piece, we can see how the relation between the two pieces it can be seen in this graphs. How the model perform well for it's not performing well, but it's okay, somewhat working for Indian classical instruments also. These are the features we can see. Okay. So based on the 9 features for abstract features, what is the observation we have find? We have to improve the existing architecture of splitter with these techniques, and it can be performed so well for the Indian classical music system. So these are the techniques like melodic structure, improvising the melodic structures, and overlapping timbre techniques. Using these techniques, we have suggested some filters also. So by using these techniques, this same splitter models can also perform so well for Indian classical instruments. Okay. So we have this same related works are we have a reference taken from music technology group of Spain, Barcelona. Okay, thank you for asking.
So it is, as you have seen, it is not a complete entire project being finished, or we can't. It's only in an observatory case we have taken, and they have applied several changes to the MIR features or the attributes that can be given to the model, and they have tested over there, and they are able to get some very different results for different types of musical pieces, and we are working on that. Yeah. So please, your questions.
Right, so in the interest of time, because we have already passed the time slot, so we won't be able to take any questions, but feel free to meet Bala and team like after the talk as well during the networking breaks and just ask away your questions with them. Round of applause for Bala, Dhayanithi and Pawan.
Okay.
All right. So next up, it's an honor for me to introduce the next person, because anything that you look in terms of music tech and audio tech in India, you will find this name. So Ajay Srinivasamurthy. He will be giving a keynote on the topic Music Informatics for Music of India, Topics, Tools and Trends. A big round of applause for Ajay.
Thank you so much for the introduction, Prashant. I hope you get something out of this. Thank you again for inviting me to present some of my work here. Again, just to kind of mention, the title is very generic. That's intentional, but then a lot of work that I'm going to describe here is going to be inspired or kind of biased towards my work a little bit more, mainly because the field is so vast, and then I have worked only on a part of it. I'm not aware of the entire field. Yeah. So with that disclaimer, yeah. So I just want to kind of start with a quick show of hands, just to kind of read the room a little bit. So how many of you are trained in music? This should not be a question, but then just a show of hands. Yeah, it's almost everyone, so that's good. And how many of you are trained in Indian art or folk music? Art music is Carnatic classical, Hindustani classical, or folk, any of the folk musics of India? Okay, so it's quite a good number. And how many of you are trained in Eurogenetic, or as it's popularly called, Western music? Okay, thank you. Yeah, and electronic music, how many of you play electronic music? Very enthusiastic show of hands here. Yeah, thank you, that's good. So I mean, that just is a broad spectrum, and then so when we kind of go and then try to answer what Indian music is, it's not clear because India is so diverse. So let's try and kind of address some issues. And how many of you are avid music listeners, at least? Yeah, that should be everyone in the room, actually. Yeah, okay. And how many of you understand signal processing and or machine learning thoroughly, I would say? Yeah. I mean, okay, exposed, that's fine. Thoroughly, I think. Yeah. Okay, all right. Yeah, this just to kind of understand what depth I should go into. Yeah, perfect. Thank you so much. Let's start. I mean, so let's start with what is art of music. Well, in fact, music, I think, is a part of a lot of music, I mean, world cultures, and then it's prehistoric as well, right? And then it's closely tied to traditions, not so much recently, but in the past it was, both in instruments and form. And they also say it's one of the uniquely human creations, in addition to, say, language. Language also exists in other species of the world, but music, not so much. And music has independently developed universals in different parts of the world that were completely disjoint and disconnected. It just means that there is something inherently human in that. And then a lot of them relate to melody, rhythm, and harmony. I mean, harmony, debatable in Indian music, but then, yeah. So that's one of the concepts, right? And when I say Indian music here, I kind of encompass everything that currently exists in India, which could be art music, Carnatic and Hindustani predominantly. There are others, of course, and then folk and film music. So this is hard to define, very hard to define. So I will kind of stick to some defined music traditions, just to be kind of not treading on like unknown charter territory. But then, as I think it was pointed out, both our folk and film music are also inspired from any of the existing, either Eurogenetic music or in Indian art music, or some folk music, right? A folk is also kind of, so it's hard to kind of define and then describe. So, but let's still try to kind of understand if some of the techniques and try to kind of apply, also extend that, right? Then comes the science of music. Science of music is broadly, I think personally, two directions. One is to systematically study the music, which kind of comes in this field of musicology and music theory. And then understanding of music, which is music perception and cognition. This is the science. What some basic questions there would be: why is music musical? Why emotions and music? How do we correlate between them? Do I need culture-specific attributes to describe music versus what is universal? What is culture-specific? And what is the meaning of improvisation? Where does that virtuosity in some musicians come from, whereas others? So where is that distinction coming from? Then, more familiarly for this audience, the engineering of music. This is not new. The earliest examples, any music instrument that you hold in your hand is an engineered piece of work, actually, right? So earliest examples are music instruments, piano being one of them, for example. I mean, it created a revolution for music to move across continents, and then it created a very low barrier for people to learn. Same with music scores, for example, like people could transmit music across Atlantic or something like that, which was not at all possible before sheet music, for example, came in. All of those are engineering of music, right? And last few decades, I think I would say engineering of music was mainly supporting the music industry, kind of with MIDI, synthesizers, samplers, recording and playback technologies being built. And more recently, when I say more recently, is the last 2-3 decades maybe, it's this interdisciplinary MIR, as it's called. What do we do there? Mainly, we develop tools and applications for representation, understanding, analysis, synthesis. If I want to give you some examples, I think all of you are familiar with these examples. That's the piano. This is Hatsune Miku, who is a Japanese icon who kind of sings synthesized music. And sheet music, as I was talking about, that's the tambura box. And then this is we have a nice handle on a mridangam, which makes it easier to carry, but destroys the sound. But then, yeah. So all of them are like examples of engineering. And then you see a big DAW on the side and some applications here, right? All of them are examples. So what do I kind of say when I say music technology here? This is a very long definition. I'll take parts of it and then so that we understand it. So as engineers, we are worried about building tools and technologies. That's our basic work. Why are we doing that? For the functions of playback, consume, analyze, understand, appreciate, store, archive. So these are functions, and then that's what I call as music informatics. And then there is also this other functions like learn, teach, compose, analyze, understand, appreciate. So that's a part of computational musicology. Musicology in general, and since engineers get involved, they want to add a prefix to that and then call it computational. Right? So what's MIR? MIR for me is a very interdisciplinary field with so many different inputs coming in from so many practitioners. So that's why if you want to study MIR, we need to kind of bring in several people together who speak different language together to kind of work together, right? So computational musicology, before just this slide, just to give you an understanding, it's a scholarly analysis of music. It's multidisciplinary, but again bringing in data into foray, and then bringing in tools that engineers use to kind of learn these facets of music. And perspectives, how would you, so we can learn music, we can do musicology from a historical perspective, cultural or cognitive, right? And then basically the underlying core part is we use computational tools for musicology. That's the idea, right? And then, I mean, when we want to make it data driven, then it becomes more of music corpora level statistical analysis. So I have a huge corpus of recordings. So I mean, I start with a musicological idea. I say, okay, what could be this particular music? What's this element doing in this particular piece? I kind of make a hypothesis. Then you do experiments with lots of data. That we have tools for that, and then kind of come up with useful generalizations there. Right, and then it's mainly the idea there is to supplement and complement manual analysis. So I mean, you could see even now, in fact, in musicology departments, people work with 10 pieces of music and then work on it for 4 years, and then really write a fantastic analytical thesis on how those 10 pieces are to be analyzed. And then what if you could expand this 10 music pieces to 10 million music pieces? So that's what we are trying to do here. Scale to large corpora, generalize, and then verify common knowledge. Somebody will say, this particular music is very harsh for my ear. So what makes it harsh, and at the level of human population, right? Or kind of derive additional insights into music, right? So what opportunities do exist in the field right now? So we live in a multicultural world. So in fact, each music exists its own socio-cultural context. So using that is an important opportunity as well as a challenge. We have lots of data, but everything is copyrighted in the music industry. So that's why I can't even play some music pieces here. But then, so they are unlabeled and suboptimally organized. So that's the main issue here. So copyrighted music, unlabeled, suboptimally organized. So that's like a clear opportunity there. And there is subjectivity in general, which is a hallmark of music. In fact, it's necessary. It's there in creation, consumption, and analysis. So there is also subjectivity in consumption, which we don't think about, and analysis, right? I mean, people don't agree on the concepts being exactly the same, and then they do not agree on a particular music piece being a particular way, all of those. And so that's where we need to define music similarity. What does similar mean in that kind of a subjective world, right? And it's interdisciplinary, which means we need to involve the community as we want. And then different people speak different languages. So I mean, language in the sense of terminology, everything changes. So in that context, what we started to try out to build was to build culture-aware technologies. That's where Comp Music project comes in. So which was to build culture-aware music information research tools, wherein the idea was to bring music knowledge into methods that we build, music concepts into engineering formulations, convert them, and then involve music communities. These were the three main tenets of the music. We studied these 5 music cultures at that time, and then I'm going to describe some of that work here. So let's come back to the idea of musics of India. What does it mean? So I'm predominantly talking about art music, which includes Hindustani and Carnatic music, and folk music, which I can't enumerate here. They're very rich and diverse, largely oral traditions in India, right? I mean, they're orally transmitted. Nothing is written down. So my grandmother told it to my mother, and my mother taught it to me, kind of a kind of transmission. There are very few formal schools where you can go and learn folk music. It's still a part of you go do field research, learn a few songs from somebody, and then come back, record it. So it's very difficult to kind of work on that. But there are elements of art music in folk music, no, not formalized, and in fact vice versa. A lot of folk music got kind of agglomerated together, concepts came together into art music, right? The way it's practiced today. Film music is, again, there is no bounds there. It's rich, diverse, cross-genre, varied instrumentation. And film music is kind of the main way I would say Indians consume music, a large set of Indians. So it's necessary to be analyzed, but then having the tools with art and folk music and Western music, probably we'll be able to address film music in the future. Right, again, I think we have a good introduction to Indian art music from the previous talk and before. So I'm mostly going to talk about Carnatic and Hindustani music. Carnatic music from south of India, south of the Indian subcontinent. So Sri Lanka also practices some bit of Carnatic music. Hindustani music, again, northern part of the Indian subcontinent. I say subcontinent because you will see some part of Hindustani music also practiced in Pakistan and then Bangladesh as well, right? So, I mean, this is again the original Nepal, even in Nepal a bit. So, but again, this is again what I would say is like a part of it. But now with the Indian diaspora around the world, so you will see this music around the world as well now, right? So what's the difference between these two? I mean, mainly some concepts and terminology, they are very similar, but there are differences in practice. As I said, I think mainly, so that's the geographical location. But they come with centuries of evolution. So they have evolved over like quite a few, with influences from, as India was culturally evolving, the musics of India were also culturally evolving, right? So what I would emphasize currently is that they come with sophisticated melodic and rhythmic structures right now. What that means is there is a huge body of literature which explains this, talks about this. There have been clearly a PhD thesis on musicology which explains how these structures are, which is a necessary fundamental foundation on which engineers can build things. So it makes it easy for us to kind of work on them. So why exactly? So this is because the music is predominantly oral, and then they have sophisticated structures, and then there is a lot of scope for improvisation, wide variety of instruments and variations, and it continues to evolve as we speak, right? I mean, music that was 30 years ago is not the same music today. When the microphone was introduced, it caused a change in the way Indian music was performed, for example, right? So now the vocalist did not have to shout at the top of their voice and beat the mridangam in their sound. So it kind of made it so much more easier for them. So that kind of changed the music a little bit. So it continues to evolve with technology and everything, right? And in terms of community, it has a large dedicated audience, which is good, and at the same time significant musicological literature. So we can borrow from literature, build tools, give it to an audience that will consume them. So that's essentially means that we can do something that is meaningful and contribute back. But they come with unique challenges, of course, right? So I would just like to emphasize on one big challenge where I think most of my work has gone into. It's then organizing music collections with data, right? I mean, typically if you go to Spotify today and you want to learn, search for music, the way you would do is artist, album, title. So I want to search this artist, this album, this title. And the music is also organized in that way. But that's not really how we consume Indian art music as well. Like the way we consume is something like that. Can you play? I want to kind of remember. Do you remember that little slow kriti in Mohan Raga and Mishra Chaptala that the teacher taught us that day, right? That's how we want to kind of search. So what we want to do is search with these, and then some examples could be, I have highlighted some keywords in red, which is necessary for us to do this search. So Tintal Bandish, for example, and other things. So this is largely editorial metadata, right? So you could say a particular song, you can go to the musicians and then say, what is the form of this music? What's the raga? What's the tala? They'll tell you, and then you just write it down. publish it as a part of the song, and then you can search with that, right? So that's editorial metadata. But there are certain more things that are not exactly editorial metadata, like they are content-based descriptors. They are coming from the content, right? So what does that mean? So play a slow kriti. What does slow kriti mean here? And then can you show me a playlist of the Trintal Bandish that contain improvisatory sections? So what are improvisatory sections? That can only be deciphered from the content, right? And other songs that have similar rhythmic passages, what does that mean, right? So that's also not very clear. So these needs, so we can start with organizing music collections based on editorial metadata, but that's not sufficient. We also need to go and then do content-based description. Understand what's there in the content and use them to organize your music collections. So at the end, we want to get to a situation which kind of is like enriched interaction with music. That's what we want to do, wherein we kind of want to kind of organize music and discover music through editorial metadata as well as content-based descriptors, and with large collections. So we have large collections which can be enriched with these, and then we can group them based on similarity measures which are based on content essentially. And then with Indian art music, so anything to do with that. So when we want to define similarity, when it comes to melody, we have to build descriptors that are related to the raga, and then with rhythm, with the thala, right? So, and at the same time, we want to build what is necessary for the community, involving musicians, music students, musicologists, listeners, engineers, scientists, technologies, essentially all of them, music producers, record labels, as well as address the subjectivity that is like the elephant in the room, right? So built for the community, enriched interaction, products and then technologies that could be used by the community, which includes producers, consumers, teachers, and then everyone, right? And additionally, this is a pet problem for me, which is to make the code open source and then data easily accessible. So that kind of builds the community and then moves it forward, right? So this is not a necessity from a consumer perspective, but then it's necessary for the research to continue as it goes. So I want to take a small detour here just to kind of give a perspective of where we are with respect to machine learning. So this kind of comes back together when we look at the data and then see how inadequate it is for the existing kind of work that's being done with AI externally, right? So we started out with rule-based analytics. This is just a very quick overview of evolution of machine learning from my perspective again. So we started with rule-based analytical systems wherein we had human expertise. We wrote rules saying, okay, if it's less than this, it's this. If it's less than that, greater than that, it's that category, right? And then we were able to write those rules. Then we moved to a place wherein we had a little more data. Therein we kind of started extracting abstractions out of with human expertise, so features, and then we would build a function mapper again, which would learn from data, and then we would kind of do the same machine learning, data-driven expert systems. Then data-driven large models. So large models need limited human expertise currently, but lots of data. You see the imbalance changing from human expertise to data. And so now we are in a different mode of operation, if you see with respect to several other domains, wherein we kind of start with a representation or a feature or an embedding learning, and then we kind of fine-tune models based on some foundation models that we have built from huge amounts of data. So we build generic foundation models, which can kind of on an average do multiple different tasks. Then we fine-tune them with little bit of data towards a particular problem. That's where we are now. So now this is the paradigm currently, and then we have to see how music problems can be mapped to this, and at the same time what kind of data can be used to kind of get to an architecture that works like this, right? So let's go back again. So let's go back to what are the MIR topics and tools that we have at our disposal. I want to kind of put it in this abstraction layer here, simple to complex. Simple not from a technological perspective or it's easy to do, but more from music understanding and what musicians would think is this is like trivial versus this is more subjective, right? So I'll start with onset and pitch, for example. Those are objectively defined, could be objectively defined. Then comes meter and melody. So meter builds on onsets, melody builds on pitch, and then segmentation problems, which is to kind of understand problems and then patterns. And then once we segment, we can build out patterns out of those segments, and then finally define similarity based on that, right? So this is like different levels of abstraction that we could do. I'll give you basic examples of each of them as we go. I'll not be able to cover all the problems here, but then just a sampling of several problems in each of them. So before we start any of these, we need representations of music that we could use for kind of understanding and then extracting out these music descriptors, right? So they help us to interpret, transmit, and archive. So we saw audio, so for example, so PCM is a representation, so digitizing and then just sending out numbers instead of audio waveforms. Audio waveform is a representation because that's how most of us that's like a direct mapping between a pressure wave amplitude and an amplitude in a particular signal that you are representing, right? But again, representations can vary with content and can be lossy. So we might lose information when we change representations, right? So, and they might represent only some or all the elements of music. So broadly, we could say we have two broad representations, symbolic representations, which uses music scores, piano rolls, MIDI, for example, and they could be prescriptive or descriptive. Most of the music scores are prescriptive, so they are not describing a performance, but then they are telling us how to perform. Whereas acoustic representations are direct representations of recordings, so they do not have that abstraction level, but then they were exactly what was performed. So waveforms, spectrograms, compressed audio, MP3, for example, right? And features that we extract from audio, they are descriptors. They are also acoustic representations, right? So with these representations, let's look at some tasks, basic tasks. So let's start with tonic identification as a problem. This is a fundamental task, so I just want to spend a little while on this, right? So tonic in Indian art music, it's essentially what's called the pitch of the drone, right? If I want to kind of simplify here, it's flexibly chosen by the lead musician, which is a deviation from, say, what is typically done, say, in Western music, wherein a particular key could be kind of chosen for reference. And then the tampura or the tambura is the drone that's tuned to the tonic. And then all instruments are tuned to the tonic. If they can be pitch tuned, including the mridangam and percussion instruments, right? So it's a fundamental task, hence, to kind of understand what the tambura is, because that's the reference for every melody that is being sung, right? It's useful for defining melodic patterns. So if you don't know the tonic, a transposition in melody can actually mean something different, and that we'll not be able to get that it's a transposition unless we know the tonic, right? It's also useful in intonation analysis, understanding what the melodic content of the music piece is, and also extract ragas, right? So yeah, that's once we have the tonic, then we can actually do melody extraction. So predominant melody is what's called fundamental frequency of the whole recording that we are trying to extract. So predominant melody extraction is, I think, for Western music is defined in a different way. But then when it comes to Indian music, we kind of already face a roadblock here, because so what's a complete representation for a melody? So is it a sequence of frequency values, or is it a sequence of notes? So typically when people say a melody, they just sing out a sequence of notes and then say that's a melody. But then that's not all it, because each of notes are articulated in a particular way, and that is captured through a sequence of frequency values. But at the same time, if you just look at the frequency values, you do not have the identity of the swaras there, or the notes. So what is the best representation? And that depends on the problem. There is no one answer for that, right? So what I'm saying is sequence of notes is inadequate, sequence of frequency values is over adequate, and then we still need to go back to the abstraction of notes if you want to kind of do something meaningful, right? Yeah. And in terms of pitch estimation, so how do we estimate pitch? So let's say we want to extract a sequence of frequency values of a particular, when I say predominant melody, it's the melody sung by the lead artist there, which could be vocal, it could be an instrument as well, right? And then, so now, if you want to do that pitch estimation, so we have to kind of solve the cases of solo instrument versus multiple instruments, right? And also kind of understand the characteristics of the melodic contours so that we can extract them out. And then typically in Indian music, we have dual melodic lines. So if you see most of the music, you heard that, right? An example, I can also play one example. So we had the lead vocal and then a violin closely following it. So you have two melodic lines that are coming in with a little bit of delay, right? So the melody the violin player takes a little while to understand what the vocalist is singing and then kind of follows it, right? So there is usually a little bit of delay. In addition, of course, there are also differences. So violinists can play something different as well. Same with Hindustani music, where they usually use sarangi or harmonium, right, as the accompaniment, which also kind of does something similar. So these are problems to solve in pitch estimation for Indian music. Right, let me just give you a quick example here. Let me see if the sound is too loud. Okay, sorry. Let me pause here. So this is a monophonic, so there is no violin playing here. It's a simple example because I wanted it to work. So yeah, so you see the spectrogram very well. You see the harmonic series very nicely here. And then now you want to extract the melody. This is how it sounds. I've just sonified it with a set of sinusoids. See, there is an error made by the pitch tracker here. It's going to a different place and then just coming back, right? So this is what we want to extract. So from this contours, now I can actually extract out patterns, and then we can do several things. Let's start with pitch histogram. So now I extracted this contour. I've simplified it for the sake of here. So I have 3 different notes, and then I have that's how the progression of the melody is going. And then if I just average it out, right, and plot a histogram, this is how it's going to look like. So it just means that Re has it stayed in Re for 2 seconds, whereas in Sa and then Ga stayed for about a second, right? So this is an important content wherein like we can clearly say how much each swara is being sung, and then it kind of gives us a lot of information. If you do this averaging over several different recordings, this is what you see. So you see something like this, wherein you have all of these notes, and then you see some kind of a distribution of each of these notes, and then this is what is called an intonation curve. It tells me a lot about, so there was this comment made that there are a lot of microtones which come in the form of gamakas, right, in Carnatic music or even in Hindustani music. There's not a very easy way to model them, and then this is like compressing all of them and then saying if you see a peak to be wider, it just means that there is a lot of meandering around that note, and then it just means that there is a lot of oscillations around that note, and then so you can characterize this curve and then understand a little bit of raga characteristics. In fact, this pitch histogram is used quite often for recognizing ragas as well. So now let's move on to melodic motifs. So with this, I can also look at patterns, which are sequences of these melodies, right? So short segments of melody, sequence of notes, pitch contours. So both of them are melodic motifs. And there are characteristic melodic phrases. If you are trained in Carnatic or Hindustani music, you'll know that a particular raga has a characteristic melody. As soon as you hear the name of the raga, you know that's the melody. If you hear that and then say, okay, this is this, it gives an raga identity, right? So those are characteristic melodic phrases. They are quite repeated within and across music pieces, even in an alap or even in an improvisatory section. You want to bring the flavor of the raga, so you kind of sing that often and often. So like what we want to do is something like that. So I'll just play an example. So this is work of a colleague, Sankalp Gulati, so wherein he kind of pulled together patterns from a huge corpus of recordings, put them together based on similarity, and then this is how they sound out. So each of those clusters that you see there, they are similar melodies. I've picked one cluster. I'll just play a few examples from that. You see the diverse set of instruments, they are all from different recordings, but then it was able to extract out these patterns. So now I can kind of say, this is a part of music piece that I'm looking for. Can you find this particular pattern in all of the recordings? And then it would basically be able to go and search and then give you all those recordings where this particular pattern occurs, right? So this is a more useful kind of search that we can do. Let's move to rhythm. I know some rhythm guys are there in the hall here. So rhythm, in fact, let's build on it, right? So essentially rhythm is characterized through onsets and tempo and in fact meter afterwards, right? Onset is a note event, so they are basically events in time, whereas like you have pitch to be on the frequency grid, right? So and then these onsets are grouped to form different rhythmic structures like beats and bar and so on and so forth. And tempo is, you could define it to be like the median inter-onset interval, which is a good estimate of tempo, for example, and it could be time varying. So people can vary tempo, they can go faster or slower. So we take local averages of sorts, right? So that's how onsets look like in a very clean piece. So it never looks like this in real world. So these are like essentially places where you have a hard hit, for example. So I can play an example here. You see, these are some of the onsets extracted by an algorithm, and you'll see those red lines on on the graph. It's too faint, I think, but then, so those are the onsets that were identified. I can play an example, and then you'll hear clicks at the places where there are onsets. So the song starts, and then after a while, you'll start hearing the clicks. So you could hear those clicks. So they are the onset as detected by the algorithms. This is one of the onset detection algorithms. So you see, largely they were kind of tracking the mridangam, which is like giving a nice set of onsets. But this becomes a problem as soon as you remove percussion instruments, or there is onsets even in vocal singing, right? And then it's a hard problem to detect that. There are of course some approaches to do this. So this is like a typical approach. So you would do some pre-processing, then you would convert the signal into a detection function based on amplitudes, and then, or working in the frequency domain with spectral flux. Then you would do some kind of a differencing, and then you would get peaks of that to be the onsets. So that's like a overall, what do I say, an approach that people take to do onset detection. Once you have these onsets, then we could move to the next level of rhythmic analysis, which is meter. So meter is a general term. It's also used in speaking, poetry. I mean, it means that in Indian music, it relates to extracting out the components of the tala, and in probably Western music, it's the beats and the bars essentially, right? So we want to kind of detect beats and downbeats, and then also estimate tempo, rhythm class. Rhythm class here is the tala, name of the tala, and then patterns, right? So I kind of wanted to kind of distinguish two different problems here. One is the problem of meter inference. When I say inference, you don't know anything about the music piece, and then now I want to kind of detect which tala it is, then track the tempo, the beats, and the downbeats, all of them together, right? Whereas meter tracking, so this is a problem that makes the algorithm, go a little happier. So wherein we kind of tell you that this is the tala. So when I kind of give you the structure saying, okay, this is an 8-beat cycle, now can you track it? Right? So that's easier to do, because marking out each of the beats of a music piece is a hard task, because now you have to align, then you have to struggle. But then giving the name of the tala is an easier problem, right? And then it makes it easier for the algorithm to track the meter, right? So there the rhythm class is known, the structure is known, what am I tracking, that's known, and then now I'm tracking only the beats and the downbeats. Let me give you an example, right? So this is an example in Carnatic music. So this is a cycle of 3 beats. So I marked so there is a downbeat, or sama as it's called here, which is marked with X. Then there are 2 and 3. So X, 2, 3, X, 2, 3, right? And then it goes in a cycle. So the X sounds a little different, whereas the 2 and 3 sound a little different here. X, 2, 3, X. So this is, I think most of you followed this, right? So let's take this example, which is again a cycle of 12 beats here in Hindustani music. In Vilambit, Vilambit is slow meter. So the previous one had a nice little 90 beats per minute kind of a beat BPM. So it's easier to track. So let's listen to this. So this is a cycle of 12 beats. So it starts on the sum with the first beat, and then let's see where it is going. Yeah, let's see if you can track this, right? That's the downbeat X. 1, beat number 2, sorry. 3. Which beat are we on? 6? You were counting. Okay, good. No, you see, so there is a concept called working memory. I think in general applies in cognitive. I'm not an expert, but then so anything that's longer than the beat period here is about 5 to 6 seconds, and then the cycle itself is about a minute long, and then that's not actually a cycle that could fit in your working memory. So you can't track it as a cycle, but then as events that are happening slowly. right? So so compared to the previous piece, this is a much harder. This is not a solved problem. So I miserably failed solving this problem. So if people are interested, solving Vilam with Tala tracking is a open problem for you. So you see now, you see the wide variety in Indian music, right? So you have cycles which are 3 seconds long to 60 seconds long, and then now how do you track the beats of this long cycle, wherein the structure, if you just play this to somebody who doesn't know Hindustani music, they'll not be able to track this. I mean, they can still, if you give them the structure and then if they handhold them, they'll be able to do it, but it's a hard task, right? So now with that, we have extracted out the metrical structure. So most of the patterns are aligned with the metrical structure, and then we could extract out rhythm and percussion patterns. So what's the difference? Rhythm pattern is typically not directly always associated with percussion instruments, whereas percussion pattern, it's a sequence of strokes of a percussion instrument, for example, right? So what do we do with that? So lots of things could be done musicologically. So we could extract out cycle length rhythm patterns, which are quite relevant, and then they could be used to represent accents in a cycle. So they are very useful for meter analysis. So this is example. So you see, this is a cycle of 8 beats. X starts for beat 1, and then so you have 1, 2, 3, 4, 5, 6, 7, and 8. There's a repetition. The other X is the next cycle, right? And then if you put all those patterns together, chop the entire signal into cycle length pieces, extract out features, average them out, this is how it looks like. So what it says is kind of beats 1 and 3 have accents, strong accents, 5 and 7 as well, and 1 and 5 are similar. So this is like a representation. You go with this to a musician and then say, this is Adi Tala, cycle of 8 beats, and then ask them, where do you think the accents for this Tala cycle is? They're going to tell you something similar. So we are kind of verifying musicological, so we are trying to find evidence for some musicological concepts that are like common knowledge. They'll say, okay, I want to emphasize on half of the cycle and then the 7th beat, whereas can you verify that with some data? So this is what could be an example, right? So then once you have these, then you kind of go supra a little and then kind of say, if I have the whole concert, can I segment it into smaller pieces? The most logical one would be, in most of the way we consume Indian music is through concerts. Not so much for Hindustani music, but more for Carnatic music. So you go to a concert, they play 12, 13 music pieces, each of them in a different tala and a raga, and then you come back and then, So that's how you consume music. Now can you segment this automatically into pieces? And then there are ways to do that. And then within a percussion or within a kriti, which is a piece of music, so can you segment out sections? Right? Each section will have multiple tala cycles, multiple patterns, and then everything together. Now everything is coming together. In a concert, can I segment it first? Then can I annotate it with rhythmic cycles, for example? Then can I identify melodic patterns? Can I identify the tonic, the onsets, the tempo, and then kind of present that music piece with this enriched information for you to consume. So that's the problem we are trying to solve. Then you could kind of do this for a whole data set, and then that comes the problem of like organizing music collections based on these content-based descriptors. So I've left out several set of tasks that you could do here, but then this is like gives you probably an overview, right? So now with all of these, we could define what's called similarity, right? So can I look for these structures not at the level of audio or at the level of metadata, but based on the content and the descriptors that I've extracted from content, right? So that's the problem we are trying to solve. If you want to understand more, please, again, this is one place. So there's a monograph on Indian art music. It's a book with contributed chapters from several of the leading researchers in India and elsewhere who are working on Indian art music, right? So, and then I think we contributed with a chapter here, which is called Getting Started on Computational Musicology and MIR from an Indian music perspective, art music largely. This talks about different tasks that we could take up. What are some important, immediate approaches, right? The problem is always the trade-off between, I have to start something new. Where do I start from, right? And then can we borrow, or it's not really borrow, can we understand what has been done in the state of the art and how does it actually apply to, when I apply to Indian art music? So we don't know that. So it's like baselining whatever we are doing. And then we can, of course, build on top of it. And the same thing is with data. So what data exists already, can we use some of it for building our systems, right? And then as we do that, we kind of can build newer methods after we baseline ourselves against the state of the art, right? So this chapter kind of talks about some of those elements. So please, if you find, I can share it, or it's on Google play. It's a book, so it could be a good read to start with. One thing that I think we haven't touched upon, so we kind of looked at source separation, for example, right, as a problem. Source separation is a very tough problem because of all the problems that were mentioned, right? So there is a bleed, and then most of the music is performed in a live setting, right? I mean, and that's by design. In fact, musicians are kind of pretty much interacting with each other. You can't put them in like boxes, like drum boxes as they are in studios, and then ask them to play a concert. So that's not going to happen. So bleed is not a bug, it's a feature of the current concert system, right? So what do you do in such a case? And then, I mean, source separation has been, I think even my PhD supervisor used to say it's not a problem we should work on because it's very hard to solve. But then I think now we see a lot of progress in that with splitter and demux and then very fantastic advances that it's recently solvable. I mean, solvable in the sense of we can at least try to solve it, right? The other problem that I think keeps coming up once in a while, it started from the legacy of C.V. Raman, is the actually kind of design and development of electronic Indian music instruments. And at the same time, which is kind of a corollary to that is the analysis of Indian music instruments and modeling of them, right? So today, in fact, if you go and then ask for you want to buy a veena, you go to a shop and then say, I want a veena, there is no standard veena. So they will ask you, whom do you want it from? So which is the name of the artisan essentially, or the person who is making the veenas, or a set of people, right? So that knowledge is very, very tribal these days. When I say tribal in the sense of known only to a set of people, and then it's transmitted orally, and then there is lots of information in transmission. So standardization here kind of is about kind of documenting best practices, or understanding what are the characteristics of the instrument that I'm looking for, and then what's the impact of changing this part of the wood, this particular wax, and then this particular material on the final sound of the instrument, right? So what makes a good violin and a bad violin? There is a lot of study to kind of say why is it that some companies make the best pianos versus some others are kind of not, right? So that analysis hasn't been done for Indian music, and then so that kind of what it makes is there is a limited throughput for our artisans as well. So they can only make certain number of veenas or a certain number of mridangams as their kind of manufacturing process. And then if you make them efficient, we can get good instruments out to everyone. At the same time, we can also kind of say this is a standard, or a good mridangam should sound like this, and then this is the process to do that. And then that it's a part of our heritage, right? To understand how things are. What if, like, say, 2 generations later, we don't know how to make a mridangam? So then we are at loss, right? So this is an useful problem. In fact, G. Rajnarayan, the author of this particular chapter, runs. In fact, he's a very senior electronic music instrument manufacturer in India called Radil. So he's the founder there. And then he talks about building the tanpura, for example, electronic tanpura, which used to be, I mean, people used to carry the tanpura before 2 decades ago. Now you don't see that. You see a small box which does really well. So that's like an innovation, right? So he talks about that. And then so if you want to take up modeling instruments, again, there's a lot of scope there to build on things. So I just want to kind of wrap up by giving some resources that exist for different MIR tasks. Just to kind of quickly introduce, so building data sets itself is a research problem. In fact, it is essential for data-driven MIR. It's a research problem as well. So we need to involve the communities that we're eventually going to consume. I'm just kind of, again, copied from the previous slide. What's the community here, right? So what exactly are we trying to build? So we have a real world, right? And then we build a research corpus, which is a subset of that real world, which can be used for multiple set of problems. And out of that, we build test data sets. These are data sets that are useful for specific tasks. So to give you an example, there is Carnatic music out there in the real world. Then I kind of bring in n number of hours of Carnatic music, which is a representation of Carnatic music outside, which is a research corpus. Out of that, I kind of annotate a part of that for doing beat tracking. So that's a test data set. And in fact, test data sets can even come outside of the real world for synthetic data and then things like that, right? So, and then just to kind of see how do we build data sets? I mean, I think we need data sets. How do we build them? There are some systematic ways of building and approaching. This is one way. So you kind of analyze what's the purpose, what's the coverage of the data. So why are we building this data set? What's the coverage? Does it cover all the elements and the concepts that I want to kind of model? And completeness within the concepts that I want to model, does it include all the information I need to kind of do the analysis? Then quality, it's self-explained, needs to be of good quality. Reusability. So am I kind of going to some remote repository, pulling out data, and then not annotating it? And then am I able to share that data set outside of the research group? Because music is copyrighted, so I do an analysis, I publish a paper, but that data set is no longer, you can't really share it outside, which immediately means that nobody else can build on it except you, for that matter. Including you can't really publish too much out of that, right? Yeah, so which means that we need open data sets or commercially available data sets with good annotations, but so that we can map back. So I say, this is the song I used, this is where you can buy it. So you can also buy it and then do work on that, right? So, based on reliable references. So, the other approach that people can take, I think, please read through this is very useful, FAIR principles, which kind of similar in terms of philosophy, wherein we have to build data that is, and then this is more on machine actionability. So the previous one I talked about is in general. Here, this FAIR principles was a framework that was developed mainly for machine learning data sets. So accessibility through machines, right? So findable, accessible, interoperable, and reusable, same ideas. So findable metadata allows for easier discovery. So I can find the data easily. And at the same time, it's accessible through, again, it has good metadata, so I can navigate through the collection better. Interoperable, so which means that I have APIs, or essentially it could be easily integrated into other systems that exist, right? And reusable. Reusable is, I think it's everything now, because we have to do collaborative research here, right? Yeah. So, I think there was a mention of Saraga here. I'll also talk about Saraga, but again, some of the data sets from ComMusic are available through a browser to kind of look at how the data set is and everything, and also through an API, so that you could kind of go and then download some of the data and do analysis. There are already some pre-computed features and all. So the audio of ComMusic is commercial audio, so they are easily available. So you can buy those recordings, for example. And at the same time, we also have an open audio collection, which is Saraga, and then extensions of that, right, as well. There are some extracted features already through open licenses, and editorial metadata is on MusicBrainz, which is a repo of metadata of music in the world. And annotations are publicly available, so they are available as data sets, and all of these are archived on Zenodo. So if you find some of these data sets, you can go to Zenodo, there's a form, you can fill in your details, and you'll be able to get some of access to those data sets. So there are several data sets. I don't want to go into the detail. So several of the examples that you saw were built, the tasks were built using these data sets. So please look through them. It's available in this URL, which you'll have access to. There are so many data sets here. And talking about Saraga, I think we wanted to kind of at some point move away from copyrighted music towards open data sets. And then this was one effort towards that. Wherein the idea was to kind of build a large annotated open collection. When I say large, this was 2015, so large was large doesn't seem very large in the current context of large models. Yeah, and we wanted to share it under Creative Commons licenses, so that we don't have the issue of copyrights essentially. So audio and editorial metadata, we use the same best practices here to kind of annotate. It also comes with automatic annotations about melody, rhythm, and structure. I think so. This Saraga dataset is available. So basic stats is there are some multi-track recordings as well. Like, so it comes to about 100 hours of music, Carnatic and Hindustani, right? Access through open source API. You can fetch metadata, source, and derived files through that. And it's version controlled. It's a public repository. So you can also, if you see a mistake, you can send us a pull request, and we'll merge it, and then it make the dataset better through as we go. Right? Please contribute if you please use, and then please see if you want to add more data to that, please do contribute as you want. Several applications that you can use it for, several MIR tasks, melody extraction, automatic rhythm annotation, several tasks. One good application that came out was musical bridges. In fact, this was an app developed at MTG again, wherein they talked about music understanding and appreciation, and then how do you kind of bring somebody to appreciate a new music genre you've never heard before by kind of providing additional information about what's happening in your melodic structure, rhythmic structure with the music piece, right? It involves interactive visualization. So if you search for musical bridges, you'll see this. And then we also have an app, which is not currently well maintained. It has all the elements here, in fact, and then you can do enriched listening of Saraga collections. So you will see a song, you'll see all the annotations, you'll know exactly where samas are, you know what are the phrases that are being sung, and then so it was a nice app. It visualizes metadata really well. Several, I think, there is a Saraga audiovisual, which is not really an extension, but a separate data set that was built. So at some point in time, I think recently, so there was, I mean, so the video modality came into picture, and then there is a lot of interaction that's happening from the musicians and between the musicians that also add to the experience of understanding music. It's not only the audio dimension. So Saraga audiovisual kind of includes the video of the recording as well, concert, and with all these annotations of different gestures, which could be useful for kind of building multimodal applications here. And then we also have the Sanidha dataset. Sanidha dataset addresses this problem of bleeding, right? So there is a lot of bleeding that's there in Saraga dataset, multi-track. Again, as I said, it's a feature, but then doesn't mean it's a good feature. So it's hard to kind of build anything for source separation with bleeds already in place in ground truth, right? So this talks about studio quality multi-track recordings with minimal or no bleed, because they actually put musicians in boxes and then recorded this. They had video of the other musicians, so they could still interact in some way, but then they were kind of very isolated. And these are HT videos plus audio, which has very less bleed. Right? Just to kind of wrap up with opportunities that exist in India, these are some of the institutions that are working on music. We should see more institutions. We are seeing more institutions now. I see more institutions that are coming in working on MIR in India, right? And industry, of course, there's a lot of interest from the industry in music. On India, Beethoven, in fact, Siddharth runs Beethoven. And then we have Sensible, and then we have Music Muni Labs. These are like homegrown Indian startups, as well as we have all these large companies. Radel has been there for 30 years now, or even 40 years maybe. Yeah. So, and then there is a lot of interest. And then, so community, ISMER is International Society for Music Information Retrieval. Please, if you are interested in any activities of the society, which also includes the conferences, so please to join that list. Comp Music has a mailing list. It's not very active right now. And then if you want to understand where MIR is going, this is a good roadmap to kind of look at. It talks about, it kind of got inputs from several of the senior researchers in the world, and then put together a roadmap. It's updated every few years. And then we have music tech community in India, which I think Siddharth and Albin and Manasvi, Prashant, they're doing a fantastic job with that as well. Please to join these communities to contribute. To learn, there are several examples, several books, and then there are like tutorials that are available on specifically, again, the Spark monograph is a good starting point as well. And build and contribute, please. Hack days, I think I don't need to explain to this community that hack days are fun. And then there are also hack days that happen as a part of ISMER and then several other places. Please to contribute again. This again is a MIR evaluation exchange is a place where there are like, it's like a benchmarking portal wherein you could submit your algorithms and then also for specific tasks and then see how they perform on unseen data. And with a lot of interest, in fact, the community, in fact, MIR includes some of the Carnatic and Hindustani music data sets for evaluation. It's a good indicator that there are music cultures that are like clearly applications, with clear applications. And then currently, I think there is one opportunity I just want to briefly mention about building an application for enhanced discovery and listening of Indian art music. If you're interested, please do reach out. Where we want to work on curated collections and then go from listening to enriched listening to guided listening to discovery to interactives. So that's like the progression of, and then we want to combine audio, text, symbolic representations. So please get in touch. I just really want to thank some of my collaborators and then mentors and guides whom I work with. So you'll see works from several of these people in what I described. Lastly, I just want to kind of leave it here to kind of say we are organizing ICASP satellite workshop. This is in Hyderabad in April. It's called Vimaga, Workshop on Indian Music Analysis and Generative Applications. It's a one-day workshop, which is, I think, the papers, we had several interesting submissions, and then there are going to be several papers presented, and several experts that come to ICASP on music, they are going to kind of give us talks there. So please to join if you find the time. Yeah, thank you so much. Thanks for your time.
I think we can take some questions. Anyone?
Hi. Do you have any comment on the impact of MIDI 2.0 on MIR in Indian art music?
I'm not too familiar with MIDI 2.0 specifically. Haven't worked too much with symbolic music. Sorry. Yeah. But I mean, anyone else in the audience who's familiar, maybe?
I can answer this question partially because I'm sort of started working on this myself. But with MIDI 2.0, there's this protocol called MPE, just come out. And in fact, a lot of you who are on Insta might have seen some artists, Carnatic, who are performing on an iPad using apps like GeoShred, which uses this protocol. And the advantage of this is it's more intuitive than the previous MIDI, where every note is being given its own independent control. So every note you can add a gamaka, for example, you know. So that's going to be quite a game changer. It's being adapted right now, adopted, and even for the Western, music production software, not all of them have completely integrated it, but already people are familiar that this is a powerful protocol, and I see myself like it having a lot of applications for Indian art music, because the amount of expression we put on a single note, I mean, we need a very robust sort of representation, and MIDI 2.0, especially MPE, is something you should look into. Yeah.
All right, thank you. Anyone? Any other questions?
Hello, thank you for your talk. I was just wondering about what you were saying about structural segmentation, and then you showed like the audiovisual data set as well. I think the concerts were from RK Convention Center.
Right, that's right.
And they have like a live chat where people are constantly like posting like what ragam it is, what composition it is. I was wondering if you had tried using like the text modality for segmenting instead of like, say, just using the audio and like the rhythm and all of that, like using the text to add meta tags or something like that.
Yeah, thank you for the question. So yes, I mean, in fact, there is text, and there is also, in fact, one of the approaches that, so if you have a listing already of the concert, which you could get from social media, Rasika Priya, for example, or essentially which talks about the concert, then it becomes much more easier. I know that there are 12 pieces, I know this is the structure. At the same time, what was also tried out was applause, essentially, as a way of kind of distinguishing music pieces. So there's usually people clap after a piece, but people also clap in between pieces in Carnatic music. So if they really like the phrasing and everything, we should ideally use all modalities that are available, including text. Text was used because we had listing, and then it was used to map largely, but also to understand how many segments to actually make it to.
Hi sir, it's so nice to meet you in person finally, because we are working in the same domain as you, and thank you for your wonderful contribution to Indian art music. And my question is regarding the subjectivity that we discussed about. You said like, do you consider that Western music is more generative than Indian classical music due to the various aspects of folk music interference that's being performed all over India? So is that a factor that affects subjectivity of Indian art music? Is subjectivity considered a difference between Western and Indian classical art form? And another question I want to add on the same aspect is that how do you think that forming communities, music communities, is going to eliminate the subjectivity problem of music?
Right, yeah, thank you. I mean, music is inherently subjective and different kinds of subjectivity exists. And as you kind of, I mean, so the purpose of music is not just conveying meaning, right? I mean, so that's the purpose of language. So there is less subjectivity there. Music inherently has it, and I don't know enough to kind of comment if Western music has more subjectivity or less than Indian art music. But in terms of like influences, it's almost similar, right? I mean, even when we say Eurogenetic music, it has evolved over multiple centuries. It has influence from everywhere, and then so similar to India. India is very diverse as well, right? So the subjectivity itself comes from like a diverse set of people not agreeing on set of things. So if we have the second one, right? Second question. So if you form communities, you can at least build that discussion, and then that's how musicology grows. So certain things can be agreed upon, and then engineers can take over. I don't want to take over something that's very subjective still among musicians, right? Then I'm solving the wrong problem. Then as engineers, we can take over things that are at least largely objective, and then move on, or kind of build tools that can help manage subjectivity. And subjectivity will never go away. I don't think the goal is to eliminate subjectivity. In fact, that's what keeps the music alive and then nice as well, right?
I think there was one more question here.
Thank you for the very informative session. My question is, you had said that there is challenge with respect to data sets not being labeled properly. Is there a particular format in which you would expect the data sets to be labeled so that for training purposes it becomes easier? Like I know that DDEX standards exist, but is that the one?
No, I think I'm aware of DDEX. I think very recently we started a conversation with them about kind of having a, I mean not for Indian music in general, but ISMER being a little more involved with DDEX so that we can establish some standards at least. But as of now, there is no standard. And then that kind of surely affects each person chooses their own way of annotating. Some of them are simple to convert, like you have some clear JSONs and then CSVs. So they are easy to manage. Whereas if you want to kind of annotate more, have more interoperable data sets, there is some bit of effort to kind of build APIs. So you could, I mean, so to kind of organize all data sets together, say in a Zenodo repository, and then have a set of recipes that can access each of those data sets. So there are some individual efforts towards that, but then I don't, at least to my knowledge, there's not a really standard, but it's good to have. But at the same time, it also depends on what applications we are building these standards for. So if there are suitable applications that can benefit from this, why not? Surely, yeah.
Any other questions? Okay, a round of applause for Ajay again.
Thank you.
All right. We are back for the next talk. I hope everybody had a good time networking. We'll again get one more chance after we conclude for today. So our next speaker is Harsha Vardhan, who will be giving a talk on spatial localization and techniques for synthesizing real-time binaural audio for headphones. Give a round of applause for Harsha Vardhan.
Hello everyone. My name is Harsha. I am a computer science student at BIT Mishra. I work with C++ and Juice to make audio plugins. Today I'm going to talk about spatial localization and binaural audio and making binaural audio from normal audio. So let's start from the basics. What is spatial localization, right? It's about being able to locate the source of an audio just by hearing without actually looking at it. This happens because animal and human brains kind of see the differences between your left and right ear signals and kind of differentiate and kind of get the information out of it to kind of approximate where the audio source is located. The things that our brain used to differentiate these things are called localization cues, which we are going to talk about in a minute. It's even happening right now. You can see that the audio is coming from the speakers even if you close your eyes, because your brain can kind of see the difference and conclude the audio source. So why is there a need to study this localization and spatial localization, and why is there a need to reverse engineer this, right? Well, one of the main things is it's really interesting because it's really interesting to see how we can be able to just locate an object just by hearing it, and also the more important thing is reproducing this, taking understanding how this works and kind of using that to create our own plugins or effects that reproduce this binaural effect. And there are a lot of applications for this. For example, movies have surround sound, games, virtual reality. Virtual reality is very depending on binaural audio. And for example, emulating spaces. For example, Meta has this kind of whole virtual space thing, and you can use this binaural audio to completely recreate the environment, including the visuals and the audio. And for this talk, the most important thing is being able to emulate binaural audio from normal audio. So I use this word binaural audio a couple of times before, but what exactly is it, right? Bi stands for two, and aural is anything that is related to hearing. So binaural audio is how humans actually hear sound, because the sound we hear is not exactly what the sound is produced at the source. It has a lot of reflections kind of embedded into it. It has reflections from your head, your ears, your external ears, your body, and diffraction from your head on the shadowed side, and all of the stuff. And so recording this binaural audio is not possible through a single microphone. You need a special setup of microphones. Like you can have two earphones set up at the beginning of ear canals on both of the sides and kind of record this audio and kind of play it back. So the end user who is listening to it kind of listens what you are particularly experiencing at the moment, instead of listening to the original sound. And by emulating binaural audio, I mean taking any arbitrary signal which does not have a positional information of the source and adding the positional information based on any arbitrary position. And a little terminology based on this talk, we are going to use spherical coordinates, and the horizontal angle is called azimuth. It changes from 0 to 360, increases from front to the right, and elevation, it changes from negative 90 to positive 90, where negative 90 is below, and radius is from 0 to infinity, where 0 is from the start of the ear and not at the center of the head. So I talked about localization cues that our brain uses to kind of approximate the source position, right? And here are 4 localization cues that I'm going to talk about today. And the first one is intraoral level difference. It's the difference between apparent sound intensity between the two ears. This actually happens because of something called the head shadowing effect, because when there is a sound wave produced at some point, your head is kind of an obstruction for it, right? So it kind of diffracts at the edges, and because lower frequencies can diffract better than higher frequencies kind of get attenuated. This causes this attenuation in the sound level in the shadowed side of the head. Like the ear which is in the shadowed side of the head kind of has lower perceived loudness of the sound than the opposite side. And also this can also happen because when the sound source is really near to the head. Because sound has an R² fall off, just like most waves. If the difference it can create in movement, even in small distances, can be like enough to kind of create this level difference. Like the amount of perceived loudness in one ear can be completely different to other because of the distance. At longer distances, it may not be a big thing. And the second localization cue is interaural time difference. It's basically because sound is finite speed wave, it kind of takes time. The difference between the sound reaches from one ear to other kind of causes this delay, which humans cannot actually consciously recognize, but our brains can subconsciously analyze this to kind of confirm this. And third and most important localization cue are spectral cues. Spectral cues are frequency notches and frequency peaks that are formed by reflection and diffraction from the external ear, from your head, and from your body. This happens because when sound is positioned differently, some of the frequencies get kind of resonated, and some of them kind of get attenuated based on your ear structure. And this is really useful because level difference and time difference can only get you up to some point. For example, time difference cannot tell you the elevation, similarly with the level difference, but spectral cues can give you a really good idea about where this is positioned, where the elevation is positioned, and the distance from the source that is positioned. And also this, because everybody has a different structure in ear, head, and your torso, you'll get different types of notches and peaks in this spectral frequency spectrum that that help you to kind of localize where the sound is positioned. But the change in notches, like how the notches change from azimuth and how they change with elevation, which we are going to see in a minute, will remain same for pretty much all of the people. It may change for animals though. So how are we going to measure these spectral cues? Like there are frequency peaks and notches, right? But how are we going to measure them? There is something called head-related impulse responses. It's basically, for anybody who doesn't know what is impulse response is, it's basically an audio sample which contains information about how a frequency kind of goes through, how a frequency kind of behaves depending on time. So generally they use a small white noise sample to kind of start it, and they record what's left of it to get the head-related impulse response. It kind of captures all the spectral cues, the notches, the peaks, and everything related to information when it is recorded. And the subject, the person or the dummy head, has like 2 earphones at the beginning of their ear canals, and the whole thing is recorded. And if you think about it, because both of the microphones start recording at the same time, it also has like the level difference and the time difference kind of built into it, which is really important, because when we do convolution, it kind of gets transferred directly without any external effort. And here are some few visualizations that I did based on how spectral cues change based on azimuth, how they change based on elevation, and how they change based on distance. So here's a small video. You can clearly see like the level difference, the level of the left, what we hear in left ear is kind of changing, and you can also see the peaks and notches kind of sliding over in the frequency spectrum. And when the source is coming to the opposite side, you can see the opposite happening. And also another thing to observe is the ear that is in the shadow side of the head kind of has this fuzzy spectrum fuzzy spectral cues rather than these sharp spectral cues that are in the actual side of the source. And these are this is with elevation, how spectral cues change with elevation. This is at 0 azimuth, and you can, I know the image is really small, but you can see kind of like a low pass thing happening at the elevation about 0 and kind of notches passing through here. These things your brain can kind of subconsciously analyze and know the elevation and kind of information from that. And this is finally, this is like the change with distance. For example, this is at 0.5 meters, this is at 1 meter, this is at 2 meter, and this is at 3 meter with the same azimuth and elevation. And we can see from increasing distance, the spectral cues become more fuzzy. Like here, there are much well-defined peaks and notches, which kind of become more fuzzier as we go through. And so here, head impulse responses, we have the impulse responses, but how are we going to actually modify and distribute them, right? We cannot have like a bunch of impulse responses and give it to somebody, naming HRIR at 0 azimuth and 0 elevation, right? So people who worked on this stuff kind of came up with their own file format called SOFA. It stands for Spatially Oriented Format for Acoustics, has an extension .sofa. It contains like the metadata, the room structure, the microphone it was recorded with, the setup that was used, and everything else kind of built into it. The file has all of this stuff, and the impulse responses are also built into this file, so you can just use the file and distribute it with others. And this file in the beginning, this file actually had APIs from MATLAB and GNU Octave, if anybody uses GNU Octave. But afterwards, they had APIs from Python, so from a library called SOFA, which I actually used. And you also have C++ APIs if you want to use. And finally, one thing that I wanted to mention, all of the things that we are discussing till now are kind of measured in an anechoic chamber. That is, no reverb is recorded. Every sound wave that is going to the wall is completely absorbed, so you will not get any kind of reflection from the sound, so no reverb is observed. But there are data sets that are called BRIRs, binaural room impulse responses, which are actually by design recorded in a room, so they also contain information about the reverb and all the diffuse tails, reverb tails, everything. And this is a website, if anybody is interested, you can find like a compilation of all the impulse responses and transfer functions. So the fourth localization queue is dynamic queues. This is not an explicit localization queue, but like a amalgamation of the other ones. This is the queue that we get because of the relative motion between source and observer. For example, those I talked about the changing trends, right? Those trends can actually help us to kind of position, remove disambiguities and stuff like that, to position and get better precision at approximating where the audio source is. And also I wanted to mention a couple of other things. Are Doppler effect, you guys probably know about it, which is used to kind of remove the disambiguity in distance, and parallax effect, because the amount of angle change near will be much bigger from the measured from the ear, and from if the same distance, it will not be so different in angles at a longer distance. So now for the more interesting part, how do we take all this information about localization cues and kind of use it to make our own binaural audio, right? By making binaural audio, I mean emulating binaural audio, which I already talked about before, taking any arbitrary signal and kind of positioning it in space. For some people, this might be really intuitive, but so we want to find a way to take the characteristics, take the time delay, take the level difference, take the spectral cues, the notches, the peaks and everything, and kind of transfer it to our arbitrary signal. So how are we going to do it? We are going to use a convolution. Convolution is a mathematical operation that is equivalent to kind of multiplication in the frequency domain. We can use this to kind of take information about take information that is present in the impulse responses and kind of give it to our signal that we want to make binaural. So here is a small overview or the pipeline that I'm using right now. We have HRDF databases that are the SOFA files that we are considering to use. We can have multiple of them or based on what we want. And pre-processing consists of removing the time differences, the whole time differences. I'll talk about why we remove them afterwards. The complete time differences and relatively normalized channels at all different distances. And also we only select the data points which we want in the pre-processing step, or we create new ones based on interpolation. And we create a model. The model basically what it does is it takes like a spherical coordinates and kinds of spits out your impulse response, which you can use as an impulse response for your convolution engine. And in real time it can basically apply these characteristics to the signal. And some of the challenges that I faced during this are, first things first, IR measurements are discrete. That is, most people who measure these head-related impulse responses, it's not even possible to measure every possible spherical coordinate, right? So they'll always cover only partially. That is, at for example 5 degree discreteness or something, and elevation at probably 10 degree. So we will get this kind of mesh that you need to make it much more. You need to make it more resolution basically. And the second thing is adding time difference and attenuation with distance. I'll talk about, you may notice I told we remove them in before and now we are adding them. It kind of like makes no sense, but I'll talk why we do it. And third one is space, because everything is like naturally everything we work is like a reverb environment, right? We do not work in an anechoic chamber where there are like no reflections of sound and everything. So it's really important to kind of incorporate this space or reverb thing directly into the sound or the binaural audio that we are making. And also, even if you use a binaural room impulse response, which is actually recorded in a room, you won't get the flexibility because it's only recorded in a single room. You cannot have like a bigger spaces or everything. So solution for 1 and 2 are like solution for the problem, solution for the challenge 1 and 2. It's about interpolation. Instead of interpolating direct impulse responses, we interpolate them in frequency domain using certain steps that I'm going to talk about. So first we are going to start. We'll take a arbitrary position of which we want the impulse response to be at, and we find the nearest 3 points. And using barycentric coordinates, probably anyone using computer graphics might know about this, or you can just measure the distance from it. You can have them as weighted average or something. And having the interpolation in frequency domain kind of gives you a good enough result that you can actually use. And then we add the time delay, because convolution, if you have time delay and convolution, it automatically gives the delay to the signal that we are processing, and interpolate between distances, because most HRTF databases are from a single distance. So in order to kind of interpolate between different data sets, we need to have like a proper mechanism to have the attenuation based on the distances and other things. And convolution, so that's what I'm talking about. Scaling IR with distance get naturally transferred, because convolution also transfers the scaling if you do not normalize the signal before. These are like the pros and cons of interpolation. Interpolation gives you a really bigger spatial resolution than having those discrete points which they are only recorded. But there are certain cons. For example, you cannot do like some kind of pre-calculation and storage, because it will be way too big to store it anyways, and your binary is going to be massive. But there is a second point. We need to because we need to interpolate this at runtime. There are going to be runtime costs, which can be kind of reduced with caching, which I'm going to talk about. So for the question I asked about earlier, why are we actually removing the ITDs and adding them afterwards, right? Why are we removing the delay and adding it afterwards? It's because interpolating in frequency domain doesn't exactly kind of interpolate the time delay. Like, it doesn't interpolate the number of empty samples before your impulse response actually starts. So you kind of need to remove it before and add it afterwards, because when you are interpolating between two different data points and they have different delays in time before, you are not going to get a good result. You are not going to get like an average delay if you are going to do a frequency interpolation. And about the relative normalization I talked about in the pre-processing step, it's because first things we need to do relative normalization because interaural level difference is kind of built into the convolution. It is built into the impulse response. So we need to preserve the difference between two channels. And also the normalization is really important when you are kind of interpolating between two different distances, because two data sets may use different kinds of levels which we need to normalize before applying the attenuation afterwards. And solution for 3, adding reverb. Why can't we have an inbuilt reverberator? This is like a good question. Because we cannot have a reverb in serial, because when we are already when we are adding the characteristics from your impulse response to the signal, adding a reverb kind of already has those spectral cues, right? But reverb doesn't actually work like that. Reverb works because of the reflections of your sound based on the room and based on the source, and it doesn't have much of a directional value to it. Even though it changes with the direction, it doesn't much have a single directional cues to it. So that's the second point. Reverb tail contains some information about source position, but it doesn't actually fully incorporate a single directional source. It kind of is a spread out version. So we are actually going to use a parallel convolutor which is going to have the reverb convolution in it, and which only has the reverb tail part of the impulse response, because the head part is going to get convoluted in the HRTF convolutor, which gets those characteristics that I'm talking about. And about I just talked about how the reverb also has like data about this source position, right? So we are going to give the characteristics to it based on the first reflection. That is, for example, if I'm talking from here, first reflection would be something like this, evolve to this and here, and the reverb is going to have like slight characteristics because of that. That is, the reverb tail is going to have a slightly louder voice on this side because there are more reflections closer to me, and also the time delay is going to be different, right? Because a sound wave traveling from here to there and coming back takes much less time than it's going from here to there and coming back to me. So we can also add like these kind of time delays and level differences based on the first reflection to add this horizontal localization cue. And for elevation, you can add like simple low passing and stuff like that, which I talked about earlier. And a small thing about caching, if any programmer is interested, we use a min heap to kind of preserve the latest used and most used impulse responses instead of generating them every time, and kind of have a much optimized way at runtime, because we do not want to calculate every time, even though if it's calculated before. And if you are interested in this topic, there are some other topics that you might also be interested. Ambisonics is basically kind of creating the spatial audio effect using multiple speakers and speaker setups. And surround sound, we all know Dolby audio and home theaters. Head tracking is about tracking your head and kind of changing the sound position based on your head tracking. And directional recording is basically having multiple speakers at different directions pointing to different directions, and they kind of capture like a 360-degree audio. And psychoacoustics is basically how audio will be affected, and how audio is how we take audio, how we think about audio and everything. So this study is made basically for a plugin that I'm working on, which will be open source and will be released on next month. And so check it out. Thank you for having me. Hope you enjoy.
Any questions?
So
So hello Harsha, yeah, it's a really great work. I really enjoyed your presentation, and you have put up a lot of research effort in the presentation. I can very well feel there. I hope you have worked with MATLAB.
No, I actually use Python scripts.
Python,
Yes.
okay, that's okay. So because we have tried a lot with this kind of spatial computing, and so I know the difficulties in this. And apart from that, I really congratulate for going into the area of psychoacoustics, which is very niche topic in of course in our country that too. And at present we were working in collaboration for the psychoacoustic, typically this binaural audios for dementia detection actually, and this is very important there, and for sure I will connect you with that doctor from, he is a neurologist in London, and he needs this kind of an application over there, because this is a very important topic for such a high mortality rate is there for dementia people when they're affected with this kind of a mental disorder, and they use this kind of a diagnostic tool for detecting dementia. So for that I was amazed on seeing this being taken over there. Okay, thank you. Okay.
That's amazing. Anyone with any other questions? No? Yeah.
So what file sizes are the SOFA files?
It depends based on the recordings, the sample rate, and everything. They can change from 1 megabyte to 802 gigabytes or something.
How do you compose them? I'm guessing the impulses are recorded with like a regular mic.
No, not a regular mic. I talked about
I
it.
mean,
right? You have like
as in
a
they are
directional
recorded
mic.
as regular audio files.
Yes, they are recorded
and
as
then
regular audio
you
files.
compose them into, like, you consolidate all of this information.
Yes, into a single file.
Into a single file, okay.
All right, so that's the time we had for these questions. A round of applause again for Harshavardhan. All right, so now we have the last talk of today before we get to the conclusions and other bits. So this talk is by Joshua, and the topic is Auralization and Active Sound Design with Spatial Audio on a Vehicle Simulator. Round of applause for Joshua.
Thank you all for joining this presentation, and thanks Prashant for the introduction. Hello everyone, my name is Joshua, and I'm an early stage researcher and an audio engineer for over a decade now. And today I'll be talking about auralization and active sound design with spatial audio on a vehicle simulator. So in this talk, I'll give a short introduction and a little background about myself, what I do, and what is my research, and also the importance of automotive audio. And I will touch a bit upon active sound design, and also give a brief introduction about spatial audio. Also, thanks to Harsha, he has covered a nice overview of binaural audio and convolution, which also I'll be covering a bit on. And I'll be talking about my research that I'm doing and the current work and the future works. So I work as a research engineer associate at Siemens, which is located in Belgium, in the nice city of Leuven, and our office looks like this. It's a beautiful campus out there. I work in the acoustics team in a project called Gap Noise, which is funded by the European Union. I'm also doing a PhD in mechanical engineering with focus on acoustics, which is also located in the city of Leuven. The university name is KU Leuven. Before this, I did my master's in sound and music computing from Maynooth University in Ireland, and I did my bachelor's here in India on computer applications, and I also hold a diploma in audio engineering from Music Launch School of Audio Technology. So my research focus is on spatial audio, acoustic, NVH technologies, and sound synthesis. So this picture, this is my life for over 10 years. And I'm sure you all also can relate to this. We go to the studio or our mixing space, we make music, we mix for hours, bass is tight, it's punchy, highs are nice and crisp, and everything is on place. And we go and play it back in the car, and we know what happens. It doesn't sound good, or sometimes it sounds great, but we can never judge how it's gonna sound in the car before. So why is it? Because cars or any vehicles are complex spaces with speakers located in weird positions. So it's important as musicians and audio engineers to understand the space our audio is going to play back. So it's important to consider that cars are not just a mode of transportation anymore, but a space to listen to music, to feel emotions, and to spend time while traveling. So now, before I get into the topic, I will play two sounds, and I want you to all to tell me which one sounds more powerful and sporty. Okay, raise of hands. Who chooses A? Not surprising, no one. And who chooses B? Great. Now I'll play two more sounds, and you have to tell me which one is faster. Okay, who chooses A? No one, no surprise. And who chooses B? Everyone. So my friends, you did not see any accelerometer. You did not feel the wind on your face, or you did not see how fast the car is going. But how do you know that this car is powerful? Or how do you know this car is going this speed? So it's important to understand the auditory senses. Even without visual cues, we humans have the tendency to identify certain emotions, not just emotion, but also the perception using our auditory sensors and audio cues. Which brings me to the topic of active sound design. So manufacturers, they don't just keep it as theory, but actually implement these theories into actions when they build a car or manufacture a car. So music producers, who are a combination of engineers and music producers, they sit and design the car's sound, how it should sound on the exterior and how it should sound on the interior. So active sound design is a process of artificially generating and modifying vehicle sounds in real time to enhance driving experience, emotion, and safety, especially in electric and autonomous cars. Even though it's a creative process, there are certain rules and regulations that we have to apply. There are like some certain engineering rules and also rules and standards from the government on how loud it should be on the exterior, how it should be on the interior for safety and perception. And the most common methods that producers or the engineers use in this technology are order-based synthesis and granular synthesis, which is a familiar model of synthesis, which you guys are an expert more than me. So this is an interesting graph of a comparison between ICE vehicle, an internal combustion engine, versus an electric vehicle. As you can see, the ICE has the powertrain noise or the engine noise predominantly taking over the overall contribution of the sound. But when you go to the EV, the sound has completely reduced. The powertrain noise came from 50 to 15%. And the main contributors of sound now is road and wind noise. So how do we approach it? So through active sound design and through active noise cancellation, we implement this technology into these cars to create brand sounds, specific brands of specific car sounds, and also to make the passenger comfortable and also make the space more pleasurable. But it doesn't just stop there. More than EV, the future of cars is autonomous and smart mobility, where there is going to be no drivers in the cars, and it's going to drive around automatically. And there are going to be complex speaker systems placed inside the car with a lot of sensors outside the car as well, like ADAS, like radar, LiDAR, and a lot of cameras. So as engineers and musicians and composers, it is important for us to have tools to design sounds for these platforms. So we cannot build an entire car and then test. If it doesn't work out, we go and scrap the car. No, it doesn't work like that. We need a simulation system where we can actually implement these technologies, test, analyze, and we make decisions even before building the car. That's where my research comes in. So my PhD research topic is sound synthesis of autonomous vehicle, where the goal of this PhD is to develop a framework for rendering real-time, event-dependent spatial audio cues, moving and static. Once that framework is developed, we evaluate vehicles' operational conditions and also the passengers' physiological and psychological reactions, and to finally understand the correlation between vehicles' acoustic attributes and our psychoacoustic factors. Because even though we make the most finest sound of the car, at the end of the day, humans are going to sit inside the car. So it is important to evaluate the psychoacoustic characters of humans as well. So how we do that? We measure, we do a lot of measurements. So this is me wearing a binaural head and sitting inside a car, and we also use stereo and other methods. So what we do is we do several maneuvers like a run up, goes down, which is like we raise from 0 to 100 or come from 100 to 0, and also we measure constant speed and we synthesize these audios. So we use these measurements, and along with this, as Arsha showed in his previous slide, we also use an anechoic chamber. We take the same model of car inside, and we also measure the cabin's impulse response and the cabin's response and apply it to this algorithm or tool. So what this tool does is take a limited set of measured data and give us unlimited data. So basically, based on the throttle position, we can predict how a sound is going to play in that specific position. And the sound can be decomposed into orders and broadbands. Orders are just harmonic contents, like how we use in chords, like let's say a C chord, and broadband is just the background noise. And we record this total sound. And we break it down into orders. So this is just the engine noise that you hear now. And we then separate the background noise. We heard a lot about source separation today. It's similar to that, but we separate orders here. So, but now the challenge is, the passengers are not sitting in the car upright, and the driver is not holding the steering and focusing on the road anymore. So there are no drivers in the autonomous car, and the technology is evolving. So it offers new challenges for engineers and creatives in this platform. First is you're not paying attention to the road or your surroundings, and you're in random positions inside the car playing games or something. So how do we approach it? So you cannot have a fixed head position. You cannot have a driver and 3 passengers. So now everyone is considered a passenger, and we need to make sure everyone inside the car is aware of the surroundings and aware of the alerts that is coming from different directions. So we use spatial audio technologies for this. So what is spatial audio? Spatial audio is generally a 3-dimensional audio experience where sound is coming from all the directions. It can be rendered from multiple speakers, and also can be acquired using specialized microphone arrays like an ambisonic microphone array. So this is a topic which I did in my master's degree. So it's basically to emulate space. As you can see, this is a nice octophonic room from Maynooth University, where the listener is at the center and 8 speakers are around. And I want to digitally simulate this room into a software, which is what you see here. These 8 knobs represent this 8 speaker, and the listener is from the center position. And there is also a paper published on this, which you can find from this link. And this is also open source, so you can check the Git and try and use it. So how we did this is basically we take dummy head microphone and we apply convolution as explained in the previous talk. But I'm not going to go in depth of this topic and explain all these formulas. I'm going to simply explain what I did. So I played sine sweep from each of the 8 speaker with respect to the listener's position. So we get, for 1 speaker, you get left and right. So for similarly, I took for 8 speakers and I developed a application using a language called C Sound, and then developed a GUI to build this software. So it does convolution in quasi real time, if not actual real time. But there are quite a few limitations here. Since the head mic is just fixed in one direction, what about if the heads are turning? So what will you do in this case? Or each and every humans have different ears, different body, different head sizes. So the sound coming from one direction and hit your ear is going to have some diffraction, and each humans are going to hear a different sound. So our ears are, it's called acoustic fingerprint for a reason, because every human have a unique hearing capability. So you have to apply an individual HRTF equalization before it reaches one's ear. So how do we do it? And finally, how do you get more spatial resolution? To address this, we use ambisonics. Ambisonics is basically, it encodes a three-dimensional space using a set of mathematical functions called spherical harmonics. In the first order, it has 4 channels, where the W channel represents the sound pressure, and the other channel W, X, Y, Z represent 3 angles X, Y, Z. So in its first order, it has 4 channels. As the order increases, the channel also increases, the spatial resolution also increases, the file size and the processing restriction also increases. So we have to make a right trade-off and use the right microphone and use the right processing to get a real-time rendering of these signals in our headphones or in our speakers. We have already measured quite a few spaces and also quite a few cars using this microphone. As you can see here, it's a Zelia microphone. It has 19 capsules in it, strategically positioned so that it captures audio from all directions, and it can be encoded into the spherical harmonic domain for processing. So the advantages of this, you get high fidelity spatial reproduction for sound synthesis and NVH analysis, and also one big advantage of ambisonics that it can be rendered into any mediums or any formats, 5.1, 7.1, Dolby, or even if you want to create your own speaker formats, you can also adapt to it by using SOFA files. You can create a SOFA file and use ambisonic. So it's very flexible in terms of reproduction and rendering. And also with the use of a head tracker, or if you can track using your camera, your head movements, it can also dynamically adapt for better spatial sound perception. So the overall goal of my research here is to contribute to the advancement of autonomous vehicle technology using the role of sound and audio, and also inform the design and implementation that prioritize safety, efficiency, and passenger comfort, so that the manufacturers can make the right decisions even before building, which saves cost, time, and also gives us better results. And to finally have a holistic understanding of human-machine interface in the context of autonomous driving. Thank you so much. And this entire research was funded by European Commission through Marie Curie Scholarship through the project Gap Noise. Thank you.
Any questions? Yeah.
Hi Joshua, thank you for the presentation, it was great. We at Harman also do something similar. But I have a specific question with respect to ambisonic reproduction, right? You said you can decode it to 5.1, 7.1, binaural, all of those. But in a car, it's a very specific case where you have speakers that have restricted frequency ranges. On one side, like one door you take, you have 3 different speakers, tweeter, mid-range, woofer. So the fundamental assumption in ambisonics is that there is direct line of sight. All sound decoded from one point in space. Come from one speaker, right? How does it sound when you decode an ambisonic recording into a car speaker system?
Very interesting question, thank you. So I got the same question 6 months back, and I started investigating on it, and I came on a topic called crosstalk cancellation, where 2 speakers are placed close to your ear, which mimics binaural, but instead of using an headphones, you place 2 speakers in your headrest very close to your ears. That way, you can isolate your space. I think you're familiar with that concept. Using those technologies, you don't only utilize the line of sight speakers, but the ones that are closer to you. So the rendering is more personal.
Okay, understood. Thank you.
Any other question?
So I saw as many as 8 speakers in your setup. And there's this recent trend for MEMS speakers, right? So like, where is this thing going? Is it going to be like a lot of speakers all around, because we already have so many cameras, of course?
The speakers in a car, you mean, right?
Yes, of course.
So it's going to be placed like the recent cars that are coming out. It's not just 4 speakers anymore or 8 speakers anymore. For example, recently a car in India came out with its first Dolby Atmos setup, and also the car I showed here, EV6, it has 16 speakers built into it. So the decision is made by the manufacturer themselves. This theory proves a concept which builds a framework which anyone can take and apply it as they want. That's the goal of the research.
I see. Thank you. Very interesting.
Right, we have one more question here.
Hey Joshua, I have a follow-up question of this. So you mentioned something about cross-talk cancellation, right? So it's basically placing speakers right behind the ears of passengers. So are you planning to create profiles for different passengers? So like say someone is shorter and they're sitting in a car, their head position won't align with another passenger. So how do you address that issue?
Indeed, it's still an ongoing research. So how we are planning to approach is basically to have a speaker that will have a bit more wider depth of spread or depth of field, wider imaging. So it's still in progress that we have to find the how accurate it is translated.
So, any other questions?
So it's a very basic question. So I would like to know about what about the noise cancellation mechanisms that you use in the spatial audio there inside the vehicles? What kind of a progression that's happening there in noise cancellation techniques?
So noise cancellation and spatial audio are entirely two different approaches in acoustics. You don't necessarily need to control the entire noise or apply an active noise cancellation to render spatial audio. Noise cancellation can be approached in two ways. One is by using certain materials to block sound from entering into the car, which is an entire research topic on itself called metamaterials. They research on what materials to use and how they can insulate a sound. Another one is active noise cancellation, where you use yes. Yes, it's basically how it works on headphones. It's very similar.
Oh, okay, very similar. The same way that's
the
works for the 3D spatial
yes,
also.
the theory is similar.
Similar.
Yes.
Oh, okay.
Any other questions? All right, I think we are good. So round of applause for Joshua for such an amazing talk. Thank you.
Hey everyone, we are towards the final stages of this event, and before that we also had an event last 2 days, which was the Music Hack Day. Some of you were there, some of you were not there. So just to show you some glimpses of it and just to talk a bit about what happened there. So we started off with some pretty amazing workshops by Pradeep, Sangarshnan, Arjun, as well as one by me. And also we started with a lot of idea jamming sessions during the hack day, through which participants formed some teams and also got to just discuss some amazing ideas which are not feasible. Some of them which were feasible, they started working on. Here are some photos of them working. And eventually we had 3 winners who will be presenting here today. So each of them I'll just call out one by one. So first team is Team Mute, Unmix Mute Practice. Please come on stage, Vedant, Masaki and Syed.
Hey guys, we're Team Mute. Our whole idea was to build a musician's toolbox for practicing new music. Like Sid mentioned, I'm Vedant, this is Masaki, and this is Ali. Before we go into what Mute is and why we went about all of this, I just want to go through my process for learning and practicing a new song. So step one for me is solo the drums for any tricky sections that I can't really figure out. Slow it down to identify what exactly is being played. Practice, practice, practice. And once I'm comfortable with improvising over what's being played, I want to remove the drums and just do my own thing. And of course, as a drummer, metronome, metronome, metronome. I always want that click track. Now, here are the problem statements that we're trying to address. We want to be able to solo and mute specific instruments, slowing down or speeding up the entire track, and of course, creating a metronome that follows the track perfectly. Not all songs have a perfect tempo. Not all are recorded to a metronome. So if I have a song that's actually at 143.25, setting a metronome at 143 BPM will eventually lead to it diverging over the course of the entire song. Our goal was to create a metronome that follows it perfectly. Why does it matter? Like I mentioned, to help people like me who are learning, and of course professionals, play along with their favorite songs, either just for practice or even live. Let's see Mute in action, actually. Let me give you a quick demo. So as you guys could see, we had a little link where you could paste a Dropbox where you could paste a YouTube link. We would then download that. We also allowed you to enter a speed, like a float value, which let you speed up or slow down the song. In the case of the demo, we'd slowed it down to 80%. Another thing that you did see was this is a very DAW-like functionality that we wanted in there. So the ability to mute, solo, and adjust relative levels. So you can make your own mix that you want to play to. Additionally, all the lines that you saw there were the beats that we detected. I don't know if you guys noticed it, but when it sped up, we actually had the beats speed up along with that. So we had a metronome that followed the song. We also added in a little functionality that when in case the model detected a beat at the wrong place, we'd allow you to actually click on it and move it around and fix the metronome. Okay, so how it works. Step one, the user pastes a YouTube link into our UI. The server then downloads this audio and processes it, whether it's time stretching or beat tracking. We also did want to include pitch shifting for you vocalists out there. Unfortunately, with the 24 hours or so that we had with the hackathon, that wasn't feasible. Future work. Step three, the server then runs stem separation through, we were using a model called DMUX, which I think has been addressed today a couple of times. Step four is the actual UI that you guys saw, where the user can play around with the tracks as they want, mute and unmute the stems, and play them with a metronome. Key features, like I mentioned, source separation using DMUX, time stretching and pitch shifting for practicing at different speeds, mute and unmute stems for focus practice, downbeat detection to create a metronome that follows the song, and this ideally would be all web-based, so you don't need to install anything. You just paste your YouTube link and go. Thank you. We've been Team Mute. You can reach out to us for any questions, or if you guys want to try it out on our Discord or Instagrams. Thanks.
Thank you for that, Team Mute. Was team mute, and we actually had 10 hacks submitted at the end of it, apart from all the ideas that didn't make the cut. And out of those, these 3 are the chosen winners, and I welcome the next team, the ContraPunks. Is the stream live as well? Yes. Okay. Yeah, Abhinav and Vibhav.
Thank you everyone for staying till the very end for listening to the Hack Day talks. We are ContraPunks, and I'm Vibhav. This is Abhinav. We created a tool called the ContraPunk, which is a real-time accompaniment generator. So it's based on counterpoints in Western classical music. The reason it's called ContraPunk is because contrapuntal writing in classical music just sounds way better than counterpoint, and sounds a little fancier. So you took contrapuntal and just made a name out of it. And I'm gonna call Abhinav here to explain what counterpoint is.
Hi everyone. So counterpoint is a Western classical music theory concept wherein if you given a melody line, we try to generate 2 or 3 or multiple melody lines based on the original melody line, and it follows a set of rules which are already there, by analyzing pieces of Bach, Mozart, all these guys, and it's based on consonances and dissonances. So we try to, as part of our code that we implemented in Python, we've tried to implement these rules in our algorithm, wherein we leave out the dissonances such as seconds and the sevenths as the suggested notes, and we've tried to create the secondary melodies motion as far as possible to move in a stepwise motion, and to avoid parallel fifths and octaves because they just sound like the melody itself. So we've tried to harmonize the melody while the secondary melody sounds an independent melody on its own. So there are several types of counterpoint species. We've tried to do the first species, just the first species, wherein the one note is mapped to the one note on the generated melody, and the second species and the third and fourth species, they all have multiple notes being generated on the map to the original melody. And yeah, I'll invite Vibhav to discuss the features of what our algorithm does. And
so we made a simple Python script which acts as a standalone application. It will basically take in your MIDI input and then split it and output to multiple buses. So you have to define these buses from beforehand into Mac. So this right now it only supports Mac. So these are IAC buses, inter-application communication buses. And what we do is, before these are sent to the buses, we pre-process these MIDI inputs to change the notes of those MIDI messages. So we basically take the list of possible notes that we can input, and then score these notes, which would be the best possible note that we can put in next, and then we use a random function to pick out the random note from there, and then also record these previous inputs so that next time we are generating an output for the next note, so we know what came before, and then give a better output. So the support in pre-processing modes is basically how we went about making this tool. So first we did diatonic intervals, so we did thirds, so that every time, so if you have 4 outputs, every time you press a key, you get a 7th chord. Then we did for diatonic with random, and then we added some contrary motion, so we gave more score to notes that went in the opposite direction. And then finally we added one more rule, I don't remember now what it was exactly, but which let us know that okay, we've kind of finished all the standard counterpoint rules. Then these are the current features that we support. So I'd like to go ahead and show the demo for this. Yeah, so here we have one second. So here we have the UI for ContraPunk, and it was made in TK Enter in Python. And see that we have the MIDI input for it, and I've selected 4 outputs, and then I'm selecting the IC buses that I've defined, like I've added in Mac. And then you can see the key that I want my diatonic notes to be generated in. And then I'm saying add strict, so there are different modes, and I'm saying that I want strict counterpoint rules. Then I press the start button. I usually forget to do that. And then here Abhinav is playing just random melodies. So here you saw that these, one second. So here you saw that these melodies were generated, right? So the first instrument that is there, so it's taking the input directly from the MIDI input and then copy pasting it. But the outputs the inputs into the instrument 2, 3, and 4, they are generated based on counterpoint. So 2 is a counterpoint generation of 1, then 3 is of 2, and 4 is of 3. So that way, like we thought like it would be a good idea to do that. So we kind of create like a very good sounding like harmony together. So you can also call it a chord generation at this point, because that's how it acts. So the next we are planning on supporting global tempo. So there will be some sort of click track, and you can play to it, and the harmonies that are generated or the counterpoints that are generated are kind of have like a life of its own, and it would sound like different people who are like playing those tracks. And then these are some other supports as well. And if you'd like to see something in this tool, please reach out to us. This is our contact information. Thank you so much.
Thanks, Abhinav and Vibhav. At this point, I'll also like to thank couple of our prize sponsors. One is Pitch Innovations. Krishna is here. Thank you for sponsoring the prizes. And also a shout out to Splice for some of the prizes, as well as Akash Sharma, who goes by the pseudonym Sound.Codes. He was kind enough to handcraft some synthesizers as prizes. And finally, we have our third team, Pan Symphony. Please welcome Dr. Balamurugan, Ritik, and Guru Prasant.
Good evening all. We're very happy to again be here and give our talk on the yesterday's presentation in a very glimpse manner. And we have our team of my Balamurugan and Hritik and Guru. So immediately I jump into the presentation. So what are the problems in hand? The problem statements were given by Indian Music Heritage Museum, and then we have taken out of the 12, we have taken addressed 4 use cases in that, and then it has been clubbed up over here. One is the understanding the pattern formation using the ragas, then identifying the fundamental pitch and the accuracy of the soar note detection, then exactly identifying the 12 swaras and also the 16 swara system. Apart from that, we also try to implement the 22 swara system also. Then finally finding out if a tune is played with a raga, then we have to find out the rasa out of that, out of the navarasas. So all these things are gamified, and then we have presented a small game for that. What is the why we need such a kind of a game? Because everyone, it is very you all know that it's very restricted to only a few people. Classical music, of course, all over the world, classical music is only restricted to few, and then because of it's of the complex nature that is present over there, so we have to attract more people. That's what when we spoke with the director, she told we need attract more people, and it should be more enjoyable and trending, and there should people retracting from the study case should be high. The retention rate should be good. that is what they told. So for that case, we have designed this game, and you can see there is first one is the Shruti system, and the Aranga, then the Swara detection will come. How we are doing? The first we are going to find out the 12 swaras, the Sarigama Pada Nisa. That one has to be detected with proper Sa Re 1 Re 2 Ga 1 Ga 2 Ma 1 Ma 2 Pa Da 1 Da 2 Ni 1 Ni 2 Sa. All these things should be placed as boxes, and then when they get the swara over there to the ears, then they should be able to click whether which swara they are hearing, and then they have to click the button. Like that it starts. So that is basically, then slowly the patterns will be formed and the ragas will be formed next. Then the patterns they have to form, and then they have to develop it. Then you will see the demos over here now.
So basically, in order to, as we seen from the previous task, we couldn't have a standard electronic sitar or standard electronic classical instruments. So we took the basic pitch, like C pitch of a sitar instrument, and we generated the 12 semitones for us to implement these things. So for the overall UI, a player can free practice and get the gist of the notes that they are being played, and so the player is being rewarded based on that. And for level 2, we hide the visual cues that are being given in order to focus only on the auditory. And based on the levels, the complication also increases. And you can compose your own pitches, like in the end of the video as you see, in order to develop your own patterns.
Here it is about the swar note detection or anya swara detection. If there is one raga, there are some ragas where there are upanga ragas and bashanga ragas where there are the anya swaras are possible. Like that, that's a swar note actually, where when there's a pattern, and then if there's a pattern is played, if you're able to hear to that, and then if there is going to be a glitch over there, you have to identify and say where that has occurred. That one also, for the practice purpose, we are giving it over there. Simply we are taking for the simple C major Shankarabharanam, we have taken as a twinkle twinkle, and the first phrase is given over here.
What you saw is that a demo of detecting the off note. The person is used to hearing the normal and accurate melody, and when an off note is being pronounced, the player should be able to detect it, and the scores would be rewarded based on that.
Okay, then the entire the system of 12 pitch system, which we see in the Western side, but it is our classical music is not based on the 12 pitch system alone, and it is totally based on the 22 based system, and the entire Melakarta scheme and the parental and Janya scheme is all based on that. So we have to train the students based on the 22 Shruti system with the Gamakas over there. For that they have made this kind of a microtonal analysis also for the pattern recognition. Then comes the rasa identification. Out of the Nava rasas, we have to identify, because the final element of music is emotion identification. So for what kind of a ragas, there are classifications of ragas based on this too. When a phrase is heard, and such kind of a phrase, what kind of an emotion that is evokes over to you, that also the student can get learned out of the ragas. Initially it will be given through very simple patterns, then complex, a single raga with a different kind of several different bhavas also can be given over there. You can hear to the
So as you can see, when the player click the Shanta as an emotion, Shanta is basically peace and happiness. So when you hear the emotion provoke this happiness, and when you click that and get it right, you would be rewarded based on that.
So it is it's a very basic thing. The raga in which the Harivarasanam, the song which was played over there, is in the raga Mathyamavadi, and Mathyamavadi is typically it is patterned to the rasa of Shanta there. So this one we have to. These are highly psychoacoustics. As I told, it is depend upon the person. Ethnic things also come into picture. The same thing what we heard may not be the same for a non-Indian. We don't know actually what is going to happen. Those are all research topics. I don't want to go there. But the Mathyamavadi Raga was mapped to Shantarasa. That is a basic thing. That is what given over there. So this can be used for the key features. It is all reward focus. We can give reward points for the music, and then auditory training, the pitch training, the alankara, the pattern trainings, and then he can create his own alankars over there, and then get used up with the ragas. But then the 12 system can be converted to the 16. That is called as the in the Melakarta there are two different types. In this 12 and 16 are possible there with the same things, and also then the next complex Gamaka patterns using the 22 systems is also possible with this game as well.
Thank you.
Thank you.
All right, thank you so much everyone for taking the time to be part of this event. First of all, how was it? That's all, like only few responses. Did you all enjoy? Yes. I mean, so assume that you did not eat any food, you don't have any energy, but you have to convey how much you enjoyed. Did you really enjoy it? Yes. Okay, nice. When we edit the final version, we'll just add some more sound effects. I am from Soundly, so I can do all of that. So, right. So for those of you who attended last year, you will know that there's nothing. If I am here on the stage, there has to be some story. Last year, I overused the word ecosystem. If you see the live stream or the panel, you'll see I was just talking ecosystem everywhere, because that was the aim for. Like, we were all working together to just make things work. And this was like last ADCx India was not the first attempt at this. Like Ajay mentioned, there has been efforts done for many years by various people who are also luckily all part of the organizing team, which I'll come to in a bit. So the reason for the focus of being the word ecosystem was that we wanted to bring everyone together. There are people doing some things in different pockets of India, different universities, different colleges. And when they meet together, when they share ideas, they realize, oh, you know what, I'm not the only one. And that was the reason why I was overusing that word. This time I have a different word. Any guesses what that new word is? Ecosystem community is like almost similar. Any other guesses? Oh my God, no. Let's not get political. So the new word, the new hype keyword that you will hear me say a lot in these next 5 minutes is momentum. The reason for that is we built an ecosystem. Hopefully a lot of people in India now know there is something called music tech. A lot of people already knew, but now even more people know. And the way we build the momentum is by hosting these events, because believe it or not, 6-7 months just go by, you don't realize how much effort goes into it. Like we have to ideate so many things. There are so many moving pieces. There is the venue, the catering, which is like the logistical, but then we have to make sure that we are reaching out to the speakers on time. We are doing the selections properly. We are mindful of the live stream setup. Like there are a lot of things that goes on, but all that effort is not just to do an event, it's to build that momentum, right? And while that is slightly difficult part in a sense that you really need to make up your mind of why you're doing something, because it's a not-for-profit event. None of the organizers get anything monetarily. I mean, we get a lot of things feeling-wise, but nothing monetarily. So you really need to have a very specific reason of why you're doing it to build that momentum. And the reason I'm bringing this up is that building the momentum is one part of the equation. The rest of the equation is about retaining that momentum, right? Taking it forward. And that part, frankly speaking, is really, really easy. So if you have met someone here and you have shared your contact details, if you have shared an email ID, if you want to like discuss an idea, what is the effort required? You take your shyness away and send them an email, right? Compare that to 7 months of effort to host or build a momentum, right? So what I'm trying to say here is that now that the momentum is in place, let's do some small efforts to keep it going. If you met a friend here, if you made a friend, if you met a person who you might want to collaborate with for your startup, for your company, or maybe hire for jobs or internships, whatnot, let's actually take it forward. And if you, for example, are a student who met somebody and you're like, hey, that person is such a senior person, like 40-50 years of experience, should I write an email to that person? The answer is yes. The worst that can happen is that person will not reply. And believe it, or like I have done this many times, people who are super experienced are the fastest to reply back because they understand your point of view, because they were doing this when all of this was not even known here, right? So again, that's the whole story. Like I don't want to bore, I don't want to overuse the word, even though I said, but yeah, let's retain this momentum. Not sure when this event will happen again, but if we see that momentum going down, that will be one of the reasons why we would want to do it again. When that will be, you will get to know how you will get notified and stuff like that. But let's just a quick yes, at least. Will we all like work together to like retain this momentum? Yes. Nice. All right. So keeping the story short. So it's time to thank a bunch of people, because again, it is impossible to do these events without support. The first thing that we should thank for is the sponsors, starting with Juice. A round of applause for Juice. So Tom and the entire team at Juice has been really supportive. All we had to do was, hey, we want to do ADCx again because we want to keep the streak going, because streak is really important. One thing is starting your engine, but retaining is very like a critical step. And the first reply from their end was, when is it? No other things, like what are they going to gain? Nothing, just when do you want to host it? And then we immediately get to finding and other things. So shout out to Juice. On the same lines, Pace, the team that also, Juice and Pace are the teams that also run the main ADC event. So they have been a really driving factor why these events have been happening for the past 2 years. So big round of applause to the Pace team as well. This time we were also joined by a team called FOSS United, which is free and open source software. And they were really helpful in making sure that we were able to give away diversity tickets. And they're also here in person. Ansh, are you around? Oh, Ansh is sitting right at that corner. So if you have not met Ansh, like just make sure to meet him. The FOSS United team completed 5 years of their effort. They have been actively helping out different developers with open source software, and he'll be really helpful for you maybe to connect with him and maybe participate in the FOSS events that might be coming up. So first of all, a big round of applause for them to complete 5 years. And also for sponsoring event, the diversity tickets part of the event. Now, thanks to our volunteers, if things went fine, if there were no glitches, that is a lot of effort from the volunteers. And I prefer to personally mention each person's work and profile. So Jigyasa, where is Jigyasa? Oh, Jigyasa is here. Round of applause for Jigyasa. So Jigyasa is into software development. She's a software developer, but she's also a musician. So she's kind of exploring the world of music tech, and I'm hopeful that in a few years you'll switch. I hope nobody from your company is watching. Or maybe you start a department in your company. Who knows? Yeah, that's a better way of saying it. The other person is Pradeep Matthew. Where is Pradeep? Shout out to Pradeep. Pradeep has been like super active in making sure that everything runs on time. Everybody gets everything you need. Even if you, for example, came a little bit late and you did not get your goodies, Pradeep probably came to you, to your seat and helped you out. So it's just his commitment that I want to applaud again. Shout out to Pradeep. Then we have Ronak Burde, probably the only few people in India who understand game audio. And from my experience, there are less than 10. So shout out to Ronak. And then we have Ali, who you definitely met if you were here on the hackathon. Yeah, I don't care where you are, Ali. Oh, but he is there because everybody else do care. So Ali is basically the one who is geeking about synthesizers. And he actually messaged me on WhatsApp before he was accepted as a volunteer. He was basically bribing me. He said, you know what, after the last event is when I started exploring synthesizers and all. I don't know how much that was a buttering or was it actually a reality. Okay, so it was actually for the YouTube audience, it was a truth. So the event helped him out and he's helping us back by volunteering. He's making sure everything that we record is all backed up. He made sure that the hackathon stays fun. And I think he also made his spring reverb, which he is going to sell under the name of Karibi Industries. So free shout out to you, Ali. So round of applause to Ali. Whenever you make a profit, you know, I'll send you my bank account details. And then we have Arjun Bahuguna, who not only is helping out with photography today, but he also hosted a workshop. He has been running the book club sessions on our Discord server, the Music Tech Community Discord server throughout the year. And he has been like a super active participant in the audio community. So shout out to Arjun. And then we have George Panigar. George is here right at the wall giving a nice pose. So George, okay, let's clap for him first. So George is a creative coder who also is exploring audio and coding and visual arts and everything together. He was a speaker last year and he's a volunteer now. So you got to upgrade, man. Just kidding, you'll probably be the organizer next time. So shout out to George because he has been really helpful throughout the event, making sure everything stays on time. That was just a joke. All right, so the organizers. Again, you might have just seen my name in the emails and stuff, but there's a team that works really hard on making sure that things happen on time. First of all, shout out to Siddharth, who is the CTO and co-founder of Beethoven.ai. I spoke a lot about that last year as well, and I'll just repeat that. There are very few companies in India that are actually doing something in audio tech and doing it ethically and making sure that we actually build something big from India. And Siddharth has been one of those persons. And with the event, he has been making sure that everything that we need is all in place. So shout out to Siddharth for that. Then the rest of the names that you see here, they could not be here. And that is because of the dates that were chosen for the event. All of these folks, I'll just introduce one by one. Nanditi and Computational Mama, they have this initiative called Ajaib Ghar. They made sure that we get the venue places sorted. They made sure that we improve the messaging that we use in all of the communications. They helped us with the diversity initiatives, and they have been like all throughout the planning stage. They have been really, really helpful. So shout out for Nanditi and Computational Mama. And then we have Manasvi Mishra, who I'm pretty sure that many of you already know, if he's probably watching right now on YouTube as well. So hello, Manasvi. Manasvi has been really key factor even last year in hosting the event. He's also been the driving force for the music tech community for the hack days, not like the last 2 years, but even from early 2017 and so on. And I'm pretty sure if you just message him with a question about audio tech, you will definitely get a response, not just a reply, but even a way to help you out in your learning journey. So shout out to Manasvi for being such a support for the whole event. And then we have Albin, who also is worked on the MTG group, and I think Siddharth and Albin are probably college mates in masters. And Yeah, Manasvi, Alvin, and Siddharth. So that's how the community gets formed, right? And Alvin has been super helpful in terms of making sure that we plan out the website properly and whatever is required in terms of planning the tech side of things. So shout out to Alvin for that. All right. Yeah, thank you. And then we have to thank the ADC team. You all met Bobby, for those of you who are here on time. If not, you can always watch the YouTube live stream. Bobby, Tom, Andrew, Ralph, Derek, Sophie, Jim, all of these folks are the ones who run the main ADC event. All of these are the people who we learned how to host an event, how to make sure things stay on time, how to make sure that it all feels professional and everybody in the audience feels welcome. So it's all their doing that we are trying to replicate here with our events. So again, big round of applause for the entire ADC team. And yeah, I want to also support and thank the supporting team from IME, Dr. Aditi, who helped us ensure that whatever we require for the event is available. To Sridhar, I'm not sure if Sridhar is here right now, but he's probably arranging the tour part of things. But Sridhar has been a troubleshooter all 3 days. Whatever was required for us was handed over to us in no time. We had weird asks, can we have this kind of setup? Can we make sure that we have this different podium because the previous one was sliding? And he just made sure that whatever we need is here. And if any of you have hosted an event, you will know this is not a very normal behavior from venue owners, right? And that's a really, like for us, it's a really helpful thing because we didn't have to worry about anything. Sridhar took care of everything. So a huge shout out for Sridhar. Then Shivraj, who was handling the mic on 17th on the hackathon. Coincidentally, Ali and other folks were doing some jams and their aux cable was broken. He made sure that he brings the cable required so that the hack and the fun activity can happen. And then I was like Pradeep was playing guitar and I was fiddling with the pitch knob controller. And then Ali took a video in which I am not even visible. So Ali, you really need to improve your camera game, man. But yeah, somebody else also probably recorded. So if you have a video in which I am visible, please send it to me. But shout out to Shivraj for making sure that we enjoy the whole hackathon and we don't have to worry about the tech. So Shivraj. And then we have Anand, who is standing right behind you, who has also been really helpful with all the tech required for the hackathon. Make sure that the audio is all sorted, especially for people who are doing hack presentations. You all know how it becomes tricky when you are in this area. So shout out to Anand for that. And then we have Sahana, who gave the music hack day ideas from IME that Bala and his team also worked on. So round of applause for Sahana. And yeah, I think it would be very unfair if I don't thank the live streaming team because Ganesh can anytime stop the stream and my whole speech will just get ruined. So shout out to Ganesh for being so sporty. Like anytime I give him a signal and he's always so active. Please don't stop the stream now, but shout out to Ganesh for that. And then we also have the person behind the camera, Chetan, and he also helped us with the group photo today. So congratulations to Chetan for helping us out with the whole event. And then we also have Prashant, but I don't see him here. Is he there? Oh, he's sitting in the console area. And he has been a support for Ganesh for making sure the live stream goes well. And anyways, his name is Prashant, so we have to round of applause for Prashant. And then no conference can work out without money. Team Alishan has been helpful to us last year as well as this year to handle all the finances. Again, it's not an easy thing to take care of. And Sandeep Sharma, Mukul, and the entire team of Alishan has been one of the major reasons that enabled us to do the event in the first place. So shout out to Team Alishan. All right, thanks to all the speakers for such an amazing set of talks. We have already clapped for them, but let's do it again. By the way, People Plus AI, the first talk that we had today, they had shared a doc with us. We'll make sure that it reaches you in the final after-event email. And a huge applause for all of you for being an active part of this, not just this event, but of the audio tech ecosystem. And hopefully you all will help retain the momentum and we'll be able to just make the audio industry in India as big as possible with or without these events. So a round of applause for all of you. Yeah, so quickly looking into the future, I'm taking a lot of time. Is somebody typing me? All right, so these are some of the important links that you need to notice. Any ADC mentor or mentee from this year? Okay, we have a few. So for those of you, and don't worry about like the QR, it's getting recorded in the live stream, so you can always take the QRs from there. So the mentorship program is basically ADC's approach to connect people who are in the industry and students who want to kind of get into the industry. So you can sign up for it. There is also an ADC newsletter. A lot of people don't get notified on time, and they were like, hey, we did not know that we could submit a talk. So how you get notified is through the newsletter. And if you want to watch all the past talks, it's all available for free on YouTube, and this is the YouTube URL. So the next step would be, please share your feedback. We read every single feedback, and whatever feedback we got last year, we incorporated this time. Make sure that if you have clicked any pictures or taken videos of the event, I will be sharing an email again, which will have a OneDrive link. You can upload the images to that. That way we'll all have access to it. Participate and do make submissions. Like if there is a talk, if there is an event happening in the future, submit a talk. Like don't be shy. Maybe it will get selected and you'll be here presenting it. So take your chances. Collaborate. The ball is in your court. Do whatever it takes. And these other next steps are actually from last year. But yeah, I think we can still do a little more. With that, I think I'd also like to quickly announce that the ADC 25, which is the main ADC event that happens every November, has been announced. Bobby shared a little bit about that in the starting, but I'll just mention the dates are November 10th to 12th this year. It will be happening in Bristol, but it will also happen on Gather Town. So it's a virtual way of attending the event. So you can not just attend the whole conference virtually, you can even give talks remotely. So again, take your chances, submit a talk whenever you get informed about it. And the way you get informed about it is through the ADC newsletter. All right. And the second last point is the most important point. Sponsorship slots are available. So any potential sponsors, I know one name, but I don't want to take that name, because that person said that they might be able to sponsor ADCx India 26. So you know who you are. All right, with that, it's a wrap for the online audience. So thank you so much, everyone watching on YouTube. Let's give a round of applause for concluding this event.